and sort of yeah, I guess like sort of being here, like having papers and so on. So I'd like to sort of say a couple of things about the highlights of the program. So we have we've had, I think, a record year this year. We've had 170 full paper submissions, out of which 39 have made it into the program. And these are spread out over 16 sessions over 3 days. We have 3 keynote talks, and then we have the usual sort of business meeting this evening, and then the banquet tomorrow. So I'd like to maybe give a couple, like sort of ask Alexei, the local organizer. I'd like to ask you first to give him a hand, because he's really been working a lot to make this happen. And I think he has a couple of details he'd like to share.
Okay, so I'm Alexei Gozman. I'm from IMDE Software Institute, which is a research institute in Madrid, and I'm organizing this with Antonio Fernandez Anta, so he's over there. So I just have a couple of, I have a couple of organizational things. So there's a very fancy screen, and unfortunately you cannot connect to it using HDMI cable, so we're using Zoom. If you're a presenter, you received an email with the instructions. Please make sure you read that email and have Zoom installed on your laptop, and that it has the permission to record the screen, right? So that's important, because you may need to restart Zoom for this. And please show up like 10 minutes before the session to check everything. Then, as Dan said, today we have a business meeting. Before the business meeting, we have happy hour with drinks. So the happy hour is a bit shorter than an hour, but the venue people told me that you can take your drinks here during the business meeting, provided you don't spill them on the, on the chairs. So hopefully this will make the business meeting more entertaining than usual. And tomorrow we have the banquet, but the banquet is not around here, so you would have to take the underground to the place where it is. It's like, will take like half an hour. So you all received a piece of paper with instructions on how to get there. So please make sure you read it tomorrow and plan appropriately. And that's it. Enjoy DISC.
All right, so with administrative details out of the way, I want to introduce our first keynote speaker, Stefan Schmidt, who is a full professor at TU Berlin in Germany. I think he sort of grew up in the DISC community, but then moved on to do great things in the networking community. So I think he's had a particularly diverse background, both in terms of affiliations and research activity. So he's held positions in Switzerland, Germany, Denmark, and Austria, as far as I know. And he's been awarded the IEEE Communications Research Award a couple of years ago, as well as an ERC Consolidator grant. So I'm really excited to see what he's going to talk about at the intersection of distributed computing and networking.
Thank you so much, Dan. All right. Actually, next year, DISC will be in Berlin. So my incentive here is to give you so many research directions and open problems as I can. So you have a lot of submissions, a lot of accepted papers, and a lot of registrations, I hope. All right. This talk is not about wireless networks. I do that. I think someone needs to pull it in or not. I'm sharing the screen. Yeah. Okay. Thank you. All right. So this talk's not about wireless networks. DISC and POTSI contributed a lot to this area, right? But there's also interesting things to be said about wired networks. And I want to convince you today that may be worth also looking into. Maybe you may wonder, okay, wireless, a wire network, that's really fully understood, right? It works, everything is so easy, it passed the test of time, it cannot be changed and it should not be changed, right? But it's actually an area where really fantastic innovations are happening. Okay, so a lot is going on all the layers. So maybe you remember these layers in networking, like application layer, transport layer, network layer, and people are trying to improve performance and dependability of these networks. And it's still very interesting because of a lot of constraints and a lot of structure and a lot of models that are quite discrete and easy for people to define compared to wireless networks. Okay, so let's turn back time a little bit. Why are networks evolving in the first place? So initially, the internet was designed for a very different purpose and very different context, right? So this is, of course, not the very network where, like, for example, TCP was invented, but since the early stages, there has been a lot of change in the scale and the applications. So now I argue we enter the age of computation. So even today, all of us use maybe not gaming applications, but applications related to health, business, streaming, entertainment, and all of them are hosted in the cloud. So we really require these huge data centers and do a lot of processing there. Actually, there is other evidence that we entered the age of computation. This is one of them, NVIDIA, the fastest growing company ever. Okay, so you've seen a huge rise in the bots or buyings of GPUs. This slide I actually stole from Thorsten Höfler that showed us last week. So some of the models are computed not only across data centers, but even across multiple nuclear power plants. So we need a lot of energy, a lot of computation for our new workloads. And oops. Actually, some scientists, they even define like societies based on the amount of energy they can consume. Okay, so there is this Kardashev scale that maybe you've heard about. So we expect that the more we evolve, the more energy we will consume. And also the more computations we will do, I think. Yeah, there is other evidence. You heard about the Nobel Prize that actually in physics, it went to computer scientists for doing work on machine learning. Also in chemistry, Nobel Prize, we could claim some of it is actually related to computer science here, so we can be proud of that. Also an evidence for computation. People have joked that maybe we should also get a Nobel Prize soon in the area of blockchains. Maybe for economics, there's a lot of innovations there, right? Actually, last week, Thorsten also asked, maybe ChatGPT should get sometime a Nobel Prize in literature. So let's see. But actually, a lot of these applications are not just running in data centers, but they're also distributed applications. So traffic is, like communication traffic is rising a lot in data centers, and we need bigger and bigger machines to handle that traffic. And the infrastructure, especially of the network to the data center, from the data center and inside the data center is growing very fast. Okay, so this is a visualization that a colleague of mine in KTH did, Marco Chiesa. This is like to visualize how much traffic a router in a data center has to handle today in the core. So if each of these drops is a packet, that's like roughly the amount of traffic that these core routers have to handle today in peak times. The problem is that there's also something like the Moore's law in networking, and it's not something different from the other Moore's law that we know, because it's all about transistor density rates that are stalling, power density rates that are stalling, and we need more and more equipment and larger networks to handle this traffic. And this is also opportunity for research, and I want to show you a bit why. Actually, people are also thinking to run like computations on the routers, for example, to speed up all reduce operations. So the network really becomes a distributed system as well. Okay, let me show you some of the opportunities on the different layers. Some of them I don't go very deep, others I go a bit deeper, okay, to see that really we see the models. Congestion control, a very decentralized problem. Do you know how many packets get dropped in the internet today? What fraction of traffic gets dropped in the routers today? If I guess, you think maybe nothing, right? Because it's very evolved. 10%, not so bad. So actually quite a significant amount of packets get dropped. And not because of congestion, really, but because of the way we control congestion. Okay, so why gets traffic dropped? Because TCP, it doesn't know like what's the state of the network. It needs to guess like how much can I send or at what rate can I send. And the only way it could learn about it is like, is there a packet drop? Okay, so TCP just tries to send faster and faster until I get a packet drop, and then I say, okay, now it's probably at the congestion point, and then I reduce. And of course, that worked very well. And the question is like, how optimal is this, however? And this is something you know from your lectures, maybe yourself. So there was this, or is still around, this additive increase, multiplicative decrease approach that is actually amazing success because it has been around for over 30 years. And the traffic since then, since it was introduced, it increased by a factor of 1 billion. Okay, so it's really a different internet today. However, this is like the tooth pattern that we know, or that you maybe have seen, that we try to increase the rate, and then if there is a drop or a packet loss, then we halve the rate, and then we increase it again. And this means that roughly we have like 75% of efficiency in these networks. Now there are better versions. For example, TCP in Linux, it's called Cubic, so maybe you know that one. It tries to be a bit more clever by just increasing the rate a bit faster until it goes close to the capacity or where it's dropped last time, and then we have it. And by doing that, we try to get a bit better throughput here. Okay? But there is still a lot of efforts that are currently being made, not just in data centers, but for example, you probably know about Google's BBR. There is Quick, Netflix. So we have a PhD student that works at Netflix now. And she is actually studying like how to improve congestion control for Netflix. And it's a very exciting area. The direction here is that we don't just take into account loss, but we also get some additional information from the network, like latency, queue length, and other information. Okay, so this is the trend. I think there's a lot of opportunities for this here, because a lot of these protocols don't have any theoretical underpinnings. Actually, when Google introduced BBR, there was a first version, and then people noticed, oh, actually when Google introduced something, they can do it really fast, right? So they introduced BBR and then had a huge deployment very fast. But then they noticed, there's actually a bit of unfairness there. So they made another version, and now there's actually the third version in planning. So we are still doing going a bit back and forth here, and I think it's good to do this experimentally and by simulations, but I think it would be really nice to have some like theoretical underpinnings for this. Let me go to the network layer. I wonder how many of you know how actually packets are routed in the internet today. Do you know which routes packets are taking in the internet today? Yes, someone knows. They always go shortest paths. Okay, so the routers, they do distributed computations of the shortest paths. That's it. But nevertheless, I can influence the routes packets are taking, like for example, Austria Telekom or Deutsche Telekom. How do they do it to guide kind of the direction of the packets? right, that's intradomain, but like intradomain, like inside their telecom network itself. Yeah, you can do it physically, right? But there's actually another way to do it. You can just reconfigure something else. The link weights. Okay, so the routers always compute shortest paths. So the only way you can change the routes, you need to change the link weights that changes the shortest paths. So this is a bit classic now that I show you. I show you the new things in a second. Okay. So let's say you have this network, and all of them have capacity 1, the links I mean. And you have 2 sources of traffic. One is from S1 to D, and the other one is from S2 to D as well, and both have demand 1.5. And the link capacities are all 1. Okay, so how can I route this traffic? So, yes, so this is the second demand. So, usually I want to, of course, not violate any capacities, and I want to minimize the load on the links. And let's say all the link weights are 1. What would happen now? So routing is shortest path. So what would happen to the traffic from S1? Half of it would go on the top because it's the first shortest path, and the other half goes at the bottom because it's the second shortest path. Okay, so like a 50-50 split. So that's how routing works, or traffic engineering works. So now, this is good, right? The link utilization is less than 100% because we have an equal split. If you have any questions, by the way, just tell me any time. We can have long questions at the end, of course, but I will tell you whether your question requires a long answer or a short one. So, however, what happens to the second traffic? So the second flow from S2 to D, that will violate capacity because we only have 1 shortest path. There is just this direct link there, right? So what do we do if we want to serve both the first traffic and the second one? Not at the same time, okay, but one after the other. We can play with the link weights. But unfortunately, it's not possible. Okay, there is no link weight assignment to serve both these traffics at the same time, one after the other, okay? So the reason is because we have this indirect control over the traffic. So we can only change the link weights. We cannot directly steer the traffic itself, because in principle, it will be very easy, right? You could just have the second flow also going half there or half on the top, and you could easily serve both of them, but due to this indirect control, that's not possible. Okay, any questions? This example? Yes? Then, first of all, you cannot, okay, this example is a bit simple, you cannot do zeros. In this example, it actually works. In practice, you need to have something larger than 0. Okay, good question. But what you can do is segment routing. And like maybe you know valiant routing, this is a very important concept in oblivious routing, which again is a very distributed way to do routing in networks in general. And how it works is that you can define an intermediate point of a route between source and destination. And in valiant routing, you can define a random, or you define a random intermediate point. And here you can choose one. Okay, so this is the new innovation they do in IP networking, that you can define this intermediate point. Okay, so if you define that, you can go shortest path from S to this waypoint. You cannot have multiple ones, and then you go to the destination. So now you could do these things. So even if you have link weights 1, you could say, okay, I define this waypoint V, and then half of the traffic goes shortest path from S2 to V, and then from V to D, and the other one goes on the top. So I can force half of the traffic to go shortest path to this waypoint. Also, this example is just to keep it simple. It's not so interesting because you don't have a shortest path there. It's just a single link. But that's how you can split the traffic with segment routing. And we get back to this a little bit in a more interesting case in a second. Yes? Right, actually min-max load is usually the metric you want to have, but you can also look into fairness. But everything you do, you only can define link weights on the graph. You cannot directly choose the traffic there, and you need to do it for all of the traffic at the same time. So you cannot remove that and then change the link weights for the rest of the traffic or something like that. Was that your question? Right, so there are other approaches like software-defined networking where you can choose the path wherever you want. Okay, and you can also pre-install all the rules as you want, but this is not so scalable as this based on IP routing with these waypoints exactly. But there are like, you can even make tunnels. There's something like MPLS, you can make tunnels. But the scalable solution that Ines is very interested in now is this kind of segment routing, extension of the IP routing. But there are other ways indeed. Okay, maybe I should just stay at the same distance. Okay. Good. There are many more examples. So, for example, on the link layer, that is the Ethernet layer, people are studying like how to make Ethernet for automotives, how to do an Ethernet for data centers. That's, for example, something that is called Ultra Ethernet, a big consortium of industry trying to do Ethernet for data centers. In general, if you want to increase the bandwidth of the network, that's much more cost efficient than if you want to change the latency. If you want to change the latency, that's usually very hard and very expensive. Actually, the speed of light in the vacuum is much faster than if it's down here. So sometimes it's worth sending something to the satellite and then go low latency in the vacuum, basically in the space, and then go down again. People are trying to make fibers that are hollow, that is like a vacuum inside, just because you have a faster speed of light there. Okay, so for like certain applications, like stock market, it's very important sometimes to have low latency. Okay, but I want to go a different route now. So I want to show you two applications in more detail. And one is resilient routing. And you can react to failures in two ways. You can either react in the control plane or you can react in the data plane in the network. And in the control plane, this is like a distributed algorithm that recomputes shortest paths. In the data plane, this is a very local algorithm where you just react to the link failure locally. And this is what I want to focus on now. Because reacting in the control plane is slow because you have to reconvert, you have to compute shortest paths, etc. In the data plane, it's very fast. Okay, so how does it work here? So I can install rules on the router that tell me if this link is failed, then go to another port. Okay? And the algorithmic challenge here is that I need to pre-install these conditional failover rules so that even if there are link failures, I still stay connected in the routing. And okay, why do I care about it? If I reconstruct the link slowly or if I restore slowly, during this restoration time, I have a lot of packet loss. So I really want to make this quick. Okay, so how does a router decide how to handle an arriving packet? So I have a table where the packet gets matched, and then I need to decide what to do with it, and the action is usually where I send it out. And the only information I have locally is the following. I see the packet header, and I see from which import or from which port the packet arrived, and I see which links have failed, like the incident link failures. And now the question is like, how can I pre-install these local fast failover rules so that I can ensure reachability even under these failures? And how many of these failures can I tolerate? And for example, in this graph, if of course these links fail, there is nothing I can do because it's physically disconnected. And yeah, so if there is no topological connectivity, then of course it's not possible, but is it also sufficient to have topological connectivity also to get the routing layer connectivity? And as usual, we define the connectivity of the network N to be K if this is the minimal number of links I need to fail so that I disconnect the network, in which in this case it's 4. All right, so there are two very confusingly similar definitions of what we want to have here. One is called ideal resilience, is that if the graph is k-connected, I want to be able to tolerate k-1 link failures. Okay, so of course, after k-1 link failures, the graph is still connected. And there is another term called perfect resilience. That means that as long as the network is physically connected, I want to be connected on the routing layer too. Are the definitions clear? Oh, which one is stronger? Yes, okay, great. Okay, so let's say the link failures are undirected. And let's see whether we can achieve ideal resilience. So now we have this router and we need to locally decide where to send the packet. And what I can match is either the destination, the source, the incoming port. Maybe there is something probabilistic I can do. Maybe I can change the header. Maybe I can put some information in the header. So depending on the model here, so there's a lot of different models, okay? One of them is most interesting, and that's the one that we currently cannot solve. Maybe Antoine solved it in the meantime. Okay. So what if we have just per destination matching? What kind of level of resilience can we achieve? So the packet arrives. I don't know from which port it comes. I only know where it needs to go. And I cannot change it. I don't have any probabilistic methods. How resilient can this routing be? It's probably hard. I'll show you an example. So let's assume that we have this network here. And now we have pre-computed these failover paths. And let's say there is the S is down there. We want to send the packet to D. Now let's say this link there is failed. So now if S sends this packet on this direction, then it goes to this next node. Then it sees the failure. It sends it back. But since S cannot distinguish this packet from the one it sent, it will send it back. And we already have a loop. Okay, so is the example clear? Okay, so what if we have a table that we can match both the destination and the source and the incoming port? What kind of resilience can we get there? There's an idea how to do that. In a k-connected graph, can we tolerate k-1 link failures? Sebastian? That one is actually easy because we can compute k disjoint paths because the graph is k connected. So between any source destination, we have like k disjoint paths, like link disjoint paths. And what I can do is I can first just send out the packet on the first path. If it hits a failure, I will send it back to the source. And then I try the next path, I try the next path, and so on. So why is this possible with this in this model? Because I will just install these rules, go out first on this first path. Why can I send it back on this path? Because I have this import matching. I see when the packet comes from the other direction, I can forward in that direction. Why do I need to match the source? Because the source now needs to see, okay, the packet is coming back. I'm the source. I will send it the next path. If I'm not sure I'm the source, I don't know what to do with this packet. Okay, so here we can actually get k-1 resilience. So I will just locally see it, okay? So if I'm a router, I will see, okay, these incident links, they have failed. Right, so there are two options there. There is like a hardware sensing that the router senses the link is not there, or it has some hello packets going back and forth with its neighbors, and then it sees it also. It's not perfect, and this is already not standardized, so different vendors have different approaches, but that's then in the end the signal that you get in the table. Okay, so what about this scenario? We can match the destination, we can match the incoming port. This is like the most practical setting, because the more things you match, the bigger the table also becomes, of course. So if you do this, we don't know how to solve this problem for many years. Okay, this is an open problem. And we know it for some graphs. Okay, so here we just removed the source. The source was critical in the solution we had before. For some special graphs, I can show you solutions. For example, if you have a two-dimensional torus, which is a typical network, for example, for high performance computing. So here what you can do, it's a four-connected graph. So it allows us to decompose this graph into two edge-disjoint Hamilton cycles. Sorry, I didn't draw the wraparounds here, but this is the first Hamilton cycle. And then there is edge-disjoint second Hamilton cycle that is like this. And if I have that, what can I do? I can go in both directions because I have the import matching. So now what I do is I go along. The good thing about Hamilton cycle is if I go in any direction, I will always reach any node, right? So I will just go in one direction until I hit the destination. In case I see a failure before, I will go in the other direction of this Hamilton cycle and will reach it the other way around. If I don't manage that, I go on the next Hamilton cycle, the blue one, let's say, and then do the same there. And only if I see 4 failures, I will actually not be able to reach the destination. So as long as I have this decomposition into edge-disjoint Hamilton cycles, I can find a solution. Okay, so there is this result. If I have a k-connected graph, and it has k arc-disjoint Hamilton cycles, I can do k-1 resilient routing. What can I do if I don't have, not many graphs have these Hamilton cycle decompositions, unfortunately. If I don't have it, I can try to do something similar with what is called arborescences. So these are like directed trees. And we want them to be arc-disjoint and spanning and rooted at the destination. And then there is a classic result by Edmonds that if I have a k-connected graph, I can always find these arborescences. Okay, I will show you this in a second. So the idea is I go along the first arborescence until I reach the root. If I don't find it, I go to the next arborescence because there was a link failure. And then I try one after the other until I reach the destination, or if I fail. Okay, so I will show you this in detail. There is this classic result by Edmonds. If I have this k-connected graph, I can find, in this case, it's 4 connected, 4 spanning arborescences. So I have this brown one, it's spanning, right? Then I have the red one, it's also spanning and disjoint. And now it needs to be edged, like arc disjoint, so I have edges in both directions, but I don't have like the same direction on the same edge. So it needs to be disjoint. And also this yellow one, it's spanning, it's arborescence, and it's also disjoint. Is it clear? Okay, so there is this classic result, this always exists. And now what I can try to do, all of these arborescences are going to the destination. So I can just try to send the packet along the first. And then maybe I hit the link failure. Now I cannot go on these arborescence anymore. So I will choose another one. And now the question is, which one will I choose? And I can just make an order on these arborescences. Let me just define a global order. So this is called circular arborescence routing. I compute an order on the arborescences, and then I just go to the next one whenever I hit the failure on one of them. So let's see here. Maybe first in my order is red, so I go along the red. Now I hit the failure, so I need to go to the next arborescence in my order, which is the blue one. I go there, but unfortunately now I hit another failure. And I cannot go along the blue one, so I need to go along the next, which is the green. And now, unfortunately, I hit another failure. So now the last one I have is the yellow, and unfortunately, I get stuck. Okay, so now we see that in this case, 2 link failures, even though I have 4 arborescences, actually lead to a loop. But at least I can show that I can tolerate k divided by 2 minus 1 failures with this approach. Okay, why can I tolerate k minus k divided by 2 failures at least? because like one link failure can kill at most 2 arborescences, because these are undirected failures. So that's already quite good. However, that's all we know. Okay, so there is a conjecture again that we can do this up to k resilient, but we don't even know like k divided by 2 plus 1 or something like that. So in general, this is unclear. Probably it's quite a graph theoretical problem if you want to solve this. I think maybe a lot of people try to solve this from an algorithmic point of view. Maybe not so many people, okay, but some very strong people. Maybe it's better to think about impossibility, and maybe you can use some of these techniques we have in the community to solve this problem, so it's impossible, because it's kind of a local problem. What does it make it non-local, I think, is that we have this import that we can match, and you can kind of signal a lot of information by the way the packet arrives at the router, potentially. Because if you have a faraway failure, the packet comes in a weird port to me, maybe this tells me something about the rest of the network, I don't know. You cannot easily make this indistinguishability, but I don't know, I have no idea whether this conjecture is true or not. And then there is this perfect resilience that is even stronger, as we discussed. And actually there you can show this is not possible in general. So there are some indistinguishability proofs you can show even in this graph, this is not possible to solve. Nevertheless, there are a lot of open questions like which graphs can I solve, in which model does it work, etc. Of course. Whether this is the minimal graph. The problem is actually related to a lot of things, a lot of problems we looked into in the community. One is like geometric routing, because on a planar graph you can still do some tricks like maze search, left-hand rules, and things like that. There is something, maybe some of you know this, local algorithms without communication, where basically they use a lot of balanced incomplete block design approaches to solve these problems, which can also be used if you like consider load in the network. So if you worry about congestion, the problem becomes related to this problem. Then there is these connectivity problems. I think this Romer-Reingold's result. Connectivity in log space. It could be potentially applied here too, but it's a very complicated approach in this context. Okay? And only if you rewrite header bits. Okay. So a lot of open problems. We also can look into synthesis, like how to generate tables automatically that are resilient. For example, using binary decision diagrams, special graphs, how to do segment routing how to do failover routing in segment routing. So there you have these waypoints. I just want to give you one more perspective on that. So remember, in segment routing, I can put waypoints in the middle. And this is actually about to be standardized now by the IETF. So it's a very good moment to contribute something here, because I will tell you how they do it at the moment there. For a single link failure. Okay, so let's say you're on a route from source to V, and then you hit a link failure. You want to push locally a waypoint so that you can still reach T, and you only go shortest paths. Okay, so that's the setup here. And what they propose is like push a waypoint that is making sure that you have a shortest path to this waypoint that will not use this failed link again. You don't want to see this failed link again. And then from the waypoint to destination, also you don't want to see this link again. So how can this be done? So they have all the nodes that are reachable on shortest paths without going through this failed edge E again. They call this the P space. And all the nodes that can reach T on shortest paths from W, they call this the Q space. And you can just push any node in this intersection. Okay, and this ensures you can go shortest path to that guy and then to the destination. If the intersection is empty, there's also a trick. If this is empty, there's like they're adjacent to each other. And then you can do a trick there. Okay, so that works for one failure. it's not clear how to do this for 2 failures. So IETF, they're very happy if they can solve this now with 1 failure, but maybe you can show even this algorithm, it can be done for 2 failures. Okay, any questions regarding this? Yes? Right, so you also need to pre-compute that. This again in the data plane, you kind of need to predefine that. And then you see my local failure, and then you know what to take out of my pre-installed table, which waypoint to put. But you need to pre-compute this globally. And then you react locally, basically. Right, exactly. I'm not saying this is efficient, right? And that's why they only do it for 1 failure, because if multiple ones, you may have to do this more combinatorially. But that's how it needs to be done at the moment, yes. Yes, they don't have huge amount of memory, and you really want to save on this. And that's why also we have this without the source case that we are so interested in, because we don't want to store all the sources in the model before. But in principle, if you really want to have a reliable network, that's how you do it. And some of these networks are actually not super large, so these are like maybe 500 nodes or so. But probably there are better solutions. All right, other questions on this? Okay, now I want to show you one more opportunity. And now this goes to the physical layer. And this is just 5 minutes, just to give you an idea. It's about data centers and how they're interconnected. Okay, and data centers, they have these racks at the bottom, and then they have a topological interconnect. It's like a rack-to-rack network. And there are different ways how to interconnect the data center, but the most common one is to have like a fat tree or closed topology between them. There are expander graphs, there are hypercubic graphs, but all of them are fixed and oblivious to the actual traffic. And what we always say is like building a highway that ignores the traffic is like wasting resources, because maybe you have a traffic jam on the right and a lot of capacity on the left. It can be frustrating. Why not use this capacity as well? And maybe in the evening the other way around. Maybe you know this Golden Gate zipper. This is this bus on the Golden Gate Bridge or robot that can change the number of lanes. Like in the morning it puts more lanes in that direction, in the evening it puts more lanes in the other direction. So you can do this more flexibly on the roads. And what people are considering is like, can we do the same also in the network itself? And so what's the new area here is that we have a flexible interconnect. So you can think of it like you have like mirrors at the ceiling and you have lasers at the rack, but there are other technologies, I will show you in a second, that if you have a demand from rack 1 to 2, from rack 3 to 4, 5 to 6, 7 to 8, you can just interconnect the racks so that you have a direct link between them. Okay, you just do the interconnect so that it matches the demand. Now, if you have a demand that look like this, 1 communicates to 5, 2 to 6, 3 to 7, and 4 to 8, then again, you change interconnect so that it directly matches the demand. So these are called reconfigurable data center networks, and or self-adjusting networks. And the motivation for doing this is that a lot of the workloads in data centers have a lot of structure. Okay, so this is like, we call this a complexity map, where you can see on the upper right this traffic that is completely uniform, that has no temporal and no spatial structure. And then you can see, for example, machine learning workloads, some high performance workloads like CNS multigrid, neural networks. There is like data from Facebook, clusters like database, web frontend, Hadoop. And you can see they all have different structures, and they all have like spatial structure and temporal structure. And the question is, can we not exploit that in the data center design and build the network specifically for these traces? Actually, it doesn't have to be wireless. This is the technology. Like Google is one of the first deployer of this technology. They use optical circuit switches that are based on also mirrors. So if a signal comes in there, then it gets reflected on these mirrors like that. But within microseconds, you can change the angle of the mirror. And now if you change that, the light propagation goes like this. And you have changed the interconnect this way, the optical interconnect. You don't need to change, the fibers are anyway, or the cables in data centers are anyway fibers. If you had the classic electrical switches, you would have to change the photon to an electron and then back to a photon. Here, this is also more energy efficient. You can directly keep it a photon. This works like in microseconds if you change the angle. There is technology by Microsoft that is based on tunable lasers. So they published this in like Nature, kind of, it's like really physics contributions. And then the router is just a passive glass. And when a red laser comes into it, it goes out there. If like a green laser comes into it, it goes out there. And you can change this in nanoseconds. Okay, so we have a lot of structure. We have a lot of flexibility in the technology. So the idea here is really, can we bring it together and optimize the technology or the hardware, interconnected physical topology towards this demand to improve performance, efficiency, whatever goal you want to have there. And this is my last slide. So why this is exciting? There is a lot of self-adjusting systems already around, and a lot of people are building and interested in self-adjusting systems. For example, in data structures. So if you optimize a binary search tree in the university, you try to make the depth logarithmic. So if it's balanced, it's logarithmic, mostly you're happy. There are biased binary search trees that we call demand-aware binary search trees, that if you have a skew in your distribution of access, so if some of the keys are much more frequent than others, then the average access time is actually based on the entropy of the frequency distribution of the keys. So you can be better than log n potentially if you have a skew in the distribution. And then there are self-adjusting trees, like splay trees, that can even change according to the current pattern. So if we speak English now and later we speak Spanish, then maybe some letters get more popular than others. You can change the distribution and the tree accordingly. And the same actually holds in coding and information theory. So if you do worst case coding, you need log n bits to encode any symbol in this n size alphabet. If you do Huffman coding, it's proportional to the entropy. And maybe if you do it dynamically, you can be like entropy rate. This would be ideal to have like entropy rate over time. And the idea is, can we do the same in the network? So if you optimize the route length, the average length of the bits in the network, then maybe we can also go from today, where it's static, so if you have a constant degree, you have at least logarithmic diameter, to something more related to entropy, and maybe even entropy rate. And that's actually not just analogy, but some of these techniques and even bounds come also in the network context again. So I think that's quite cool. But there are a lot of problems here. Okay, so for some demands, like sparse demand matrices, we know this already. For general cases, there is a lot of things we don't know in this area. So it's really just new kind of area. We recently made an interview with Amin Wadat, who is one of the pioneers of these data centers that become reconfigurable and also got deployed in Google. And he said, okay, if you currently in the Google data center, they change the topology something like once per hour, where like Microsoft is already publishing papers that can do it in nanoseconds or so. We asked him, okay, is it good enough? And he said, no, we would like to make it much faster. But what we lack is like a scalable control plane. Like a distributed control plane is not everything need to be collected and computed centrally, but can we make it more distributed? How much time do I have? Okay, so I can show you just one idea what we want to do distributed here, because again, like Microsoft, they say we can change the interconnect in nanoseconds. But to some extent, it's a bit ridiculous, because if you need to optimize and compute the optimal solution and collect information about the workload, this anyway takes long, right? So this is great that you can do this, but the bottleneck is currently not there, at least for this kind of applications. And the good thing about machine learning workloads, they're quite predictable. So once you've seen or you learned a couple of images, in the next hour, you already know roughly the communication will be similar. So you don't have to collect the data online and adapt it in a real-time manner. Okay, so how can we make an optimal network for a given demand matrix? Let's say we have this distribution. It's a doubly stochastic matrix where now we have the overall communication is 1. And the higher the number, the more communication should be there. So if you want to build an optimal data center network of constant degree for a given node, what can we do there? If you have a given source and we just want to look at the first row and want to build the optimal, let's say, binary tree. Let's say you want to build the optimal binary tree for, or constant degree tree for the source 1. Then what you can do is you build, for example, a Huffman tree or a biased binary search tree that is optimal for this row. And you can do this for every source. You just build an optimal tree. So now you could say, okay, why don't we take the union of these optimal trees for all the sources, and then we have an optimal network that is demand aware. The problem is if you do that, the degree goes up, right? So you have the union of the degrees. So it will not be constant degree anymore. So we need to do some post-processing. So we need to find a technique to reduce the degree again. I will not tell you how this works. If you're interested, I can tell you in the break. But what I want to tell you is that so this is a static solution, an algorithm that we know it works if the demand matrix is sparse. This gives you a constant approximation of the optimal demand-aware network. Now, if you want to make this more dynamic, then maybe we can replace the Huffman tree with a dynamic Huffman tree or a dynamic binary search tree like the splay tree, and we get automatically a self-adjusting network. But what happens if you want to make it distributed? So now the question is, can we also replace these trees with like a distributed adaptation mechanism and then also have like a network that even adapts in a distributed like way and become a demand-aware network in a distributed way? This is something that we don't know how to do this, okay? But that would be very nice. Of course, I mean, Vadad, he didn't mean this specific problem, he meant much more general things. But that would be a nice first step. All right. So that's, I think, what I wanted to tell you. So wired networks, I think they are maybe a bit different from what you think. And they're also evolving quite fast right now. Much of the control is distributed in congestion control, which really doesn't have good underpinnings at the moment. Local fast rerouting, self-adjusting networks. I think it's a good moment not only to write papers about this at the moment, but currently there's a lot going on, like in the IETF about this failover, in the Ultra Ethernet Consortium about these new data center networks. So I think it's a good moment to look into wired network that I think are very exciting at the moment. Okay, thanks.
Maybe you can shout.
Very early in the talk, you dismissed the SDN-based approach.
Right.
Is there evidence for that?
I'm currently, first of all, SDN, I think it has a lot, it's also new technology if you haven't heard about it. I think there's a lot of great concepts there. Currently, it seems to me that industry is a bit more going away from SDN. And in part, right, this is a good question. I mean, first of all, I'm not sure everyone is so interested in this open aspect of SDN anymore. Everyone tries to do their own kind of thing and not open flow, which in addition to SDN being a nice, like centralized view, it also has this open aspect, at least in the original conception. Now I think this standardization so is not going so much forward. And at least industry conferences are all about segment routing. So SDN, I think, is...
Appears much simpler.
Right. I mean, SDN, it's simpler in an abstract sense, right? But if you have, like in SDN, you have this controller that controls the network, but in the end, this controller also should not be like a single server or something. So you again need like a distributed system there. So I agree, it's simpler. It's more powerful, but I think it's a bit too far away from what operators really know and do on a daily basis. And I think that's also one of the, so they're also not programmers, right? So you need to be more like, you have to have a different perspective on the network if you go for SDN. So I don't know the final answer, but I just see the trend. Maybe it comes back in 10 years, right? But
it's a scary trap because you
right.
we end up implementing boxes.
Right. I mean, it's scary. I'm not sure it's scary because industry is very conservative in this area. And I think it's actually good that they are like that because, of course, if you jump somewhere and then you have to do something completely different, that's also a stretch. Inside data centers may be slightly different. Also, virtual switches in data centers, they are becoming like SDN, but not in the hardware space. Right? So, unfortunately, also programmable data planes, they're slightly trend away at the moment. So I still believe in it too, so I'm completely with you, but maybe it was just too early.
Awesome.
Right. So I meant it in specifically in this failover area, where currently I see two problem areas there. One is verification, one is synthesis. Okay. So maybe you also want to look at the current failover rules you have in your router tables and ask the question, is it already too resilient or something like that? So that will be like the verification question. I don't know, to be honest, what is the complexity of asking this verification question. Maybe it's p-space somewhere. That's one thing. But maybe we have good algorithms to yeah. Anyway, the second one is synthesis, where I get the network and I say, okay, I want this to be free resilient. Can you generate me rules that give me free resilience? That's what I meant by synthesis, like feeling, for example, using integer linear programming or binary decision diagrams or any of these formal methods there. Once we thought about it a bit, and I also was not sure whether synthesis is actually simpler than verification. Often you think maybe if you generate it, I mean, there are many examples where synthesis can be faster than verification, right? Because if you have a simple example, it's easier to fill the correct solution in rather than thinking what's this complex solution that someone put in there. Also, what I find really interesting, I haven't talked about, is the way it's currently defined. I can have like rules on the combinatorics of the failed links. So if I have multiple links failed, I can have a rule that maps the set of failed links to kind of a next hop. We are more interested in something that we call skipping. It's like I have just a fixed order on the ports, and I will just write the first one that is available, which requires much less rules in the router. Currently, we don't have a single example where the skipping is not as strong as the combinatorial in neither of these models, so that's also quite nice. Maybe that helps for synthesis and verification too. I don't know. But then in general, like updating networks, so generating topologies, everything can also be done with, I guess, formal methods somehow in a good way, like integer linear programming. Maybe something like games approaches would be nice to look into, like there are Stackelberg games, PetriNet games, maybe some of these problems, like a distributed control plane that Google was asking for. Maybe that's something we could model this way. I'm not an expert there, but I think, yeah. And I'm happy to give you pointers there. I know some people look into that.
Yep. Maybe one last one. Yep. Yannick, he was first.
Right. Actually, I think there's a very big opportunity to go more simpler algorithms and greedy routing and so on that you were referring. The first word I didn't hear 3 algorithms, or what was it? The word 3? Or right, greedy. So in data centers, okay. So in data center networks, the nice thing about data center networks is, first of all, they're very emerging area, a lot of job opportunities there and a lot of innovations. And second, you can do more what you want there because it's under your control, right? You don't have to vary the interface to other ISPs and so on. It's also inside the house typically, so you can put cables more easy, make it more symmetric. So in data centers, you can come with more like simple algorithms, I think easier. In ISP networks, it's very hard, right? You've seen how long it takes to deploy like IPv6. You can imagine if you come, I want to do greedy routing, they kick you out of the IT meeting immediately. But when you go into these dynamic networks, in these self-adjusting networks, there I think it's even very good to look into very greedy and local algorithms. I should have maybe emphasized that more. Because if the graph changes, it more become like what we know from like wireless mobile networks and so on, that you need to take greedy decisions ideally, so you don't need to necessarily to know what's happening in the other parts of the network. So there I think there are great opportunities, both for like greedy topology, reconfigurations, and also routing.
Last question, Yoram.
So I'm wondering, the reconfigurations are usually generated by RF bits. How much use is there for clocks and timing in that? Because I think there could be efficiency if you redesign things to happen.
Right, if you have like fully synchronized clocks, that will be very helpful. I mean, for example, to do more consistent reconfigurations in the network. Right now, I totally agree. And actually, synchronization, I tell it to Christoph Lenzen, in the data center, I think is a very good use case.
How much use is there of timing currently in these approaches?
Right, so it depends a bit on technology, but for example, for this Microsoft technology with the tunable lasers, and also, I guess, for the digital mirrors, you have quite a high requirement. They have synchronization protocols there they use, but they use like standards in the literature. They don't develop. There's been, last year in NSTI, there's been a very interesting time synchronization paper for, I think, data center networks. I looked at it, I don't remember details, I can send it to you. I think there is a demand for this. Currently deployed ones, I mean, these are anywhere just prototypes, at least in the Microsoft case. In Google, they only change it once an hour, right? They don't need super synchronized. But I think this is coming more. And inside the data center, I'm sure you can do much easier protocols again because you have much more control. We can talk in the break more. I can find you something. I don't know what's exactly there.
All right, so let's thank Stefan again. And now we go straight into a half session on concurrent data structures. Our first speaker is Eric, I believe. So Eric Rupert from York University, he's going to talk about lock-free augmented trees. This work is a co-recipient of the Best Paper Award for its technical elegance and practical potential.
So I'm not allowed to share the screen yet, so somebody else is sharing. Try to remember to stop sharing when I'm finished. It still doesn't happen. Okay, now it's working. There we go. Okay, so this is joint work with Eula Faturo that we did during a wonderful visit to Greece earlier this year. So the main result that I want to talk to you about today is a way to augment lock-free search trees in order to support more operations on them. And these are sort of some properties that this construction has. It's quite simple to implement using single word compare and swap. It's very general, that it can handle any kind of augmentation you like. It's quite efficient, so it adds very minimal overhead to the insert and delete operations on the search tree. And it also is able to handle the queries very efficiently, just as efficiently as you could in a sequential system where you just have one process operating on the data structure at a time. The new construction is weight-free, and it also supports very simple snapshots on the data structure that allows you to do complex queries on those snapshots. Okay. So here's a search tree. For the sake of this presentation, I'm going to deal with leaf-oriented search trees. So the actual keys in the set that I'm representing are just in the leaves. All the internal nodes only contain keys to direct you towards the appropriate leaf. That just makes things more simple in the concurrent setting. Okay, so we might like to augment this search tree with extra information in every node. So in this example that I'm going to use throughout the talk, we add the size of the subtrees to each node. So each red number represents the number of leaves in the subtree rooted at that node. And that allows you to do a bunch of different new operations on the search tree. For example, I can get the size of the tree very easily just by looking at the new field of the root. I can also do queries like this, where I want to select the fourth smallest element in the set that I'm representing. So for example, here I would look in the left subtree of the root and see there's only 3 elements there. And if I want the fourth smallest element, then I should go into the right subtree. And then I continue down in the same sort of way. It allows me to do those queries in time proportional to the height of the tree. I can also do queries like rank queries, where I want to know what is the number of elements that is less than or equal to the key L. For that, I just follow the search path down to the key L and add up the sizes of all the subtrees that hang off the left side of that path. I can do other kinds of augmentations too. So for example, if each of the keys in the set has some sort of weight associated with it, I might want to store the sum of the subtree's weights in all the nodes. That allows me to do things like finding what is the total weight of all the elements that's less than L. Again, I can just walk down the search path towards L and look at the subtrees hanging off the left side of that path, add up the total weights of those subtrees, and I get my answer. So again, that allows me to do queries in time proportional to the height of the tree. And there's lots and lots of other ways that you can augment a BST. So for example, if I'm storing a database of employees where the key is the salary of the employee, I might want to know how many women make more than 100,000 euros as their salary. So for that, I could augment the tree by looking at the number of women in each subtree. That would allow me to answer these queries very quickly as well, even as I'm doing insertions and deletions into the tree. And the augmentation doesn't have to be a single field. I can add a bunch of pieces of information if I want to do more complex queries. This is just one example of that. I'm not going to go into the details. But the key property of all these augmentations that I'm talking about is that if I add new fields to a node, I should be able to compute the values of those new fields just using the information in that node and its children. So I can do something very local to compute these new fields. Okay, so this is probably familiar to a lot of you, this idea of augmenting a binary search tree. It actually is a complete chapter of the Bible on algorithms because it's such an important technique for BSTs. And it's also used as a building block for lots of other sequential data structures, like interval trees, tango trees, measure trees. There's a whole bunch. If you look in the handbook of data structures, you'll find lots of these things. So we're hoping that now by developing a lock-free version of augmented BSTs, that maybe we have ways of building some of these other more complex data structures that can be used concurrently too. And these data structures have lots of applications in computational geometry, databases, graph algorithms, and other places. Okay, so like I said, what we'd like to do in this talk is figure out a way to do this in a lock-free manner so that concurrent operations on the BST can take advantage of the augmentation as well. And the example that I'm going to use throughout this talk is a lock-free binary search tree. So the way that we do this, it can handle any kind of augmentation as long as it has that locality property that you can compute the new fields of any node locally. It adds a little bit of complexity to the insertions and deletions, but not very much. It's proportional to the height of the tree, which you're going to have to do anyway. So it's really just a constant factor, additional work that you have to do for insertions and deletions. It also supports a very simple way of doing snapshots of the entire tree, which then allows you to do weight-free queries on that snapshot. And those weight-free queries, not only are they as fast as sequential code, they actually are sequential code because you get a snapshot and you can just run the sequential code for the query that you want to do. So the example that I'm going to show you here is based on the BST from PODC 2014. In the paper, there's also another example of a static try that also uses this augmentation technique. Okay. So if I want to update a binary search tree, let's say I want to do an insertion of the key J, I can do it this way just by swinging a single pointer. I search for the key J and I replace the leaf that I get to, which is L in this case, by this new tree containing the old leaf that was there and the new leaf containing the key that I want to insert. Now, if I want to do that with an augmented tree, like this, where every node stores the size of its subtree, I have to add that information to the new nodes that I'm inserting, but I also have to walk up this path to the root in order to increment each size field along the way. And since our goal is to create a lock-free augmented tree, this presents a couple of challenges. One is that the update really does have to change a lot of nodes. It has to change all the nodes along the path from the leaf where the update happened all the way up to the root. And all of those changes have to appear atomic. And we know that when we're designing concurrent data structures, to make a lot of changes appear atomic can be quite tricky. One of the other challenges of doing this is that as changes are happening in the tree, there are also queries that are walking through the tree, and we want to make sure that the updates don't interfere with those. And another challenge that arises when you think about doing this concurrently is that really every update has to change the root, because the size of the root always changes whenever I do an insert or delete. And so that could cause a hotspot of contention. And we'll see that our technique actually avoids having a lot of contention at the root, which is nice. Okay, so the key idea of the construction is that instead of storing these new fields in the nodes themselves, I'm actually going to store them in a separate object. And that allows me to have different versions of the field. So when I want to update the field, for example, when I do an insertion of J, instead of changing the value stored in that field, I'm going to create a new version of the field and just swing a pointer to it. And the advantage of that is that if I'm doing a query at the same time, it can still go and access the old versions of that field. And by adding some pointers between different versions, that allows those queries to get a consistent view of all the versions of that augmented field. So here, what I've done is I've added pointers that says to compute this version of the field at the root, it drew information from this version of the node B and this version of node H. So I have pointers to the versions that I got the information from in order to compute the value of this field. Similarly, after the insertion of J, this value 6 was computed by adding 3 from this version and 3 from this version to get the number of leaves in the entire tree. So the advantage of having these pointers is that simply by reading the current version of the root, I get a consistent picture of the fields of all the nodes in the tree. So for example, if I read, before the insertion, if I read the 5 as the size of the entire tree, and I follow pointers from it, I get all of the information in the entire tree about the sizes of all the subtrees at that time. Whereas if I read the 6 after I've done the insertion and follow pointers from there, I get the entire tree as well. And now it includes the new nodes that were obtained or that were added when I did the insertion. So these are the trees that now support any sort of sequential query operation that I might want to do on the tree. And often when you have multiple versions of things, you have to worry about garbage collection. Here, it actually takes care of itself almost, because the old versions just become unreachable when they're no longer needed, and so then they can be garbage collected, for example, by Java's garbage collector. we don't have to do any fancy garbage collection ourselves. Okay, so I want to just talk briefly about how this information gets propagated through the tree as I do an insertion or deletion. It's quite a simple algorithm. What I do is I start at the leaf where I did my insertion or deletion. I walk along the path up towards the root, and at each node along that path, at each node x, I do the following things at most twice. So at this node x, I create a new version that I'm going to fill in. I read the left child of x and look at its current version and set a pointer to that version. I do the same thing for the right child. And then I use the information from those two children in order to compute the value of this augmented field for node x. And then I swing a pointer to this new version. Okay, so I'm going to do this at every node along the path from the place that I do my updates to the root. So one of the nice properties of this is that if I look at any one of these versions, I never change the content of it after I've attached it to the tree. And that's what gives us this property that we can take snapshots of the entire version tree just by reading the root version. Moreover, the propagation turns out to be weight-free because I'm just doing a constant amount of work at each node along the path up to the root. Okay. So here's an example of propagating the insert that I showed you before. So we insert this new node j, and then I walk along the path from the location of the insertion up to the root. So I refresh the version of node h by doing that little sort of 5-step computation that I showed you on the previous slide. And then I do the same thing at f, and now I'm finished. Once I've swung the pointer at f to point to this new version that includes all the information about the insert, I'm done. Okay, so I mentioned that when we're going to each node, we have to use a CAS to update, a compare and swap, to update the version that's stored with that node. Well, what if that CAS fails? Okay, I'll try again. What if it fails again? Then I can stop. So I only have to do it twice, because if I fail twice, then we can show that somebody else's refresh on that node has already propagated my change to the node, and so there's no need to do it again. So this is sort of a cooperative technique for propagating these changes up to the root of the tree. And the nice thing about this is that every time I do a single change, a single CAS that succeeds, I may actually be propagating information from a lot of different updates, one step up the tree. And so even though everybody does have to change the root, it's not true that everybody has to do a successful CAS on the root, because we have this cooperative approach that says one CAS that succeeds may actually shift a lot of information into the root. Okay, so an overview of the augmentation of a lock-free search tree is the following. If I have a lock-free search tree that I'm starting with, what I can do is I can just run the original algorithm to do an insertion or deletion. And then once the insertion or deletion is completed, all I have to do is refresh every one of the ancestors of that node at most twice in order to propagate all the information up to the root of the tree. And so it's going to add order height steps to the update operations. That's not too bad because they're going to take that much work anyways to get down to the right location to do the updates. Like I said before, query operations really just have to read the current version of the root and then run a standard sequential algorithm to obtain the result of the query, because I've basically got a snapshot of the entire tree when I do that. And so the step complexity is going to be the same as if you were just in a single process system for those queries. Okay, so it's a fairly easy to implement algorithm, which is nice. And often we know that sometimes simple algorithms are kind of tricky to prove correct. So some of the challenges that we faced when we were trying to prove this correct is that the updates are happening on the original tree. They're not looking at the versions of the augmented fields. And yet the queries are happening only on those versions. And somehow there could be a mismatch between those two trees. For example, those two trees could have completely different shapes because we're constructing the tree of versions piece by piece. And at the same time, the original tree is undergoing changes. It's having nodes inserted and deleted. And so the two trees may actually end up looking quite different. And yet they all work together nicely. So that was little bit tricky to prove. Here's sort of a very high-level idea. You have to read the paper in order to see all the details. The idea was that we defined, for every update operation that we wanted to linearize, we defined an arrival point of that update at each node along the path up to the root of the tree. Basically, that was meant to represent when the information from that update reaches that node for the first time. That's the arrival point at that node. And then we proved an invariant that if we look at the current version of a node, it reflects all of the operations that have arrived at that node so far. So the tree that you would get if you did all of those operations in the order of their arrival points is exactly the tree that's rooted at the current version of that node. So once we have that invariant, then it's very easy to define the linearization point as the arrival point at the root, and that makes sure that all of the queries are going to give the right results that is consistent with the linearization. And then we also have to show that our propagation mechanism actually works in ensuring that every operation does get propagated all the way to the root and arrive there. Okay. Maybe I'll just mention this very quickly. We actually have a technique in the paper as well for improving the query time. I said that the query time, for sort of standard queries using an augmented search tree is proportional to the height of the tree. In general, the height could get bad, potentially, if it's an unbalanced binary search tree. But we actually have a way of making the queries run in logarithmic time, even if the tree itself is not balanced. And that is by simply plugging in a different augmentation of the tree. The augmentation doesn't have to be just a simple number. It could be a data structure itself. And so if we use red-black trees as the augmentation, we can actually achieve logarithmic time for queries. I don't think I have time to go into the details of that. I'll mention some related work. There's been very little work on augmented search trees, even though we've had lock-free search trees for about 15 years now. The only work that I know of on augmented search trees, there was one paper earlier this year which augments a search tree with a size field, but it does require that each operation has to join a queue at every node along the path down to the place where it wants to do its operation, and so that actually makes it quite expensive in terms of the number of steps that it might have to do in the worst case. There's another lock-based tree augmentation, which you will hear about in 20 minutes from now. There's quite a lot of work on taking snapshots of data structures like this, but a lot of them do use multi-versioning and are fairly complicated. It slows down the queries a bit to have those multiple versions that you have to look through, and multi-versioning generally involves quite complex garbage collection, which we don't have to worry about so much in our augmentation. The technique of doing sort of a double refresh has been used in a lot of other papers in the past. It goes back to a paper by Effect-Dauber and Tuitu in 1995. So it's a very nice technique to use for lock-free data structures. Okay, so I'll conclude with that. I just want to recap that we gave a scheme for augmenting concurrent trees. It's easy to implement. It works for any augmentation, so it's quite general. It adds very little overhead for updates, and it preserves lock-free or wait-free properties of those updates because the extra steps that you do, those steps are wait-free. And it gives you wait-free fast queries and supports simple snapshots.
Yeah, Max.
And there are two concurrent swaps to the object. So how do you keep the factual fee and the augmented fee consistent with each other?
So the key really is linearizing things according to when the operation reaches the root of the red tree shown here. And like I said, there's quite a bit to prove in order to show that that's okay to do. To show that doing the operations, the insertions and deletions in the black part of the tree here still is consistent with all the query results. I don't know if that answers your question, but I can talk more offline.
Yeah, there's.
I wonder about the memory management. If you have a garbage collector, then you're safe like this.
Yeah.
If you don't, then all the safe memory information I don't know data structure. Here you don't know when you're disconnecting.
I mean, when I do this compare and swap, I know that when I've succeeded, that the old version is no longer connected to the data structure. It may be that some queries still need access to it. So we have to check whether queries still need access.
Spreads are going to go down. I mean, you know the first one. What about others?
I mean, it's the same thing here, that when I do this compare and swap, this old version is disconnected from the data structure. So nobody can get a new access to it unless, unless there was a query that was still needing it.
Maybe another more general question is like, are there plans to implement this and see how fast it is in practice?
Yeah, so there's a student that's working on that. The preliminary results look good.
Oh, very good. All right, so maybe let's thank Eric again.
Thanks.
Our next speaker in this session on concurrency is Philip Wolfel. Who's going to talk about snapshots.
Right. So this is joint work with Benjamin Bashari and David Chan. And the snapshot object is a very classical concurrent data structure. We manage an array, and we can usually, in the classical specification, usually you can write to the array, and then you can perform a scan operation, which computes the snapshot of the array and returns it. There's a lot of work has been done on this, and some snapshots are single writer, where only one process can write to an array position. Some algorithms are multi-writer, and a lot of the classical work just assumes that the algorithms can only use atomic read and write operations. So atomic registers is all we have. There are many algorithms on that, way too many to mention, but one of the best results just using registers has step complexity, which is polylogarithmic in the size of the array. There's a randomized version for it, and then there's a deterministic version where you get this as an amortized step complexity. The problem with these types of results is they all assume that you have huge registers available. You can store the entire snapshot in a single register, which is not a realistic assumption. Then there's some other work which employs standard primitives like compare and swap or fetch and increment, fetch and store in order to get those snapshots. Those primitives are typically available on most common hardware, so I guess there's no reason not to use them. And the best result is by Jayanti in 2005, which implements a multi-writer snapshot, and the scan has linear step complexity, and then a write operation takes only a constant number of steps, so this is optimal. And for the rest of this talk, I will just assume that all common read, modify, write operations are available that you typically have in a system. Now, another approach is, or another problem is to have a read, modify, writable snapshot. So obviously, if we have those operations in the system, we may also want to use them to update our array. And a read, modify, writable snapshot is one where you can apply any of the typical read, modify, write operations on the array entries. So here in this example, the process performed a fetch and store in an array entry, and then the scan can still obtain the correct value. There's really only one algorithm that does that. This is the F-array by Jayanti, and it has linear step complexity for both scan and update. And so essentially also we can't really get around this linear step complexity if you want to create a snapshot of an entire array. I mean, that's kind of inherent. The only way to get around this inherent step complexity is by assuming huge registers, which is not a realistic assumption. But so maybe sometimes when we scan, we don't really need to know the entire array. And so Hagit and Rashid and Eric here, they had an algorithm a while ago where you can just take a partial snapshot. Essentially, you specify a subset of the array, and then the scan just returns the scan of those array entries for which you have specified. And this one has a step complexity that's quadratic in the size of the array for scans, and for writes, it's a little bit worse. So essentially, it's a product of interval contention and the maximum possible snapshot size that you may ever obtain, and then squared. But to improve this, we can think of something like an adaptive partial snapshot, where maybe we don't really need to know, also I guess maybe we usually don't know what parts of the array we want to scan. So if you think, for example, you have an array that is sorted and you want to do a binary search on that array, then you don't know in advance what array entries are you actually going to query. And so 3 years ago, Benjamin and I, we devised this adaptive partial snapshot where you have something that I call now a click operation. That terminology was actually coined by Giantis this year. We just stole it from them. We still called it scan at the time. But think of a click operation where you just click the camera, but you don't develop the film. So you don't really know what the snapshot is. It doesn't return anything. But somehow, I guess the pointer isn't working, but somehow you have clicked the camera. And then processes can still write to the array. And then later on, you can call an observe operation where you just specify an array index, and it returns the value that this array had at this index at the point in time of your click operation. So if you do sufficiently many observe operations, obviously you can still do a complete scan of the array. But now you can adaptively choose what array entries do I want to observe. And so our algorithm had constant step complexity for clicks and logarithmic step complexity for writes and observe operations, and this was single writer, so only every process could only write to one array entry. And at the same time, in the same year, Wei and others, they published a result completely independent, which had a very similar semantics as ours. Here, a click would return some kind of a handle, and then in observe operations, you could use that handle to identify the snapshot that was associated with a click operation. And so the advantage of that is that you could even observe snapshots that another process has taken, or you kind of get multiple versions, because if you do multiple click operations, you could still reference old click operations. So it's a bit more flexible than what we have. And also, it's kind of restricted read modify writable in the sense that you can update the array with compare and swap operations, but no other operations. And click and update operations have constant step complexity. Unfortunately, the observe operation has unbounded step complexity. Specifically, it increases with the number of update operations that have been performed. And this year at POTC, the Giantis presented a very nice read modify writable adaptive snapshot, partial snapshot object, which has essentially the same semantics as our writable one, except that it's fully read modify writable. So you can modify the array with any read modify write operations that the system provides, and all operations take constant step complexity, and it has linear space. Can't get better than that. With one exception, it doesn't have concurrent click operations. So essentially, you have one process that can keep clicking, but if you cannot avoid concurrency, then you cannot have multiple clickers. In this work, this is exactly what we change. We didn't know about this algorithm, so it's completely independent work, and our algorithm works completely differently from them. But ours is fully concurrent, so we do allow concurrent click operation. It's also fully read, modify, writable, and click and update have constant step complexity. However, our observe operation is slower. We have O of log n steps for n processes. And the space is also not as good. Okay, so I'll quickly talk about some core ideas of this algorithm. We use as a base object, we use a fetch and increment object. So it's just a counter that allows you to get a timestamp. And then we use an array which kind of reflects of what is the ith component that I have in my snapshot array. And then we use a predecessor data structure which for each array component, which kind of does the core of the work that we need to do when we want to do observe operations. And so the idea is that if I want to apply a read, modify, write operation to some component, I first apply that to the array A of I. Okay, let's say here fetch and store in this example. And then I get a timestamp using my fetch and increment. And then I read the array again. It may now have changed because some other process may have applied an operation to that. But then what I do, I take the value that I have read together with the timestamp as a key and insert that into my predecessor data structure. Okay, and then I return the response that I got from my original operation on that array entry. Okay, and so this is all I have to do for an update. And now when I do a click operation, all I have to do is I get another timestamp which records the point in time of my click. And now, when I want to observe a specific array entry, all I have to do is I have to go to the predecessor data structure and find the largest timestamp that's smaller than the timestamp that I got in my click. Okay, and the value that was added to the predecessor data structure together with that timestamp is the latest value that the array had, or is the value that the array had at my click operation. Okay, so this is the core idea, and I guess now the tricky part is implementing this predecessor data structure. And imagine for now that you have an infinite sorted array for that. Then it's relatively easy. All you have to do is, if you want to insert in the predecessor data structure, you look at the first free array entry and you write your value there, and then you can find the predecessor by just doing binary search on that sorted array. Okay, obviously we can have concurrent inserts because multiple processes may want to insert at the predecessor data structure at the same time. The lucky thing for us is that we don't really care if a process doesn't manage to insert. Essentially what we do if we have multiple processes who want to insert, we run some kind of consensus protocol using compare and swap, and one process wins and they get to insert their timestamp. And the other process may lose and not get their timestamp inserted in the predecessor data structure. And that is fine. Why? Because if I do that a couple of times and I don't manage to insert my timestamp, that just means that some other update has linearized when they inserted their timestamp, and my update can linearize with that other one, and it kind of becomes invisible because nobody can ever scan that, and then we don't care about it. Okay, so this just works out very nicely. So this is using an infinite sorted array, and now we wanted to bound the array, and that's actually where most of the work comes in. And so what we'll do is we'll use a bounded but a cyclical array, and which is still sorted in a cyclical way. So values increase until it wraps around, and then they start at the lowest value again. And so we can still do a binary search for timestamps and still answer predecessor queries very quickly. However, the problem is now all timestamps that I have inserted in the array may get overwritten. So I do a process performs a click operation, it gets a new timestamp, and it now when it wants to perform a predecessor query later on in an observe operation, it may need to know the predecessor of that timestamp. And if some other process now overwrites the timestamp in the circular array, then we're in trouble. Okay, so we lose that information. And so the idea now is that we announce the timestamp that we have read, make it available to all other processes, and everybody who performs updates kind of helps me get a complete scan of the corresponding click operation. So processes, while they do updates, they will fill an array for me which has all my values that correspond to my click operation. Because the array, the circular array, is large enough, I have the guarantee that before any of my important values gets overwritten, I will receive a complete scan of that corresponds to my click in this scan array, and then I can use those values. How much time do I have? 4 minutes? Okay. So this kind of unfortunately causes a new problem, which is, okay, so imagine that I perform a click operation, and during my click operation, I obtain a timestamp, and then I want to announce the timestamp, but then I fall asleep. Okay. Now, just before announcing the timestamp, I've been falling asleep, and now the problem is nobody knows that they actually have to help me with a scan. And so there's a simple trick to fix this. So instead of actually getting the timestamp, all I do is I announce that I want to have a timestamp. So I say in this announce array, instead of announcing my timestamp, I say, help me, I want to get a timestamp. And all other processes, then they will see that, and then they will get the timestamp for me. Or someone will get the timestamp for me, either myself or someone else, and then processes can use that timestamp. Okay, so I think what is very interesting about this research here is that we have now 3 different adaptive partial snapshot algorithms, and they are completely based on different techniques and ideas. And they kind of more or less have been developed independently, I believe, anyway. So there's this algorithm by Wei et al., which has the most flexible semantics because processes can refer to click operations from other processes. Unfortunately, it has unbounded complexity, and it also doesn't support all read, modify, write operations. There's the algorithm by the Giantis, which is optimally efficient, at least as long as we don't have concurrent scans. We don't have a lower bound for concurrent scans, but the algorithm is also very, very nice and simple. And so this is kind of, I think, it's the most elegant of all the algorithms. And then we have this work, which is now fully concurrent, but not as efficient as the one of the Giantis. But again, I don't really know of any lower bounds. So it is possible that concurrent click operations inherently require slower operations, but we're not sure. I guess that brings me also to the open problems. One of them is there a more efficient fully concurrent algorithm? And the other one would be to somehow combine the semantics, this flexible semantics of the Wei and other algorithms with these other techniques that are out there. Oh. That's it. Thank you.
I think we have one of the Gianti peers.
I was wondering the space complexity. It had both n, which is like
Yeah. Yeah.
Do you need to know n ahead of time
Yeah, we need to know M and N, I mean, ahead of time right now, because the circular array that we use, that is the space, and we need to allocate it, and that's just optimizing it in such a way that you don't override anything before you have copied everything over for every other process. And the kind of this M times N comes from the fact that you have to help N processes, and you have to sort of create you have to copy an entire scan for N processes over, and all of that takes log N. So this, you see where this is coming from. Yes. Yeah, this was referring to the time complexity. For space complexity, I think we would need to do something very different with our predecessor data structure to get a better space complexity. So this is actually sort of in the previous algorithm, which was just single writer. We used balanced trees for the predecessor data structure. So there I could imagine that you could do. Yeah, no, but then sort of the problem with the balanced trees was that you cannot really do concurrent inserts. So that's why we needed to go. So yeah, you would need to do something different to get below that space.
Yula?
Something from the last paper, the same process
Yes, yes.
it makes sense to come up with a new variant of problem where when you follow observe the process, it turns something from the last paper with linearized with total observe. So it's a more general, say,
Oh, from any click, yeah.
First of all, would it make sense to consider this problem? And do you think the techniques needed would be
I'm not sure. I think the best semantics is, of course, the one that Wei et al. Had, where the click operation just returns a handle. And then you can publish the handle or something, and then anyone can get the corresponding observe operations that relates to that handle. I think that's really the semantics that we want.
Your techniques, where exactly would not work? I mean, maybe
Yeah, I'm actually not sure. I think it might not be so difficult to do that. The biggest problem is if you don't limit. And this is also exactly the problem of their algorithm, is that if you have more and more updates and clicks go further in the past, you need to keep all the information around somehow, right? And so I wouldn't know how to do this with bounded memory or bounded time complexity, and that's exactly the problem that they are having. So we would have to again do something different with our predecessor.
All right. So let's thank the speaker again. So the last talk in this session is going to be a brief announcement on some promising work on predecessor, I guess, range queries and log-free data structures.
Thank you. Okay, so hi, I'm Gal. I'm a new postdoc in EPFL, but today I'm going to talk about our work done during my PhD with RS Bedrock. So it's the same topic as the first talk, but let me briefly mention what we're handling here, which is we're looking at binary search trees, and we want to add an aggregate query to such trees. Meaning a query that summarizes a range of items with consecutive keys into some succinct value. For example, an index query, returning the index of a certain key, but we don't want to traverse all elements in this range. Instead, we want to do it more efficiently by going through a root to leaf traversal and answer the query, which is why we need to embed, to augment the inner nodes with some aggregate metadata. So, for example, the size is what we see here. For example, here, this is the size of the number of elements in this subtree, but it could be other functions of the elements in the node subtree. And this helps us to answer the query. For example, for the index query, each time we descend to the right, we know that we just skipped all elements in the left subtree, but we don't need to traverse them. We can simply take into account the value here. And then we can return our result after doing the whole root to leaf traversal. The problem is that queries read multiple values throughout their traversal here, and updates also update multiple locations, all the ancestors, the metadata in all the ancestors, and then we still need to have each operation appear to happen atomically at once. And this is a difficult problem, and that's why works on concurrent aggregate queries appeared only this year. And well, we heard Eric saying that they're working on implementation. At least as far as I can see, I don't see how any of these implementation, any of these works could be actually used in actual libraries, but maybe I'll be surprised. But I think that it's still an open question to find better solutions that can be used in practice. And so I'm going to show you a different direction. We didn't go as far as the first talk, but we went on and we took another path, and it has some ideas that might be useful to eventually obtain a practical solution. So in what we do in our solution is each update operation and each aggregate query obtain a timestamp. And what we guarantee is that an aggregate query is going to consider all updates with timestamp smaller than its timestamp or equal to it. So, for example, here is timestamp up to 12, but it's going to ignore all updates with bigger timestamps. So to ignore these operations with bigger timestamps, what we're going to do is employ some sort of multi-versioning. So in our multi-versioning scheme, each aggregate value, instead of having just a single value, we have here a history of versions of this value. And then when the delete operation arrives to update this metadata here, it doesn't override the existing metadata. Instead, it adds a new aggregate metadata version and links it to the list here, so that when the index operation arrives and wants to read the metadata here, it can ignore the metadata by the delete because it didn't override the previous one. So what it's going to do is traverse the list until it reaches the metadata with timestamp smaller than or equal to 12. And this way, the delete operation did not sabotage with the index operation. The index can still ignore the delete operation. So that's how we ignore operations with bigger timestamps. The way we still consider operations that have timestamps smaller or equal to us, even if they haven't yet updated the tree, is by using announcements. And so operation announce themselves globally, and now the index can see which operations are currently ongoing and take them into account even if they haven't updated the tree. And in the paper, we have more details about our design. We also present two algorithms implementing it. One optimizes the time of update operations, the other the time of aggregate queries. And that's it for the short talk here. Yeah, so it's pretty similar. I mean, there are subtle differences, but the basic idea is similar. The fact that you need to go backwards, it's just yeah. I mean, can talk about like, but No, I just think that the fact that, for example, each operation needs to. So you mentioned earlier, Eric, that the root is not fully considered, but still all operations need to go through casting the same versions of the root, right? And in general, the fact that updates need to go and perform castes all over this path seems like, so for example, our solution that optimizes the update time in this solution, so it has other disadvantages, but one advantage it has is that updates they only perform one cast operation and they don't contend with other operations further. So, but in others, but it has other things that make it impractical. And in all other solutions, update operations need to perform many cast operations, which I don't think would be practical in real world when you want to just insert an operation, perform an insert operation, which usually performs one or two cast instructions on the target area. Adding so many cast operations with possible contention would possibly make it not really usable in actual scenarios. So we applied it to a local-based tree by Girari and others. And I mean, it could be also probably extended to other trees, but yeah, currently it's applied only to a lock-based tree. So we count on the locks used by this tree.
Thanks again. This ends the first session, and we resume at 11:30.
And the first talk is Broadcast and Consensus in Stochastic Dynamic Networks with Byzantine Nodes and Adversarial Edges by Antoine Elhayek, Monica Hensinger, and Stefan Schmidt. And Antoine will give the talk.
Yes, thank you. All right, so first of all, you might want to know what broadcast is. So the main idea is you are a network, you have n different nodes, and then one node starts with a piece of information, and this node must send its message to everyone else. Nodes can also, if they receive the message, they can forward it as well. Nothing's better than a small example. So here you have a small tree. A node starts with a piece of information, it forwards it, and then in the next round it forwards it again, and then in the next round it forwards it again, and then everyone knows about it. And the big question is usually how many rounds does this need? And the answer also, as always, is it depends on the model. So a very quick not everything exists in there, but of course, if you have a complete graph, then this happens in one round. If you have expanders, this takes log n rounds. In the previous work, we showed that if you have dynamic trees that are adversarially controlled, then you need linear time, non-split graphs, log n time, and many, many, many more. So yeah, I need to tell you what the model is for us today. So it's a dynamic graph. That means that the communication network changes every round. And each round we will have a tree. And the tree is going to be chosen randomly. That is, among all rooted trees, we will choose one tree uniformly at random. And now the question again is, how many rounds does this need? So a small example, in the first round, we choose a tree randomly. We forward the information. And then we remove that tree, and then we choose another one uniformly at random. And you can see here, you have a root. Since it's random, sometimes we might not be very lucky and nothing happens. And then we remove the tree, we choose another one. And this time we got lucky and a lot of information is transferred and we are done. And today I will tell you that this takes log n rounds when you have a node. The main theorems that we're going to use are up here. So the first one is you need to know how many rooted trees there are from which you can sample. Very famous theorem tells you that there are n to the n to the minus 1. Another theorem that's less known is that if you have e edges that you want to be in the tree, and you're asking how many trees exist that contains these edges, then the answer is n to the n minus 1 minus the number of edges you've chosen. So you can see if you choose 0 edges, then this corresponds to the previous theorem. And another interesting thing is it doesn't depend on how the edges are distributed. And so if you divide the second number by the first one, you get that if you have a set of edges that you'd like to see in your tree, and you want to compute the probability that they appear, then it's just going to be n to the minus number of edges you've chosen. So a small example, you might have something like this. You have 9 nodes, and then you really like to see these 2 edges up here because they would forward some information. And the question is what the probability that they appear in the tree. Well, 2 edges, so it's going to be n to the minus 2 or 9 to the minus 2. One interesting thing you can see is, okay, here we have 2 edges, but what if we only look at the first one? So this is just one edge. And what's the probability that it appears? It's n to the minus 1. This one, what's the probability that it appears? It's 9 to the minus 1 as well. And then if you multiply them together, then that's 9 to the minus 2. And so you can see that the probability of all of the edges appearing is just the product of each of them appearing individually or any subset of them. Which leads us to the very nice theorem. which I summarize like this. Edges are either independent or incompatible. And by that, I mean, in the first one, you can see that the edges could appear in a tree. So the probability that they appear is n⁻e. And they are all independent. So having this edge appear doesn't really, the probability that happens is not affected by if the other ones appear or not. On the other hand, we have a set of edges that are not compatible together. So this one here cannot really happen. There is a cycle, which does not happen in a tree. Here you don't have a cycle, but you have a node that has two parents. That also cannot happen because we're in a rooted tree. And that's essentially everything that can happen. Either you have a cycle, either you have two parents, or everything's fine. Right. So how can we use this? Let's say you are at some point in time, and you have some nodes that are informed, and some other node that are not informed, and you want to compute the probability distribution of what's going to happen in the next round. Well, let's say you take a particular node U, and then you take a particular informed node I1, and you want to see the probability that there is an edge between the two. Well, we've just seen that's 1/n. And then let's take another informed node and see if there is an edge between I2 and U. That's 1/n as well. And you can do that for all of them. And then if you want to see the probability that U gets informed in general, that's just one edge from all of the informed nodes to U. That's the number of informed nodes over n. You just sum over all of them. All right. Then you want to do the same thing for V, and that is the same as well. Now, the problem is you cannot really say if this is independent or not, because there might be some dependencies that you don't really see. So now you want to compute the probability that two of them happen at the same time. And again, we're going to decompose it node by node. So let's say you take a node I1, and then you want to see what's the probability that there is an edge to U and to V. Then that's two edges. And by what we saw before, that's just 1/n². But there are also other ways for U and V to be informed in the next round. That is, if you have an edge from I1 to U and I3 to V. Then again, that's just 1/n². And then what you want to do is you want to sum over all the possibilities. So all the possibilities is just the probability that there is some informed node that goes to U and some other one to V, and then you sum over all the choices of I, J, and Ik. So you have I to the squared, many such possibilities, and each of them has probability 1/n². And now again, you realize that this is just the product of U being informed and V being informed. And this means that U and V being informed are just independent. And yeah, another way to write this is to say that at some round, for the next round, you just look at the number of newly informed nodes. That's the sum of the of Bernoulli independent variables, each of parameter I/n, and that's on the number of nodes. Written mathematically, it looks like this. So the next round is how many informed nodes you have now, plus the Bernoulli independent variables. Some of you might recognize the equation for the pull model. If not, you probably can be convinced that this takes 2 log n time. Yeah, I will not go more into details for this. So this leads us to the following theorems. The first one is that broadcast happens in log n rounds. Another one is all-to-all broadcasts happens in log n rounds as well. All-to-all broadcast is when you have each node having a piece of information and wants to send it to everyone else. And then another application is whenever there is an algorithm that works on a clique. So you can think of Byzantine consensus or these kind of things. Then in this model, it takes t times log n rounds. We have some generalizations. One of them is what happens if we have some failing nodes. So failing nodes here, I represent them in black. And again, you have a node that starts with a piece of information. And then the nodes take part in the failed nodes take part in the tree as well, but they don't receive or forward the message. So here we have something like this. And then we remove the tree, put it back. There. Forward again, remove, put another one. Forward again, and so on. And now we have broadcast. Yeah, so a similar analysis shows that everything goes through as well. So now you can also have dishonest nodes work in the network as well. And assuming some crypto signatures, then you can also apply any algorithm you know on the click. Another generalization that was a bit more interesting technically was if you have some adversary that can choose up to k different edges, and then we choose the tree uniformly at random among the trees that include these edges. So for example, we have the same structure again, and then adversary says, okay, I want these two edges to appear in the tree. And then we just select a tree that includes them. We forward the messages, and then we start over. The adversary can choose other two edges. We choose a tree, we forward the messages, and so on and so forth. What's very interesting in this model is that we can exactly define what the best strategy for the adversary is. I will not talk about it now, but if you ask me about it, I can show you pictures afterwards. And then we can show that the adversary can delay the broadcast by k rounds more than what we had before. So now the total running time is k plus log n rounds. So that's it for my paper. For future work, we can ask what happens if we take other instances of random graphs, so expanders, cliques, and so on. And also, can we use the very interesting probabilistic analysis for other problems? Yeah, I'll listen for your questions now.
Any questions? Okay, so I actually have a question. So do you have any conjecture what property of the graph relates to the time that it should take? So what is it about trees that make it log n? And maybe, I don't know, if it would be a star, I guess it would be O, right? So should be.
Yeah, it's a question that's quite hard to answer. So for example, for trees, if we change the tree in each round, then it takes log n. But I believe the depth of a tree chosen at random is something like square root n or n to the 1/3 or something like this. So it's quite like it's not clear, and it really depends on per model basis. It can really change.
Any other question? Okay, let's thank the speaker. So the next talk is going to be about memory lower bounds and impossibility results for anonymous dynamic broadcast by Garrett Parzich and Joshua Daymude, and Garrett will give the talk.
Okay, thank you. I'm Garrett Parzich. This is work I did in collaboration with my advisor, Josh Daymude. Okay, so dynamic networks are just sort of the study of networks where your edges and possibly the nodes that are in the system are changing over time. So it's sort of like the first time these sort of dynamics are being considered in distributed systems were just sort of like faults, like edge faults or node faults in the system, changing the topology. But nowadays we have many systems where dynamics are very inherent features. They're not just faults of the system. And so things are much more highly dynamic in these systems. So, lots of examples of basically with all these like wireless communication protocols we have now computational entities that can move around and communicate wirelessly. So mobile phones, satellites, all these sorts of things. Okay, and then sort of with all of these new technologies, there's been sort of all sorts of different models for how we should think about dynamic networks, and a bunch of computational questions for each of these models that go along with it. Okay, so our main motivation was we wanted to know sort of how much memory we needed to compute in these dynamic networks. And we had sort of a goal of whether or not we could do sub-logarithmic memory. And so one consequence of this is that we considered anonymous nodes, since we assumed that if you don't have logarithmic memory, you would not have enough memory to hold IDs. So to sort of start in this problem, we just chose a simple problem of broadcast to try to analyze the memory complexity of this problem. So it's just nice to choose a simple problem to get sort of the first lower memory bounds. And then also broadcast is sort of a ubiquitous problem that is also very useful. It's sort of a sub-algorithm for many other problems. And so sort of getting memory bounds for broadcast also will carry over to a lot of other problems as well. So if all you want to do in broadcast is just send a message, you have one node who wants to send a message to all other nodes in the network. Well, one simple way to do this would just be when you get the information, just send it and just send it forever. And eventually everyone's going to get the message. But this is sort of an uninteresting algorithm, and it's also very computationally expensive to just be sending messages for all of time. So we also want to investigate sort of terminating broadcast. And so we sort of have two different kinds of termination we investigated. So one is what we call stabilizing termination. And so the idea here is that eventually all nodes should become idle. That is, they should stop sending messages. And then more strong version of termination would be termination detection, where you actually have to, we require that the broadcaster should be able to know that the broadcast is complete. And this might be more useful in real systems if you need, like, if you're using broadcast maybe as a sub-algorithm, and you need to know that the broadcast is complete before you start with something else. Or also, in the case of stabilizing termination, you might become idle, but you don't necessarily know that the broadcast is complete. And so you may still have to keep some state in case you become reintroduced into this broadcast again. Whereas termination detection, you know it's done, and so you can sort of remove all the state needed for that computation. Okay, so in static networks, it's very easy to do with very low memory. Sort of the most obvious broadcast algorithm would just be, that terminates would be, you receive the message, and then the first time you receive the message, you send it out, and then that's it, and you're done, and you never do it again. This will work, and you only need one bit just to store whether you have received the message or not yet. Interestingly, in synchronous networks, it has also been shown there's an algorithm that uses 0 bits of memory. So this is a very interesting algorithm to us, and so we wanted to know, how much more difficult is this in dynamic networks, given that we can do it with literally 0 bits in static networks. Okay, so here's our model. So as I said, we assume anonymous nodes. They're not going to be storing any IDs. We're going to look at synchronous systems. Synchronous are slightly less applicable to real systems. We don't have, like in the static case, we have very strong synchronizers, and so synchronous algorithms in some sense are fine, but in dynamic networks, we don't really have that, and so they're maybe not so applicable to real-world systems. But because we're looking at lower bounds, it's actually sort of useful to look at synchronous, because certainly any asynchronous adversary could simulate a synchronous one. And so the lower bounds will also apply to asynchronous systems. We assume there's no port labels. So basically nodes have to communicate through a broadcast mechanism. They have to send the same message to all of their neighbors. And we're also going to look at purely deterministic algorithms. So just real quick, the way that computation and communication works. So as I said, it's synchronous, and it's synchronous both in sort of topology changes and in communication. So first, a network topology is defined, and we are assuming that it's an adversarial dynamic network. So it's sort of chosen in whatever way an adversary chooses to thwart our algorithms. And we just require that the graph must be connected so that we're able to sort of spread this information through the network. And then every node sends messages based purely on its state, and it sends the same message to all of its neighbors. Then it receives all its messages, and then updates to a new state based on the messages it's received and its current state. Okay, so previous work, there's been a very sort of successful line of research in this exact model with anonymous nodes, but it's been very concentrated on trying to count the number of nodes in the network. And they've also been very concentrated on how much time it takes. So I'll just go through this quickly because it's not too important for us. But at first, there were very slow algorithms that required knowledge of the maximum degree. Then eventually people found an algorithm that did not require knowledge of the maximum degree. And then eventually there was a sort of breakthrough of the first polynomial time algorithm. And then very recently, there was a very nice algorithm by De Luna and Viglietta that actually showed that you can count in linear time, which is basically optimal because we don't really parameterize by the diameter in dynamic networks. So big O of n is as good as you can do. So it is interesting for us because being able to count, obviously, it means that you can also do broadcast. And so all of these algorithms will also technically solve broadcast for us. But also sort of the lower bounds we get for broadcast will also apply to counting. So we also show like necessary memory that you need for counting as well. Okay. So there's sort of two different dimensions of assumptions that can change our results. So the first thing is termination, as I've already talked about. And then as we were writing our proofs, there was also this other assumption we found that could change things. It's what we've called idle start and non-idle start. And this is basically about if nodes start idle or not. So for example, in idle start, all nodes except for the broadcaster must be idle. So they're not allowed to send messages, and they must be woken up first. So they must receive a message before they're allowed to start sending messages. Whereas in a non-idle start, all nodes are allowed to be sending messages at the beginning. So sort of before our work, for stabilizing termination, nobody has really investigated this in this exact model. There's a similar model by Odell and Wattenhofer, where they conjectured that it would be impossible with log n, that you would need strictly more than log n memory. For termination detection, the algorithm by De Luna and Viglietta that showed that you can count in linear time is also will give us it's able to do termination detection. So this is like the one algorithm we know of that can actually do termination detection for us, but it requires very high memory. It required n cubed log n memory. And then as far as we know, no one's really considered this case of termination detection with idle start. Okay, and then in this paper, we provided a log n algorithm for stabilizing termination. It doesn't directly refute the Odell and Wattenhofer conjecture because they're not exactly the same model. But it's interesting in this model that you could do logarithmic memory. The same algorithm also works for idle start. But then we were also able to prove a lower bound that you need strictly more than constant memory. So this sort of shows a separation between static networks and dynamics, that you do need strictly more memory to compute in these dynamic networks. Then for termination detection with non-idle start, we showed that you need at least log n memory. And then for termination detection with an idle start, we actually showed it's outright impossible to do. So I'll sort of go through sort of the main points of my proofs real quick, or some of them. So I'll start with the impossibility proof. It's a very simple proof, actually, but it sort of has some of the ideas that we used for our later proofs. So we assume that we have some algorithm that is going to correctly solve broadcast with termination detection for us. So we start at round 0, and the algorithm on some graph G, the algorithm is going to run on this graph G, and eventually at some round K, the broadcaster is going to declare termination, and we assume that it does so correctly. Our goal is now to actually get to a state where the broadcaster has declared termination, but there is still an uninformed node in the network contradicting the correctness of this algorithm. So the way that we do this is we can just simply add a path to our network. And sort of the important point here is this idea of idle start. And now we see why having an idle start affects these results. And so if we connect at the very first round, if we can now connect the broadcaster B to this node V0, and V0 is technically idle right now. And so it is not going to send a message to B. And so B receives all the same messages as it did without this path here. It basically doesn't know it's here. And so it operates exactly as it had without this path. And so we can sort of continue on in this way with this path. So at every round, one more node in our path is becoming informed. We just make the path long enough so that by round K, there's still an extra uninformed node in the path. And this graph G has received all the same messages as it had without this path. And so the broadcaster must have declared termination here in round K, and it has done so incorrectly. Okay, and then I'll sort of talk about how we adapt this to get this logarithmic lower bound when we have non-idle start. So we have to be a little more clever now. We can't just do any graph G to get this impossibility result. So instead we use a complete graph. So this is sort of acting as like G was before in our previous proof, where we're going to sort of take this and try to find a way to get a configuration where the broadcasters declared termination while there's still idle nodes here. But the main problem is that we can't do exactly what we did before, because if now we attach these nodes, the problem is that this node is now going to send a message to these non-broadcaster nodes. And so it's actually going to change one of these states. So before we had all of the non-broadcaster nodes went into state B2, but now this one that's been connected to the path is actually going to go to some different state, unknown state that we don't know about, X. But the main point is that we still have every other node, except for that one that was connected to the path, will still proceed to the same state they would have gone to before. So we still have a lot of symmetry here, but we don't have exactly enough nodes to be able to create the exact configuration we created before. But sort of the idea then is to instead now look at the complete graph on n-1 nodes. And if we happen to have this configuration where the broadcaster is in state A2, let's say here, and the non-broadcaster are in state B2, and this was exactly the sort of one that we could attack before, right, where we had A2 and B2s. Well, now if this happens, what we can do is start with our k sub n, run the one step where we get our node, we get our new state x that we don't know about, but we can just sort of remove it from the complete graph and just stick to this complete graph on n-1 nodes. And now we know exactly how this is going to progress. We know that it's going to go to this A3 and B3 state, but now we'll only have 2 in B3 in this example here. But the basic point is that we can sort of gain information on sort of how this network is progressing and sort of try to slowly progress our way towards a configuration where the broadcaster has declared termination while still having a idle node. And so this is sort of the general argument we also use for some of our other lower bounds, where we have our complete graph, which is very highly symmetric, and then we also have the path, which basically just acts as one node in our path is going to get informed at a time. So by the end of this algorithm, we still have an uninformed node. Okay, so the basic argument from that is that if f of n is the number of states used for n nodes, and if we suppose that there is some n0 such that it uses less than the root of n0 states, well, actually we can show, because complete graphs are so highly symmetric, that there's only n0 unique configurations of complete graphs, because you only have a square root of n0 states. And so the broadcaster gets one state, and then all the other nodes get one state. And so there's in total n0, root n0 squared, or just n0 total unique configurations that you can have. But we show that you can sort of also find n0 configurations where we still have a non-informed node in the network. And so since we find n0 of these configurations and there's less than n0 total configurations, we know that we must have found some terminating configuration while we still had a uninformed node in our network. And so then the result of that is that we know that f of n must be greater than or equal to root n for all n. And so just the logarithm of that would be the bit complexity. And so that shows that it must be at least logarithmic. Okay, so it seems like our sort of goal of sublogarithmic algorithms is probably not achievable. We were not able to find any better than a logarithmic algorithm. And in the case of termination detection, we outright showed it's impossible. But we think maybe it'd be interesting to relax some of these assumptions to see if we might be able to do more with less memory. So something we would change is the dynamics. So before, when we had idle nodes, we could sort of hide them behind other nodes. And so we sort of had graphs that operated without even knowing that those idle nodes were there. So maybe if we allow more time, if we allow multiple rounds of communication to happen before we change the network, this will sort of get rid of that problem. And so maybe it will be easier to do computations. Also maybe looking at sort of more randomized algorithms would make it much easier, or relaxing correctness, maybe just some kind of approximation algorithm where you get it to most nodes in the network. And also maybe complete anonymity. Maybe having some level of recognition in the network might make it easier instead of being totally anonymous. And then of course, improvements, there's open questions about the improvements of the lower and upper bounds. There's sort of a gap between all of the lower bounds and upper bounds. So there's still questions about what the correct answer should be, which ones can be improved. And there's sort of also this question of, our termination detection, the only algorithm we know for termination detection for broadcast requires counting the network. And so there's also a question of, would it be possible to do this without actually having to count all the nodes in the network? And okay, that's it.
Any questions?
The node does know the does information there. Do you think if you give them this information, they will still obtain the impossibility result, or is this?
It would change things. I think you would still be able to get logarithmic results, but it might actually become possible. I'm not entirely sure. I'd have to think.
Any other question? Okay, so let's thank Garrett again. So the next talk is a brief announcement towards optimal communication, Byzantine reliable broadcast under a message adversary by Timothy Alboy, David Efrey, Ran Geles, Karmit Chazai, Michel Reynal, Elad Michel Schiller, Francois Tainai, and Vasily Zikas, and Timothy will give the talk.
We have a bit of trouble. Oh no, it's all right. Okay. Okay, thank you for the introduction. So, as Ran said, I will present you some of our work with these colleagues. the topic of improving the communication of Byzantine reliable broadcast under a message adversary. So first of all, what is Byzantine reliable broadcast? It's a fundamental one-to-many abstraction, where we have one sender that wants to disseminate some message to the rest of the system. And importantly, some nodes in the system may be Byzantine, that is, they can behave arbitrarily. But BRB ensures that eventually everyone agrees on the same message, even if the sender is Byzantine. So this BRB abstraction has a lot of important industrial applications, such as in cloud computing or even online payments. And on the other hand, we have the message adversary model, which represents a kind of external adversary that can impact the network by corrupting or deleting messages. And this adversary effectively captures some sort of partial dynamicity, such as the network interference, and the disconnections or reconnections of nodes or dynamic topologies. And as we can see, the message adversary model and the Byzantine model are orthogonal, in the sense that the MA message adversary considers dynamic and network-related faults, whereas Byzantines represent static and node-related faults. So what happens if we combine the message adversary with BRB? We obtain what we call the MBRB abstraction, which is a generalization of BRB to this new hybrid fault model. So in this model, we consider an asynchronous distributed system of n nodes, out of which at most t can be Byzantines. And in addition, we have a message adversary that can delete up to d copies of each message that is sent by a node. So the first MBRB implementation is due to this paper, which introduced the original MBRB algorithm, featuring an optimal resilience against faults of n greater than 3t plus 2d. However, this algorithm also incurs a high communication cost of this asymptote. So the question is, can we do better? Can we improve the communication of MBRB? And so we answer positively by introducing our coded MBRB algorithm, which improves the communication cost by a factor of n. So in these formulas, we have a size of m, which denotes the size of the MBRB message in the number of bits, and kappa is a security parameter. So instead of having n times m plus n square kappa, like in original MBRB, we have only m plus n square kappa. And to do that, we leverage techniques such as error correcting codes or Merkle trees. And the nice thing is that we also keep this optimal resilience bound of n greater than 3t plus 2d. So if you're interested in all the nifty technical details, you can check out the full version by flashing the code. So thank you very much.
Okay, that was very brief. Any questions?
Lower bound currently?
It's a proven lower bound. So effectively, our algorithm is optimal. Oh, you mean the communication cost? Yeah, it's no, it's not the lower bound because in BRB the lower bound entails that every node must receive the whole message. So you must at least have a communication of the whole message m. Plus, the Dolev-Raishuk lower bound entails that the BRB of a single bit incurs the sending of n square bits in the system. And actually, these bounds are not overall, they are per node, which is a bit confusing, but if you want to have the overall cost, you must multiply by n. So here we have a factor of n that is too much, but we found an even better MBRB abstraction, implementation that is near optimal. So this is in the full version. So we didn't include it in the brief announcement, but we can achieve the optimal. by a small factor of kappa, but okay, so yeah, we only considered a message adversary that suppresses messages but does not corrupt messages. But like our rough intuition is that if in asynchronous systems, if you can allow the message adversary to corrupt messages, then due to asynchrony, the adversary can sort of like impersonate any node in the system. So like it can corrupt any number of like if you are based on quorum systems, then the corruptions can like surpass the threshold of malicious messages that is tolerated. So if it does not delete messages or it does not corrupt messages, what would it do? Oh, yeah, I mean, by deleting messages, the adversary can already like impact the topology of the system in a way, but not in a static manner. Like it can, like during some communication step, the topology is this because of the adversary, and in the next one, it's different. So in a way, like we can already capture dynamic topologies using this definition of the message adversary. Yeah. Yeah, so it's analogous to receive omissions, I think. But like we found it like the simplest model for representing disconnections in the system. So.
Okay. Okay, let's thank Timothy again.
Thank you.
I'm sorry.
Just stop. Yeah, but it's see if you can.
Okay, so we are here at session 3, the last session of the morning today. This is a session on distributed assignment problems. And the first talk here is going to be by Siré Bai on almost optimal algorithms for token collision in anonymous networks. Take it away.
Hi everyone, I'm Siré Bai from Nanjing University, and I'm here to present our paper, Almost Optimal Algorithms for Token Collision in Anonymous Networks. It's a joint work together with Xinyu Fu, Xu Dongwu, Peng Huiyao, and Chao Dongzheng. Here's the outline of the talk. There will be 6 parts. In introduction, we'll first talk about the definition and applications of token collision. For related work, we'll show the existing results. For results, we give deterministic and randomized upper and lower bounds. And for the deterministic algorithm, we give some details. And for randomized algorithm, we give a quick go-through. And finally, for summary, we review the talk and emphasize key points. For introduction, we begin with an informal definition of token collision, where a token represents a piece of information, and each node in the distributed system holds some tokens. Token collision is to check whether there is duplicate information. Here is an example of token collision in real world. Imagine that a group of servers is hosting online banking service, and each token represents a logged in user. Token collision is to check whether there are duplicate users logging into the systems. See the figure for a better understand, where Alice is logging into the first server and Bob is logging into the second server, where the third party Eve is trying to log 2 servers simultaneously, which causes a collision. So our second example is database system, where read and write operations shouldn't occur at the same time. So in this case, token represents timestamps, and token collision is to check whether these transactions have duplicate timestamps. Now, an important application of token collision is Las Vegas unique identifier generation, where unique identifier is also called UID, is commonly used in distributed computing for symmetry breaking. And a natural approach to generate UID is for each node sample theta log n uniform random bits, and apparently it's a Monte Carlo UID generation. For Las Vegas UID generation, we need token collision as a sub-procedure, where after Monte Carlo UID, we check the ID uniqueness deterministically by token collision algorithm. If the check succeeds, we output the IDs. And if the check fails, we go back to Monte Carlo UID generation. And at this point, we obtain a Las Vegas UID generation. So knowing that token collision is indeed an important problem, we are ready to give a formal definition of token collision. So there's k tokens, each has length of L bits, and these tokens are arbitrarily partitioned and distributed to n nodes, and some of the nodes may be empty. Token collision is a problem to check whether all these tokens are distinct. Here is an example that we have a collision in value 4, which appears twice in the nodes. So for model, we consider the anonymous congest model, where anonymous means that nodes don't have unique identifiers and can't know the identity of neighbors. And congest stands for each message has theta log n bits. It remains to ask why we consider anonymous citing. Well, we have 2 reasons. First, otherwise, if not anonymous, then nodes have unique identifiers. There is a generic algorithm to solve token collision or almost every distributed computing task. First, we select the node with minimum ID to be the leader. Then, the leader is very powerful to first aggregate global information from other nodes, then locally computes the result, and finally disseminates the result to the rest of the networks. And second reason for anonymous is that it's a very challenging and interesting question, since a number of fundamental computing tasks are deterministically unsolvable in anonymous networks. For example, leader election, coloring, bipartisanship testing, and plenary testing. However, token collision is not one of these problems. It is surprisingly solvable in deterministical anonymous networks. For related work, to our surprise, although token collision is an important problem, we find that it has not been explicitly studied in the context of distributed computing, but similar problems has been investigated elsewhere, like element distinctness, where a given set of elements are distinct is discussed, and it is extensively studied under Curry complexity. And here is a table of what we found with a series of classical and quantum results for element distinctness. For results, we first give some deterministic bounds. So atom 1, if L is big or log n, that means the token is small and can be fitted into one message. Then we have a upper bound here. And the second atom, where L is omega log n, that means the token is large, and to send one token, we need multiple messages. And then we have another upper bound, where tilde stands for we ignore polylog factors. And finally, we have a lower bound, which can be seen that when L is bigger than log k, our lower bound matches the above upper bounds. We have a special case here when tokens are really small and L is small O log n in particular. The runtime is big O d plus small o k. And we find it interesting because d is inevitable in global problem, and the runtime is very tight. For randomized bounds, we give upper bound and lower bound, which are very close with just an additive gap. And compared with the deterministic scenario, randomized bounds have L impact very limited. And finally, we have a deterministic impossibility result where nodes don't have UID and only know local input tokens. Then it is unsolvable to solve a token collision problem. So for deterministic algorithm, we first give an overview when L is big or log n, which means the token is small and can be fitted into one message. Broadly speaking, our algorithm consists of two phases. First, we build BFS tree or BFS trees by floating tokens. And second phase, we detect token collision by first compute BFS tree size, then aggregate tokens to the root. And the root can make decision whether there is token collision or not. In detail, in phase 1, each root is initialized as the root of a BFS tree, and it keeps building BFS. But it keeps building BFS by sending identifiers to neighbors. And when the root receives a smaller ID from others, it is no longer the root, but it keeps building BFS. So when a non-root node senses that all children are ready to quit BFS, it itself
Let's get started again.
Okay. Let's review quickly of the last page that our algorithm have two phases, and we're going to talk about phase 1 BFS building. And each node starts as a root of a BFS tree, and when they receive the small ID, it becomes a non-root and keeps building BFS, until all children ready and it itself is ready. Now, when it is waiting at the ready state and it receives a small ID from others, it joins the new tree and restarts BFS building. And of course, when again all children ready, it still enters the ready state. Now let's go back to the root part. When a root senses all children ready, it broadcasts a quit signal, and it quits phase 1 afterwards. So when a non-root is being ready and receives a quit signal, it forwards the quit signal and returns from phase 1. So the above procedure have some guarantees that when there is no token collision, only one BFS tree should be the output. And when there is token collision, there could be one or multiple trees. See the figure for a simple example. When there are two identical values with the red node and the yellow node, none of them can be the child of the other one. So we have two trees, with a blue tree and a yellow tree. So based on phase 1, phase 2 is very simple. We first compute the BFS tree size, then aggregate tokens to the root, which is very similar to the standard convex cast procedure. And a root can always distinguish itself as being the only root or one of the multiple trees by value n or k. So when it has value n, it compares the tree size to n, and it can see if it is only root containing all nodes, or it can compare the all tokens it has to k and see if it has all tokens. When it is the only tree, it has seen all the tokens, then it can decide whether there is a collision. And when the root senses it is one of the many trees, that implies collision has already happened in phase 1. Now, correctness proof. We here show our main lemma that when no collision happens, phase 1 only outputs one BFS tree. Recall that in phase 1, a root waits until all children ready, then broadcasts quick signal. So here, see the blue node. When it is connected with the yellow node, and the yellow node is the only neighbor, the blue node contains the yellow node to its child. That way, the blue node has no child, and it broadcasts quick signal and enters phase 2 directly. But the yellow part is still building BFS tree. That is what happens when there is collision. Quick signal causes phase asynchrony. So that makes us wonder what happens when there is no collision. Is similar asynchrony still possible? Or in other words, can tree end phase 1 before main ID arrives? Well, the answer is negative. So we are not going to go through the proof steps, but to give intuition that when BFS building tree, any root is one of these cases. So first, it grows the tree freely that never senses a smaller ID. Or the root meets another smaller ID, and its own tree is taken, part of its own tree is taken away by the smaller ID tree. Or even worse, the root completely joins the new tree and disappears. So with these three cases and careful analyze, we can prove that our lemma is indeed correct. So when generalizing to large tokens, which means that tokens need multiple messages to send, we introduce pipeline technique. So trivially, when we compare identifiers, we need all the bits. But actually, what is really useful is the most significant bits. So we now cut the complete identifier to complete identifier pieces, and we send each piece in one round to reduce time complexity. And as shown, at last, our complexity has reduced greatly to almost optimal. Now for randomized algorithm, we now have 3 phases in the overview of the algorithm. And phase 2 is newly introduced that the root constructs and broadcasts a hash function into its members to reduce token length. So that is what distinguishes from randomized to deterministic complexity. For summary, recall that we define token collision as to detect information duplication. And for model, we study the anonymous congest model because it is very interesting and meaningful. And for application, token collision can be used for Las Vegas UID generation. And for deterministic and randomized bounds, we give almost optimal algorithms. Okay, that's all. Thank you.
Okay, thank you. Any questions? Okay, then given that we're running a few minutes late, I think we're going to, oh, so I'm sorry.
Well, message complexity we have actually considered, but here it is. We involved a lot of broadcasts, so the message complexity is not good. We assume it as a future work.
Any other questions? Very good. Thank you. Let's move on. Okay, so for our next talk in the session, we have Rangelis talking about T-sorting in 1 and 2 rounds. So take it away.
Thank you. Yeah, I'm going to talk about T-sorting in 1 and 2 rounds. This is joint work with Zvi Lotker and Frederic Marmotren. And let me start by defining what T-sorting means. So T-sorting is just sorting with T-comparators. What are T-comparators? T-comparators are just elements that get T values or T elements and sort them. They output the highest element here, let's say, and the minimal here. What is T-sorting? Well, T-sorting is an algorithm that gets n elements to sort and is supposed to sort them using T-comparators. Okay, so we get n elements, and we can decide which element goes to which comparator. And our goal is to get enough information at the end so that we will be able to sort elements. One thing that I would like to say is the notion of rounds. So here you have, I show you an algorithm with 3 rounds. What does a round mean? If the inputs for this comparator depends on the outputs of some previous comparator, this will be a different round. So here you can see that we put to this comparator some output of the first one. So this would be the first round, this is the second round, and so on. Okay. I'm going to focus in this talk on sorting algorithms with 1 round, with a single round, and with 2 rounds. So here is the case of 1 round. Okay, we have only 1 round. We have the n elements, and we need to decide which element goes where. We can put the same element to multiple comparators. So definitely, we don't expect here to have a. We don't expect here to see a sorted array because multiple elements exist. But we would like to have enough information here that we will be able to sort, or some external observer will be able to sort the elements to get the full order of A1 to AN. And maybe you ask yourselves, why should we even care about sorting with 1 round? Or maybe you ask yourself, how this even relates to conference on distributed computing? So let's consider the following example. The disk program committee gets n papers that were being submitted, and we have a lot of PC members, and each PC member is assigned with, I don't know, T papers, at most T papers, and each PC member needs to review the papers. What does it mean to review them? Just to rank them, to say which one is better than the other, and all the PC members get the results, and they send it to the PC chair, and the PC chair decides the total order of all the elements, and which papers will get into the conference and which will not. And in this case, we don't have a second round. We can only assign the paper once to the PC members, and that's it. That's what we have so far. Now, if we understand well sorting in 1 round, maybe we could realize what is the optimal size of the PC, of the program committee, right? How many PC members do we need? And so on. So this is one motivation, maybe, why we would need sorting in 1 round. So let me denote by opt and nt the minimal number of comparators needed in order to sort n elements using T comparators. I hope you can see this table. This is some previous work for deterministic t-sorting algorithm. You can see that most of previous work considered the case where t is 2, so we only compare pairs of elements with multiple number of rounds, and there are upper bounds and lower bounds. And you can see that these bounds scale with d. The more rounds that we have, usually the less comparators that we need, which makes a lot of sense. In this paper, in this work, we consider the case of large t and a single round, and we will show that this number is a lower bound for the number of comparators needed. And we will also show an algorithm that uses at most 3 times the lower bound. For special cases, for instance, when t is a power of a prime, we actually show an algorithm that achieves exactly the lower bound. So this is for the deterministic case. We will also discuss randomized algorithm, but for the randomized algorithm, we will discuss the case of 2 rounds. Again, there is some previous work with upper and lower bounds. You can see here, this is for arbitrary size of comparators, and they are kind of matching the lower bound and the upper bound. This is also the information theoretical bounds. You can't do better than that. There is a lower bound by Alon and Nazar for the case of t equals 2, and up to log n rounds, which looks like this. In this paper, in this work, we consider, as I said, 2 rounds and arbitrary size of t. The lower bound of Alon and Nazar follows immediately, and we get almost the same bound divided by t square. And I will show you, I will discuss a little bit an algorithm that achieves this many comparators. And if you do the math and plug in d equals 2 in the other lower bounds, you will actually see that this is asymptotically tight. You will have to believe me so. Okay, so let me start by discussing the deterministic case of t-sorting in a single round. A little bit of trivial observations. Folklore, if t equals 2, then we can only compare pairs of elements, then we must compare all pairs of elements. If there are 2 elements that we don't compare, we will not be able to sort them. So the optimal number of comparators is n choose 2. This is the number of pairs that we have. And it's not too difficult to see that if we have larger comparators, the minimal number of comparators that we will need is exactly this. So we still need to compare all pairs. And every time we put elements into a t comparator, we get information about t choose 2 different pairs at most. So the number of comparators that we will need is lower bounded, information theoretically lower bounded by this number. This number is not necessarily an integer. And the thing is that even if we round it up to the next integer, it might still not be achievable. So for some values of n and t, you cannot sort with that number of comparators. And our task was to find when you can do it, when you cannot do it, and understand better the situation. So here is one theorem that we get, and it says the following. For any n and t, it is possible to sort n elements with t comparators by employing at most 3 times the information theoretical bound. Okay. And if we are lucky and t over 2 divides n, then we only need 2 times the lower bound. And let me maybe explain how we get this. It's very simple. So let's assume that t over 2 divides n. Let's take the n elements and just split them into subsets of size t over 2 each. So you have all these subsets, S1 until S2n over t. And now we can just take all these subsets, take any pair of subsets, any 2 different subsets. We have t elements in the union of them, and we just take these t elements and put them in one comparator. So as you can see, any 2 elements reside in, wherever subset they reside, they will be compared by at least one comparator. How many comparators did we use? Well, exactly the number of subsets, 2n over 2, choose 2. And if you do the math, you will see that this is at most 2 times the lower one. The problem is that we might not be lucky, and t over 2 might not divide n, and then we would just need one more set for all the leftovers, because the n doesn't split exactly. And this extra set just gives us this 3 constant. And the number 3 here is actually necessary. So in some cases, for instance, when t is very large, like when t is n minus 1, you actually need 3 comparators. You can't do with 2. So this 3 is necessary. One more theorem. So this is the special case where when t is a power of a prime. In this case, we show that you can sort t square elements with t comparators, and the number of t comparators you need is exactly this information theoretical lower bound. And we have another result that talks about the case where t minus 1 is a power of a prime. In that case, you can sort that many elements, again, with the minimal possible comparators. How do we get this theorem? Well, we get it by showing a very interesting connection or reduction to design theory. Design theory is a field of mathematics that deals with finite sets and their properties. Specifically, we show a reduction between minimal sorting, or sorting with the minimal number of comparators, and a design known as two-Steiner system. A two-Steiner system is a collection of points and lines. Line is just a set of points, in which every c points uniquely determine a line. So in a two-Steiner system, every 2 points uniquely determine a line. So a line is just t points. Here, to see the reduction, so every point will be an element. Every line is just t points. It's just a comparator. And if we can assign points to lines such that any 2 points uniquely define a line, then we can set the elements into 2 comparators, and every 2 elements are being compared exactly by 1 comparator, which is the main thing that and required. What about other values of n and t? Now, because of this reduction to design theory, we can use all the knowledge that the field of mathematics and design theory has about designs to know or to get more information. So, for instance, some values are not possible. If t equals 6 and n is t squared, then this is a very famous question known as Euler's 36 officers, and it was shown in the 1900, the beginning of the 1900s, that you cannot sort 36 elements with 6 comparators using the minimal number, the information theoretical bound of comparators, as I showed. And what about other values of n and t? Well, we don't know. This is an open question in design theory for many, many years, more than 100 years, so obviously we weren't able to completely solve it. We did say something which is new, which wasn't known by design theory. So for instance, by doing composition, we show that if t is a power of a prime and n is t to the power of 2 to the k, not only 2 squared, but t to the 2 to the k, for any k, then you can sort with the bound, the information theoretical bound, many comparators. This wasn't known, as far as I know. The proof for it is just by composition. We sort that many elements by using large comparators, and then we implement every large comparator by smaller comparators. And this shows that with our algorithmic approach, we can actually say something about mathematical design theory. So this is nice. Let me switch now to our randomized algorithm, t-sorting in 2 rounds. And maybe I should start by talking a little bit about t-quicksort, which was developed by Beigel and Gill in the 90s. And t-quicksort is just doing, it's a generalized quicksort where you have t comparators. Let me remind you how quicksort works. So in quicksort, you do the following. You randomly sample k elements. We call them pivots. And then you take all the elements and you split them, or you bucket them. We call them you bucket. So all the elements that are smaller than the first pivot are the first bucket. All the elements that are between the first pivot and the second pivot will be the second bucket, and so on. So split the elements into buckets. And now quick sort recurse. We take each bucket and quick sort them. Okay? And Beigel and Guild show that if you smartly choose K, you will get this number of comparators, which is asymptotically tight. This is what you are supposed to get. And the number of rounds will be log n to the base t. The problem is that this is not 2. We want sorting with 2 rounds. And even if you sort t square elements, so this should be log n divided by half log n, which should be 2, this doesn't give you 2. So we ran experiments and measured how many rounds, and in expectation we had around 4 rounds. So this almost never give you 2 rounds. We want 2 rounds of sorting. So our idea is the following. We are going to start similar to the quicksort. We are going to pick k elements, which are the pivots. We are going to split the n elements into buckets, but now we are not going to recurse. We are going to take every bucket and just deterministically sort it. How? For instance, using the deterministic sorting in 1 round that I showed you previously, the one that gets at most 3 times the lower bound, the information theoretical lower bound, many comparators. So we will be maybe factor of 3 of what we're supposed to be, but this will be asymptotically tight. Okay. And we showed that if you pick the right k, this depends on n and t and the relations between them, then we get the following. We get 2 rounds and the number of comparators, which is asymptotically tight by the lower bound of Alon and Nazar and other. It's not too difficult to see that this is the number of comparators that you get in expectation. You just, compute the expected number of the expected size of each bucket and sum it all, and you get this many comparators. But we wanted to show that this holds with high probability. And actually, the main bulk of our work is to do this analysis and show that this holds not only in expectation, but also with high probability. And this was quite difficult. I don't have a lot of... Can I steal one more minute? Yeah, okay. So maybe I'll try just to give you a hint of the analysis. We take all the elements and think about them as sorted. So every ball is an element and think of them as sorted. So this is the minimal and this is the maximal. And the the black ones will be the pivots, right? So we have buckets, and most of the buckets have the right size, the expected size, but some buckets are huge. It happens. We didn't pick any pivot here. This can happen. And how much do we pay? We pay for, in comparators, we pay the number of comparators we need to sort a bucket goes according to the square of the size of the bucket. Okay? So this is why the expected size of the bucket is not good enough to get concentration, because this is square of it. And the analysis of the size of the buckets it's highly non-trivial. So the size of buckets are dependent, are negatively correlated, and it's very, very difficult to get concentration bounds. What we do, we use this trick of deferred randomness. I guess many of you know the principle of deferred randomness. So we think about it this way. Here again, I have all the elements in a sorted way, but maybe not all the elements themselves, but maybe subsets of elements of some size. And here, the numbers that you see is the number of pivots. Or think about it. We think about it as balls and beans kind of scheme. So here I have a lot of balls, and each ball represents a pivot. Okay. So we start with all the balls here, and then every ball chooses you inform it whether to go right or left, and they reach, some subset. And if they reach a subset, then one of the elements in this subset will become the pivot. What we would like to have, that every subset will have a pivot, because then the size of the buckets will be small. But unfortunately, maybe the balls didn't go equally, like happens. So here everything is smooth; they go equally. But here we really had bad luck, and all the balls came here. And here we don't have any pivots. If we don't have any pivots, we have a lot of elements in one bucket. And this idea allows us to get concentration, because we can now get concentration on this tree layer by layer. In the upper layer, we have so many balls that everything is smooth with high probability. In the lower layer, this is not the case anymore, because we have very small amount of balls and they don't split smoothly. But then the cost of it is not large, because like if here all the balls came to this subset and not to this subset, I only pay 2 subsets. The bucket is of size 2 subsets, so I pay 4 times. So that's not a lot to pay, and with this way we get our concentration. Okay, let me conclude the talk. So we showed how to sort with 1 round and 2 rounds. We discussed the relation between N and T. Not all pairs of N and T are feasible. Using our algorithmic approach, we were able to show more values of N and T that are feasible. And maybe there are other algorithmic approaches that will allow to advance things that design theory weren't able to do so far. Even if we don't, maybe it's a good question, what is the overhead? So certain N and T, we cannot get this lower bound, this information theoretical lower bound, but how much more can we get? And for the randomized case, I showed you the case of 2 rounds and asymptotically tight number of comparators, but maybe we can increase it to 3 rounds and 4 rounds, and what is the trade-off between rounds and comparators and how to achieve it. I guess that's it.
Okay, thank you. Any questions? Quick questions? Yeah.
Thank you. So thank you for the talk. My question has to do with counting networks. There are some connections, right? Some sorting networks can count, counting networks, some of them can sort. So I was wondering, is there any... Are your results, do you believe that they might be relevant for the counting networks problem as well? And also vice versa, do you think that there might be results on the counting network that could be of interest to you?
It's interesting. I'm not really sure about counting networks, but at least for sorting networks, our model and sorting networks are kind of different. And I think this can be seen in this case. So in sorting network, every element goes exactly once to the network and is output exactly once it appears once in the output. And for our case, it's not the case. It's actually, it's crucial. This is not the case. You need to compare the same element with multiple other elements. So you must take the same element and input it to many comparators. So there are differences in these models. So I'm not sure. I don't know how to reduce between them.
Okay. Any other quick questions? Okay, then thank you. Okay, so for our last talk of the session, Ming Hang's going to tell us about agreement tasks in synchronous fault-prone networks.
Hello everyone, I'm Ming Hang Nguyen, and today I will talk about agreement tasks in synchronous fault-prone network. This joint work with Pierre Préignon and Ami Pat. So synchronous graph broad network is a classical model. We have n process communicate by a network by synchronous route. And at some point, a node may crash. When a node crashes, it stops sending message to some of its neighbor, and it never recover again. So the number of crashing nodes normally be upper bound by T. We study consensus problem, which is an input-output task. At the beginning, each node has an input 0 or 1, and at the end, all correct nodes need to output the same value, and the output value needs to be the input of some other node. We focus on analyzing oblivious algorithm in which every node broadcasts, and at the end, decision will be made based on the set of pair identifier and input. And the source of uncertainty comes from the input configuration and the failure pattern. So agreement task in this model has a long history. For a long time, people focus on the case when communication graph is a click and the route complexity is well understood. Recently, the study is extended to the case when communication graph is general. Castaneda et al. Give an oblivious algorithm to show consensus in radius of GT route. This is a new graph parameter which depending on graph G and the number of failure T. And in this work, our result is to prove a matching lower bound. That is, for every graph G, consensus in G cannot be shown in less than radius of GT route by an oblivious algorithm. And we need the condition that the T smaller than the connectivity of the graph so that the graph never be disconnected. To give you some idea about radius of GT, let's imagine we have n node Vi and many failure pattern phi. For each node Vi and failure pattern phi j, we compute the broadcast time. This can be infinity. And for each Vi, we can compute the maximum value for a row. And among maximum value, we compute the minimum one. And at the end, the radius of GT is the minimum over V of maximum over phi of the time we need to broadcast in phi. There are some open questions. The first one is to consider the non-oblivious consensus algorithms. And the second question is about the case-set agreement, which is a general problem. The question for case-set agreement and general graph is widely open. Thank you.
Okay, thank you. Any questions? Questions? Do you have any intuition for why case-set agreement is a lot harder here?
So the characterization theorem for consensus is based on the, let's say, path connectivity of what we call information flow graph. For case-set agreement, we don't have a similar characterization theorem, and maybe it will relate to higher connectivity.
Okay, thank you. Any other questions? Okay, then thank you, and that's it for the session.
Fine.
You last time whether the actual fire, the projector caught on fire in Orlando? The circuit breaker blowing is much better than than a fire starting.
a brief announcement. If any of you wants to do some work or take a phone call or something, there are rooms downstairs, so you can use one of them. Just please make sure that you use the room that is marked with disk, because people sort of spread around and the local venue people didn't like it. So there is like one room that is allocated specifically for this. It's downstairs in the basement where the workshops were, and it's marked. Okay, so that's it.
All right, thanks for that, and welcome everyone to this session on graph coloring and friends. Just one thing in case you didn't hear it right now. So if you want to use this mic, you can use this microphone if you want. But if you use this, I think it's good if you don't turn your head too much to the side, because then the sound might drop. Apart from that, I'm very happy to introduce the first speaker of the session. And as we all know, it's customary that the academically youngest person on the paper gives the talk. So I'm very happy to let Pierre take it away.
You cannot imagine the number of lies all these guys told me not to give the talk. I mean, this is amazing. So the hard question will be for them. Okay, so I will try to be as confusing as possible, so that you will have a lot of questions and make them really, you have to make them really bad. I mean, it's, okay, I don't even think I will list their name, because, or maybe just so that the hell, I mean, they will be welcome in hell. Okay, so there is Halkida somewhere here. Patrick is not in the room, lucky for him, at least he has a good excuse. Denis is also here, and Michael is hiding probably somewhere in the toilets. Okay. So we'll talk about asynchronous fault-tolerant distributed proper coloring of graph. And just let me start by presenting kind of two extremes models in distributed computing. And what we will try to do is to bridge these two models. So to start, on the one hand of the corner, in the one room, let's say, there is this asynchronous crash-prone model. So what does it mean? It means that you have a bunch of processes, and let's say they interact by shared memory to make it more extreme, the difference between the two models. And they do so by reading and writing in the memory. So each process has its own register, write in its register, and can read the entire memory by collecting all the data that are in the registers. So one important thing here is that this model is known to be equivalent if you provide the processes with an additional feature which is called snapshot, which means that instead of reading the registers of the other processes one by one, they can snapshot the entire shared memory at once in an atomic way, which means that snapshot can be implemented in rewrite. But let's think also that if you have this facility, each process can write in memory and do a snapshot, atomic snapshot of the entire memory. And this has to do with the other model. So the other model is the so-called local model. So it's in some sense, they differ in all aspects. So first of all, the processes are connected by a network. Second, they are fault-free, so no crash, no nothing. They behave perfectly well. And they behave synchronously. So all the computation is synchronous, goes by round. Each process, all the processes goes in a lockstep. They start at the same time, and at each round, each process can read can send the message to all its neighbors, receive the message from its neighbors, and perform some local computation. Which means, in some sense, you can already see that here. The fact that you send message to neighbors and receive messages from neighbors, you may also think as each node here can read in an atomic way, can read all the memory of the neighboring nodes. Okay, so it's the same thing essentially. So, but nevertheless, they are quite different. And not only that, but the type of problem that people study, consensus, symmetry breaking, renaming in the shared memory asynchronous crash-prone system seems to differ a lot for the type of problem that are mostly graph problems that are studied on the local model, coloring, maximal independent set, matching, all kind of problems, LCL problem in general. Yet, if you think about it, these problems are not that different, in fact. If you think about this shared memory system as, in fact, which is also known as a message passing system, in which you have the processes that are connected as a click and they exchange messages along the link of this click. So there is a link for each pair of processes. Then, in fact, a problem like renaming. So renaming is essentially the processes start like here with a bunch of names from a large range of names, and they want to rename themselves in a small set with a small set of names with as few names as possible. And in fact, this is essentially like coloring. I mean, this is really people from graph theory will say immediately, okay, that's the proper coloring of the click. You want to do K renaming, which is you want to do K coloring of the click Kn. So the question is, how many colors do you need? That's the problem of renaming. How few you want to use as few colors as possible. If you think about symmetry, you're so quiet. I mean, it's amazing. I mean, you all sleep. Or if you think also about symmetry breaking, all these problems like maximal independent set, think about maximal independent set. Maximal independent set in the click, you will have one guy that will be in the set. There must be one and only one. So it's like linear election, a problem which is studied quite a lot in the other model. So these problems are actually not that different if you think about the problem on the left as a click. Okay, so this motivated the work that we did with Patrick and Michael last year at DISC, where we defined the version of the local model which we call async local, for asynchronous local model. So essentially we start from the local model. I mean, for those who are familiar with this model, again, a bunch of processes that are connected as a graph. Each process has an ID, which is usually taken from a polynomial range of identifiers. And all the nodes run the same algorithm. In the local model, of course, they run, as I said, in lockstep. They all start at the same time. So, and also they exchange messages. Here, as I said, the computational model, you can see it a little bit differently. It's the same as the local model so far on this slide. I mean, each process will write in its local memory. Let's say it has a local register, will snapshot the neighbor's registers, and will perform some individual computation. That's exactly the same as the local model. Now, when you want to do the asynchronous version of this model, what do you say? You just say the same thing, except that now computation works asynchronously. There is no more rounds. I mean, no more notion of global rounds. But all the processes will repeat this sequence of instructions right in your memory, snapshot the neighbor's memory and perform some computation, some local computation. They will repeat, they will loop, and they will repeat this sequence of instruction until they decide some output value. But they do it in an asynchronous way. That's the only difference, okay? And what we will be interested in, since we are interested in a model in which there are crashes, we are interested in the design of so-called weight-free algorithm. So for those who are not familiar with this terminology, weight-free simply means that you want an algorithm that tolerates an arbitrarily large number of failures. Actually, all the processes but you may fail. And still you must terminate in this case. So it means you are weight-free, if in some sense you don't wait for any other processes to decide your output. You decide whatever happened to the other guys. So of course, if you have the chance to communicate with other guys, you will learn more information and may decide something different, but you should be able to terminate whatever happened. So weight-free algorithm, this is why in this type of algorithm, there is never something like, okay, do this, I read, I write, and I wait until my neighbor writes something. No, you cannot wait your neighbor write something because your neighbor may have crashed and it will never write anything in its memory. So you cannot wait for it. So that's the point of weight-free algorithm. That's algorithm that tolerate an arbitrarily large number of failures. All right, so that's for the model that we introduced. And let's say a little bit of a direct consequence of the state of the art in the two models that I introduced before, and we'll see the consequence on the async local model. So the first theorem I want to mention is a theorem by Armando and Sergio, and who showed a lower bound on the number of colors you need for doing an asynchronous coloring, proper coloring of the click, which is actually renaming in the terminology of shared memory mode, asynchronous shared memory computing. So the theorem says that for any value of n, any number of processes, which should be a power of a prime, that's important here, number of processes with power of a prime, and for every k renaming, which means coloring, proper coloring with k colors, k renamings in n-process asynchronous crash-prone system is weight-free solvable, if and only if k should be at least 2n minus 1, which means that you cannot, the chromatic number of the click is n, but you cannot do with n, you cannot do even with like delta plus 1 coloring, that's a typical thing we do in the local model. Here you must use more, you must use 2n minus 1 colors. Okay, another theorem from the other side is this celebrated lower bound by Lineal, who says that if you want to do proper coloring, tree-coloring of the ring, of the cycle, Cn, of the n-node cycle Cn, you need to perform, you cannot do it in a constant number of rounds, you need to perform at least log star n rounds in the synchronous local model. So log star n is the number of times you must iterate the log function so that it go from n to below 1, or below constant. So let's say the consequences. So the first consequences is that if you want to do proper delta plus 1 coloring and n-node graph of maximum degree at most delta, then in the synchronous local, it would require at least log star n rounds. So in the asynchronous local model, it would also require this many rounds. So what do I mean by round in the asynchronous version is the number of time each process does this write in memory, snapshot the memory of the neighbors. So it's not synchronous, but you can count the number of rounds performed by each process, and this number says that at least one process should perform this many rounds. Another consequences is that if you want to do k-coloring, I mean the classical model that people use that people study in the local model, if you want to do proper k-coloring, and n-node graph of maximum degree delta, it will be doable weight-free in async local, if and only if k must be at least delta plus 1, 2 delta plus 1. Why is this? It's because think about the click of delta plus 1 node will be actually a graph of maximum degree delta, and we know from the first theorem that you cannot do with more than 2n minus 1, and here the number of nodes will be delta plus 1, so here you got the result. So it means that it's really strange compared to the local model. You cannot do delta plus 1 coloring. You must do at least 2 delta plus 1 coloring. Below 2 delta plus 1, it's not possible. Okay, so let's look at our result. We have a bunch of results regarding upper bounds. So first upper bound is that the famous lineal algorithm, not the lower bound, the lineal algorithm, this O of delta square coloring algorithm that lineal designed to do in the local model. You can do delta square coloring, any graph of maximum degree delta, in the async local in O of log star n rounds. So the same result as was established by lineal actually holds in the asynchronous world, essentially because, I mean, the algorithm of lineal works in the asynchronous world. You can make, I mean, there are tiny small details, but essentially the idea is that it works the same way. So that's the good news. We can do delta square coloring easily. Now the issue is how to go below delta square. In the synchronous, it's easy. You can do recoloring, and it will cost you a certain number of colors, maybe delta square, or less actually. We have better result than that. But it's easy to decrease the number of colors once you get a delta square coloring. In the asynchronous world, it's a completely different matter, and you cannot do that. You cannot have this type of strategy. All the nodes of degree delta square will look at their neighbors and choose the smallest color, which is between 1 and delta plus 1. No, because all these guys of color delta square, they may be slow, they will not do, so they are not working synchronously. So it's a complete mess, and you have to do something which is completely different. So, but nevertheless, we succeeded to design an algorithm that will compute a delta plus 1 times delta plus 2 over 2 coloring. And for this, we need to pay additionally to the log star n rounds, we need to pay an additional number of rounds, which is proportional to delta only. It's a huge function, but proportional to delta. So far, so good. But what we wanted is to gain one more. Why one more? It's because if you take delta equal 2, delta plus 1 times delta plus 2 will be 3 times 4 will be 12, divided by 2 will be 6. We get a 6 coloring. But the lower bound for the ring is 5. So can we do it with 5? And we claimed erroneously last year that we could do it with 5. Actually, there was a bug. It was only up to 6. So, in fact, we had to work harder. And we were able to design a general scheme, a general algorithm that save one color. Here, I mean, these two theorems 2 and 3 are exactly the same. It's just that we save one color, and it was not easy to do this. The function f is not the same. I mean, I could use f, but it's different function. But still, we can do it with one less colors. And as the corollary of this later result is that the round complexity of 5 coloring the n-node cycle in the async local models is log star n. So good, this time we have a solid result that we have 5 coloring of the n-node cycle. 5 is the smallest because the lower bound is 2 delta plus 1, and we cannot do less than 2 delta plus 1, and because of this lower bound I mentioned on renaming, so that's the best you can do. So in terms of lower bounds, we essentially obtain lower bound by reducing, by revisiting a result by Atiyah and Paz, who showed an impossibility result about weak symmetry breaking. And they show that for a prime power, for any n which is a prime power, there are no symmetric weight-free deterministic algorithms solving weak symmetry breaking in asynchronous shared memory model with n processes. And we essentially revisit this result to obtain, you see, when you want to apply this, the question is that if you think about you are in a cycle. In a cycle, you're not anymore in the shared memory model. This cycle is breaking symmetry by itself somehow. So the way the nodes are ordered in the cycle breaks the symmetry. So this, we have to revisit the model and the theorem, and with few additional constraints. So essentially, these two things that I added, non-prime divisible things, is just that it fits with the model that we have a graph that connects. So several corollaries. Proper 4 coloring is n-node cycle is impossible. Weak 2 coloring n-node cycle is impossible. In general, proper delta plus 1 coloring is also, of delta regular graph is also impossible. And we have a bunch of other results regarding MIS and also delta plus 1 coloring in trees. Let me conclude by essentially one open problem, which is okay. So if you look at our result, below, so here it's about coloring. Using less than 2 delta plus 1 colors in a graph of maximum degree delta, it's impossible because of the lower bound for renaming. We have a result that shows that delta plus 1, delta plus 2 over 2 is possible. Actually, delta plus 1 times delta plus 2 over 2 divided minus 1 is possible. Now the question is between the two, we don't know. So of course, if delta equal 2, there is no difference. These two bounds are the same. But for larger delta, there is a huge gap between essentially delta square and something linear in delta. So here we have no clue. And I think that this is really something like it's a nice playground for people both from the side of asynchronous failure-prone systems and, let's say, the local model. That's a very nice playground because you can take ideas from both communities. And of course, I mean, basic things, can we do something in using randomization? Here, all our algorithms are deterministic. Can you gain something if you care about randomized algorithm? And with this, I thank you very much.
Thanks a lot, Pierre. So do we have questions?
So regarding randomness, does the lower bound that you have hold for randomized?
Good question. Where is Sergio? So renaming, randomized algorithm for renaming. What do we know? Randomized, you can do exact renaming, so it gives hope. Sergio, I'm very disappointed that you didn't.
We really don't have any lower bounds in the randomized setting.
Apparently, this is what it means.
And what's your guess for your question about between delta and beta square?
Wow, honestly, I have no clue. And the fact that the two bounds coincide for the ring may say that maybe you cannot in some sense. I mean, but so okay, so I don't know. Honestly, I don't know. I wouldn't bet any. I have no clue. The only thing I know is that to save one, it was really, we needed a complete different ideas. There was really something additional that we have to do compared to this delta plus 1, delta plus 2 over 2 algorithm. It was heavy and it was but it doesn't mean anything. It may be because we didn't find something simpler and maybe we can save 2.
Maybe the exact formula is complicated, but the asymptotic, it's like the order of
I don't know.
Delta log delta or whatever.
Yeah.
You have no.
No. We have no. I don't know if my co-authors would like to say something, but.
So maybe we can have the next speaker already setting up. But if there's another question that someone would like to ask, like maybe as a last question, like from this whole body of literature that we have on, say, the distributed graph algorithm side, do you see any other things that might be possible to translate to the setting? Okay,
so the problem is that once you do asynchrony with failures, even just crash failures, many problems becomes impossible. So renaming is nice because there is an impossibility result, but it's about the number of names, so like in coloring. But then when we want to do MIS, the variant of MIS in this setting is impossible to solve it. So it seems that there are many problems that we cannot solve. Now, we didn't thought at all about edge coloring. That's coloring again, it will depend on the number of colors. So edge coloring might be an option. But all these problems that kind of symmetry breaking problems, since they are in general impossible in asynchronous world with crash failures, it's not very promising. But yeah, everything which is related to coloring, whatever is a variant, although weak coloring is also difficult, that would be maybe the type of problem.
Lover's local lemma, something like that?
Might be because it has a flavor of coloring. So indeed, yeah.
Okay, so let's thank Pierre. And our next speaker is Asaf, and he will tell us about connectivity labeling in faulty colored graphs.
Yeah, so hi, I'm Asaf, and this is a joint work with Shai Sapir and Elad Tzadik, who are PhD students in the Weizmann Institute, as am I. So in this work, let me start with the background. In this work, we considered informative labeling schemes, which are distributed graph data structures in the form of nodes that are assigned to the elements of the given network or a graph. And these labels are assigned to the nodes or the edges of the graph in such a way that we can answer queries of interest by merely inspecting the labels of the elements that are involved in the query. So say we want to query something about vertices 2 and 11 here, like whether they're adjacent in the graph or whether they're connected or what's the distance between them, depending on the specific problem that we're working on. And we should be able to do so by just looking at the labels of these two nodes and not knowing anything else about the graph. And the point is to make the labels as short as possible in terms of the number of bits in them. So what's short? Well, if we're allowed to store n squared bits, then we can just store the entire graph. And then, of course, we can answer every query that we want because we have all the information in the graph. And on the other extreme, if we just want to be able to specify the elements that are being queried, well, we need roughly log n bits for that. So this is like the ideal length that we're striving for. And a bit more formally, a labeling scheme consists of two algorithms. A labeling algorithm that gets as input the graph G and outputs the labels for the elements of this graph. And a query algorithm, which gets labels of queried elements and should output some information of interest depending on the specific problem regarding these elements in the graph G. But the point is that the query algorithm doesn't know G. It only gets the labels to look at and to learn from. And the specific problem that we will discuss is called fault-tolerant connectivity labeling. So here the setting is that we think of the elements of G as possibly crashing, but there could be up to at most F failures at a given time. So the queries we are interested in are of the following form. Given the labels of two vertices U and V, and of at most F faulty elements, x1 up to xf, we should report if U and V are connected in the graph when we remove the failures. So for example, in the picture here, we see that if we remove the red nodes, then U and V become disconnected, so this query should be answered disconnected. And there are two classical models of faults, one where you have faulty edges, and another one where you have faulty vertices. So this notion is also known as forbidden set labeling, and it's commonly applied to get a compact forbidden set routing scheme that allow passing messages in a distributed network from a source to a target while avoiding forbidden or faulty elements in the network. And there has been a lot of works on this kind of labeling on special graph families, like planar graphs or bounded tree-width graphs. But only recently, there have been several works that actually consider the case where G could be any general graph. And this is what we'll discuss in this talk. So here are the state-of-the-art bounds, which are already expired by a new work that is to appear in SODA 25. So this is almost updated. And I don't want to get into all these bounds, but the key point is that by now, we know that either with vertex or edge faults, if we have f of them, then we need labels of poly f log n bits, which is relatively short and quite a satisfying answer. So we can think about this problem as somewhat well understood by these recent works. And now we get to our work. So in our work, we considered a new model of faults, which was introduced by a previous work of ours, called the color faults model. So in this model, the input graph G also comes with some arbitrary coloring of its vertices or its edges. And for now, we'll stick with coloring vertices, although everything works as well if we have colored edges. And this is not a proper coloring. It's not a legal coloring. It could be any coloring that you want. So neighboring nodes can share a color. And the type of faults that we have are color faults. So what is a color fault? If the color blue fails, then all the nodes of this color crash. And this is the resulting graph that we get. And this model is motivated by something from more practically oriented engineering network called shared risk resource groups, where you have communication networks where some components of the network depend on some shared resource, and this resource might fail and crash all of them. So these colors represent these resources that are at risk and might crash. And we think about them as like extra elements in the network. So given this new model, we introduced this new definition of color fault-tolerant connectivity labeling. So here the labeling algorithm is given as input the graph G along with this coloring as part of the input and this parameter F, and should give labels to the vertices and to the colors in the graph. Think about as these resources, these elements. And the type of queries that we would like to answer is as follows. Given the labels of two vertices U and V and of at most F faulty colors, C1 up to CF, we want to understand if U and V are connected in G minus these faulty colors. So let's see an example where this parameter small f is equal to 1. If we have this network and these are U and V, and we get the faulty color blue, then we see that when we remove this color, then U and V get disconnected, so we should answer disconnected. But if instead we got the color green, then U and V actually remain connected, so we should answer connected. And let me just mention that this generalizes the previous model of a vertex fault, say, because the coloring could be such that every vertex gets its own unique color, and then you get back the previous model. So this is our new version. And the obvious challenge when you have color faults is that even one failing color can cause a lot of individual crashes in the network. So a brute force approach would be to just treat color faults as many individual faults. So if you go down this brute force route, you can use the state-of-the-art labels that you know for individual faults and apply them in order to get labels for color faults. That would also work. But the problem with this approach is that the number of what we'll do is you label a color with all the labels of all the edges that are crashed by this color. So that would work, but it will give you labels which are very large because we have no restriction on the coloring, and the color can cause lots of crashes in the graph. So can we do better than that? And our results show that indeed we can. So we mainly focused on the case of one failing color, and we showed an upper bound of roughly square root 10 bits for the labels. And we showed that this is not only worst case optimal, but also our scheme is universally optimal in a sense that I'll explain later in the talk via this new graph parameter that we call the ball packing number of the graph. So this will be introduced later. And we show how we can use this approach also to get a routing scheme for avoiding a forbidden color, and also showed some centralized results, centralized data structure oracle of the problem. And we also have other results for more colors, for F failing colors, where we have generalization of the upper bound and the lower bound, but these are not tight. So here we still have some gaps, and we have some extra results, so you're welcome to check out the paper. And for the rest of the talk, I'll just focus on the labeling results for one failing color. So let's start with the labeling algorithm. So here's the graph G, the color graph G that we get. And we start with this funny procedure that works as follows. We choose an arbitrary vertex, A0. So let's say this is A0. And then we proceed in iterations, where in iteration I, we choose a vertex whose distance from the previously chosen vertices is exactly I. So here are all the vertices of distance exactly 1 from A0. We choose one of them as A1. And then we proceed to the second iteration. Here are all the vertices of distance exactly 2 from A0 and A1. We choose one of them as A2. And proceed to the third iteration. Now we're looking at distance 3. These are the candidates. We choose one of them as A3. And continue. And now we're in iteration 4. We chose A4. And actually now we get stuck, because there is no vertex of distance 5 from the set of previously chosen vertices. So at that point, we halt. We call k the number of iterations that it took us to halt, which is also the size of the set of chosen vertices. And this concludes this pre-processing procedure. And observe that by the halting criteria, every vertex has distance at most k to the set of chosen vertices. We'll use this notation P of V to denote the shortest path from the vertex V to the set of chosen vertices. Now we can show how the labels work. So we'll need this notion of connected component IDs, which are, as they sound, identify the connected components. So two nodes have the same connected component ID with respect to a subgraph, if and only if they are connected in this subgraph. And what we'll do is for a vertex, we'll store its path PV along with a component ID for every color that might fail on this path. So the component ID of V with respect to G minus C for every color C that appears on V's path. And for the label of a color, we'll store the set A and the component IDs of every small AI in A when this color fails. So these are the labels. That's it. And the bit length is obviously K, roughly K log n, because the component ID takes log n bits. And the set A has size K, so this is for the labels of the colors. And these paths have length at most K. So we get this bit length. And we'll analyze K in a bit. But for now, let's see how we can use these labels that we define in order to answer queries. So this is what we want to do. Given the labels of U, V, and color C, we want to decide if U and V are connected in G minus C. And it's enough for us to show that we can actually extract the component IDs of V and of U in G minus C. So let's do that for V. And so recall that we have this path PV that connects V to some vertex in the set of chosen vertices AI. And if the color C appears on this path, then we actually have the answer stored in the label of V. Exactly how we define the label of V. So in this case, we're done. But in the remaining case, we know that this path is intact in this graph G minus C. It is not affected by the failure of C. And therefore, V and AI have the same component ID in G minus C. But this component ID of AI is stored in the label of C. So therefore, we can also, in this case, extract this component ID, and we're done. So this shows that we can answer queries. And it remains to analyze the number of iterations. Well, for this, we'll use this lemma that says that the graph G contains roughly k disjoint balls of radius roughly k. And why is that? Well, we can look at the last k over 2 vertices that we've chosen into A. They all have pairwise distances which are roughly k, and therefore you can have these disjoint balls centered at them. And this immediately implies that k must be of the order of at most root n, and therefore the label length, we get the label length that we claim. And now we can ask whether this weird scheme is tight, or whether we can improve it in some special graphs, like planar graphs and so on. And to answer this question, we introduce this new graph parameter, which we call the ball packing number of the graph. And it's inspired by the previous lemma. So the ball packing number is the maximum radius r, such that G contains r disjoint balls of radius r. R is both the radius and the number of balls. And by this previous lemma, we see that k is at most the ball packing number of the graph, and therefore we get label length, which is proportional to the ball packing number of the graph. So a few notes on this ball packing number. It's always at most root n, obviously, by the same argument from before. But in many cases, it could be much smaller than root n. For example, it's always at most the diameter, and many times we think of the diameter as much smaller than root n. And in general, I want to note that it's a parameter that depends on the graph topology, but not on the specific coloring that the graph G came with. So it depends on the uncolored version of the graph. And this leads us to this universal optimality result that says the following. If we have a graph topology G, meaning an uncolored graph G, whose ball packing number is R, then any scheme that would work even only for colorings of this specific topology must use bits of labels of omega R bits. Okay, so this means, in other words, that you need omega of ball packing number bits even if you are allowed to store the uncolored topology for free in each and every label. It would not help you, you would still need ball packing number of bits. And it means that our scheme is optimal up to the log n factor, no matter if you are focused on any special graph family, because it's optimal for any specific topology. Okay, so you could not improve, say, on planar graphs. This scheme is the best you can do. And let me just quickly outline the proof of this universal optimality result. So it's by a reduction to a communication complexity problem where you have two parties, Alice and Bob. Alice gets R squared bits arranged in a matrix, and Bob gets a location in the matrix. And the goal for Bob is to learn the bit that is found in this location. But Alice can, the only way they can communicate is that Alice can send one message to Bob. That's it. And we will assume that both of them know this topology, uncolored topology G. This is basically part of the protocol that they run. Okay, so they know the topology, and they know these R disjoint balls of radius R with centers VI, and these UIs are vertices on the shells of the balls. Okay, that we choose arbitrarily on each ball. We choose one vertex on the shell. So a known fact is that essentially Alice has to send all the bits in order to solve the problem. So she must send R squared bits. What we will do is we will show a protocol that where Alice colors the graph and sends labels of colors and of some vertices to Bob. And because this protocol works, it would mean that the labels that she sent must be relatively large. So what Alice does is she privately colors this graph G, where the ith row in the matrix corresponds to how she colors the ith ball in this ball packing definition, the balls from the ball packing definition. So essentially, we'll use R different colors, one for each layer, and we either color it by this color if the bit is 1, or we leave it with a default color if the bit is 0 in this location. And then after Alice colors the graph, she just sends the labels of these centers, the vertices on the shells, and of the R colors that she used. So these are 3 R labels. And one can see that Bob can essentially recover the bit by performing a query using the labels that Alice sent. So if he is interested in the I star row in the jth location, he will query the vertices from the I star ball with the jth star color. And because M has 3 R labels and at least R squared bits, some label must have at least R bits. So just to wrap up, the key takeaway is that even though only few color faults may cause lots of crashes, we can explore the fact that we know that the crashes will be correlated because we know the coloring when we get the graph in order to get better solutions than just treating it as tons of faults. And we have some gaps for f equals 2, which I listed here, which are interesting open problems for future work. So thank you very much.
Thanks, Asaf. So do we have questions?
If you would consider a specific set of colorings, not arbitrary, can you maybe improve the results?
Yeah, so probably like if you a natural parameter would be say the maximum number, the maximum size of the color class. So if you parameterize on that, at some point you'll get that using the brute force approach is better. Just treating it as like if you know that each color appears not so many times, then essentially you can treat it as just this number of faults, which is not so big, so you can use the brute force approach, and it could beat our approach. So for example, we showed that root n is needed, but if you have color classes which are smaller than root n, then you can do better. Okay, so this is like a natural thing that I suggest you could parameterize on, and in fact, we have some works on other stuff in this model where we show that you must parameterize in some sense this delta, the size of color classes.
But if you consider so you limit yourself to colorings.
Proper coloring. So I think I'm not sure if in this case it would matter, but in some cases like it does. I'm not sure about specifically these labeling problems that I introduced, but I know of other problems where I think like not specifically in labeling, but in spanner-related applications and so on, where I think it would make a difference also. Yeah.
Okay, thanks.
Maybe we can already have the next speaker set up while we have more questions, if there are any. So this universal optimality that you get, does it come specifically from the fact that you now look at the colored setting? Like, does some of these things also transfer to the uncolored setting, or is it open there?
I think the name universal optimality is kind of like, it's usually used for when the topology is fixed, but the weights are changed, right? And so now we like used it for the fact where the topology is fixed and the coloring is changing. So this is why we call it like universal optimality.
I see. So the concept itself doesn't exist in the other case because you fix the topology and then there's like nothing that in the other setting like makes sense definition-wise.
Yeah, if I understood your question correctly.
Yes. Okay, thanks. So let's thank the speaker again. So our next speaker is Yassine, and he will tell us about distributed maximum flow in planar graphs.
Hi. Yeah, so this is a joint work with my supervisor Michal Dori, Meraf Barster, and my supervisor Oren Palma. Our main result is the first distributed ordered poly-D round algorithm for maximum flow in planar graphs. We work in the congest model. We consider only planar graphs. And as usual, n denotes the number of vertices and d the hub diameter of the graph. So our focus would be the maximum ST flow problem. We're given a directed graph, G with edge capacities and two vertices S and T. We need to compute the maximum flow that can be pushed from S to T. We also consider another problem of undirected weighted girth. We're given an undirected graph G. With edge weights, we want to compute the shortest weighted cycle. So in terms of results for the maximum ST flow problem, we have an exact algorithm that works for directed networks with OTIL D squared rounds. If we relax the problem to approximation on undirected graphs and S and T lie on the same face, we can improve to D times N to the little of 1 rounds. And prior to this work, only omega root N round algorithms were known, even for approximation. So this is for maximum steep flow. For the undirected weighted graph, we get near optimal OTIL D rounds. D is a universal lower bound, so in all of these global problems, you can do better than D. Okay, so the general approach we take is to exploit planar duality. So for each planar graph, there's a dual, where for each face, we have a dual node. And for each primal edge, we have a corresponding dual edge that connects the nodes corresponding to faces on each side of that edge, in red here. So the blue is the primal graph, the red is the dual graph. And so we use these black box reductions in order to get our results. So dual distances in the dual give primal flow, and cuts in the dual give primal cuts. Primal cycles. So these are the dualities that we use. So we need to perform computations on the dual graph. But this has its challenges, because the dual is not the communication network, so any computation on it should be simulated. And its hub diameter might be a lot larger than the primal. And the diameter is a complexity measure. So that's also a problem. We overcome these challenges via 2 main tools. The first is the dual recursive decomposition, where we decompose the dual network into smaller subgraphs. And another is an implementation for a recent computation model called the minor aggregation model. So these tools existed already for the primal graph and for planar graphs specifically. And we extend them to work fully on the dual. So the main tool is the dual recursive decomposition, which gives dual distance labeling, which gives then an exact dual single source shortest path algorithm, which gives the exact primal maximum ST flow by duality. And if we use an approximate dual single source shortest path algorithm as a black box with all implementation of that model of computation, we get the approximate result of flow. And if we use a minimum cut algorithm with that implementation of the minor aggregation model, we get the undirected weighted graph. And that's it. Thank you.
Well, we already have the next speaker setting up, Yannick. Let's maybe have a quick question.
So the assumption that you have a planar graph, so is it given in any way? Like, do you have do you assume anything that you are given some hints that proves that it is a planar graph, like an embedding or the location of the faces, or do you have to compute all of that?
So it's like a promise problem where you get a planar graph, but we don't have any another assumption. So there's a black box algorithm that we use to compute an embedding, and then from there, like, we start our computation.
All right, so let's thank the speaker again. And as the next speaker, we have Yannick, and he will tell us about delta coloring under bandwidth limitations.
Okay, yes, thank you very much. So this is joint work with Magnus, and this is a classic paper in the congest model. So what we have here is this communication network, and we have congest communication. So we have small messages that we send through the edges of the graph in discrete synchronous rounds, and we have local computations, and we also do allow randomization here. So this is a randomized paper. at the end, every node should output its own part of the solution, so it's color. What is the? Do you also hear this interference? But I'm muted. Is someone else not muted, maybe? Okay. Okay, so the problem that we're looking at here is classic graph coloring. And if you've seen many of the talks here at the conference, classically what people look like at here is this classic delta plus 1 graph coloring problem, where delta is the maximum degree of the graph. Yeah. This is sequentially a very easy problem. You can just iterate through the colors in an arbitrary order and always pick a free color for a node, because at most delta colors are blocked by already colored neighbors. So you can never get stuck. This is really a greedy type problem. Today, this is not the problem that we're going to look at. Instead, we're going to color with one color less, which pretty much puts this problem into a very different regime. But fortunately, what we do know from Brooks' theorem, that still any connected graph that is neither a click nor an odd cycle does have a delta coloring. So what's the starting point of this paper? So the starting point is best understood by looking at what is known about these two problems in comparison. So what we do know is that for delta plus 1 coloring, we have this famous linear lower bound. And for delta coloring, we have a much larger lower bound, which is basically log n here. But then we've seen a lot of progress here on general graph colorings for delta plus 1 coloring, basically now bringing the randomized complexity for this problem really down. We now have sublogarithmic algorithm for this problem, essentially polylog log n, and this also holds in the congest model. For delta coloring, what we do have, we had some early works which basically solved this randomized in polylog n time, and then recent works from 23, or basically it's a combination of both of these papers here. Okay, seems like this doesn't work. Combination of both of these papers give a sublogarithmic time algorithm for the problem in the local model. But in congest, there was essentially nothing known for this non-greedy type problem. And the goal of this paper is to devise a sublogarithmic time randomized algorithm in the congest model for this delta coloring. So just looking at these headings, delta plus 1 colors, delta colors, one really wonders why should one care about the single color of difference. But I already hinted that these are very different problems, in particular from a distributed perspective. If you want to have a really fast algorithm, a distributed algorithm, what you want is you want to color many nodes in parallel. You want to have a lot of parallelism. So you want to somehow compute partial solutions and then later complete them. And that's what actually most of the delta plus 1 coloring algorithms also do. For delta coloring, this does not just work in a naive manner. It may be that you color two nodes that are far in the graph, and if you do this in a stupid manner, then you cannot complete this in the end. So basically, one of the main motivations to study this delta coloring problem is because it's an easy to state problem, but which really requires to develop new techniques and gives a new view on what can we do in a distributed setting. One can also make this a little bit more formal, because what you see down here is maybe a picture that many of you know. This is the complexity theory of so-called locally checkable labeling problems, or just think of them as local constraint satisfaction problems. And essentially, what you see here with the question mark, there's one regime in that complexity landscape that we really do not understand well. The delta coloring problem is essentially the only problem that we really know whose current state-of-the-art complexity lies exactly in this regime. So this is also one motivation why we want to understand this problem better. This paper doesn't really contribute anything to this specific picture here, because this is for bounded delta and constant delta degree. We're going to be more interested in proving it for all delta, and really the challenging part in our work is actually getting it to work for large deltas or intermediate range delta. So our main result here is actually a randomized algorithm to color with delta colors in sublogarithmic time, namely in polylog log n rounds in the congest model with high probability. And if I really want to summarize our solution in one single line, what we do is we produce slack. So what is slack? Slack can come in different forms. So for example, it can come in the form of a small degree node. So with this small degree node here, you can never get stuck in coloring. Regardless of how you color its white neighbors here, you can always complete the coloring at this node because it simply has at most delta minus 1 colors already blocked from its uncolored neighbors, so you'd never get stuck. So essentially, if there's a small degree node in the graph somewhere, you're back in this greedy regime. Another trick that we use frequently, how you can get back into the greedy regime, is by stalling some nodes to be colored in a later step of the algorithm. So these are the shaded nodes here. These are processed later in the algorithm, which essentially means now the node in the middle, this V node, does have slack. Now, regardless of how you color these white nodes around, you can always complete the coloring at V because it gets a lot of freedom by some neighbors that are colored. And then the most important part of slack, and this is what I really mean by produce slack, is what I will talk more about later, is if we really create this permanent slack by just coloring two neighbors of V with the same color. Now it has only lost one color, but two competing neighbors, which essentially again means at V you cannot get stuck in a greedy coloring. And essentially what's known from prior work is that if you're in this greedy situation, all nodes that do have slack, they can be colored efficiently with prior work. So once we have produced slack, the problem is easy and essentially we can solve it with prior work. So the main difficulty is how can we ensure that we have one type of these slack parts here at every node in the network. And this is what we're going to do. So to understand the high-level structure of our algorithm, this works as most of the recent randomized graph coloring algorithms. We're going to use the concept of click decompositions or almost click decompositions. So we decompose the graph into sparse nodes and so-called almost clicks. So these almost clicks could either be clicks with just some few edges going out, or really almost clicks with an edge missing. But yeah, the challenge is that they can also appear next to each other, and there are lots of connections, so we cannot just treat them independently. And with that definition, we can essentially already write down the high-level view of our algorithm. So what we do is we compute a fine-grained almost click decomposition, where we classify these almost clicks according to very many different parts, depending on their structure and how they interact with their surroundings. And then we have a few phases afterwards. First, we color these sparse nodes and the ordinary clicks. These are the ones in the top left. Then the nice almost clicks. These are the ones with an edge missing. And at the end, we color the difficult clicks, and the difficult clicks are further partitioned into many different levels. And the property that you have here is that an almost click in a lower level has neighbors in a higher level that are processed. As you see, there's a for loop here. They are processed at a later step of the algorithm, which gives slack to the prior almost click. And that way we can always color all of these. Of course, this does not work for the last level of difficult clicks. With these, we proceed differently. But yeah, if you are interested in how we proceed with these, come to me after the talk. Instead, I want to now talk a bit more in detail about this step here, because this was by far the most challenging part of this paper, and this took us quite a long time to actually get this to work. And this is how we actually color these ordinary clicks. These are the clicks that really, it's best to think of these really as a click on delta nodes. So delta, which still allows delta coloring, and everyone has just a single outgoing edge to the rest of the graph. This is really the most challenging part of our algorithm. So let's look at the situation a bit more detailed. What can we do here? We want to find a randomized algorithm, and the easiest randomized algorithm that we can think of is the simple randomized color trial. Every node activates itself with a constant probability, picks a random color, sends it to the neighbors, receives the candidate colors of the neighbors, and you keep this color if there's no conflict. Otherwise, you discard it. And what we did here is we analyzed this algorithm on this specific instance here on this graph. So what happens with the constant probability is that actually this green node, and now I'm just fixing at one of these pairs, looking at one of these pairs, what happens with the constant probability here is that this green node gets colored with the color C, and actually one of the non-neighbors, so these red nodes here, they're not neighbors of the green nodes, they're not neighbors, also gets colored with the same color C. So one can show that this happens with a constant probability, and what you get then is actually that the node with a smiley here, it does get this permanent slack because it now has two neighbors, right? It's connected to this node and it's connected to this node. It has two neighbors with the same color, which gives it permanent slack, which then is a toehold for the click, and afterwards we can color everyone else in the click because this node has slack. So once we find one node with slack in the click, the problem is actually easy. Unfortunately, right, we cannot just select one of these single pairs here, and constant probability of success is not enough. But instead, we have many of these possibilities, and I didn't even draw all of them in here, right? You have way more, but what one can show, there are lots of dependencies to deal with, but one can show that the probability to get permanent slack for such a click is exponentially small in delta. So this essentially tells you that if delta is large, so if it's logarithmic or larger, this works with high probability. But if delta is smaller than log n, this does not work with high probability. You have lots of places in the graph where this fails to produce slack. And this is really where the main part of the paper starts. How can we still produce slack in these parts where we don't have this local high probability guarantee? And for the people who have worked with such a situation, the natural tool that one should use here already to show existence is so-called Lover's local lemma. What we do here is we introduce a bad event for each such click that holds if the click doesn't get slack. And we have a random variable for each activation status of the nodes, for each color choice of the nodes. And what you then see, what the lemma from the previous slide said, the probability that the bad event holds is exponentially small in delta. And there's just some mild dependence between different bad events, because whether some almost click here gets slack doesn't depend on whether an almost click that is very far apart from that gets clicked. There's only you only depend on the randomness in a constant top neighborhood around yourself. So this basically tells you that via Lover's local lemma, at least existentially, one can prove there are choices of these random variables of this algorithm that avoids all the bad assignments. But of course, we also want to compute them. So we want to see which LLL algorithms can we take. The classic one, for example, Mozart-Tardosh, are way too slow. They have logarithmic time. Then there are a lot of other LLL algorithms. Most of them just work in local. But even if they would work in congest, none of them is actually sufficient, of these is sufficient for our need. Mostly because, for example, the first one has a runtime which is polynomial in delta in the max degree. And in our setting, our max degree can be very close to logarithmic. And then polynomial and very close to logarithmic is really bad runtime. Unfortunately, or fortunately, and maybe, we developed in a different paper, we developed additional LLL solvers that can actually be used here and they are actually helpful. So this is a congest paper. So one of the main challenges here is actually that one cannot even learn very efficiently for a bad event the status of all the variables that the bad event depends on, because the situation looks really like the picture on the right-hand side. It's very dense and one has to communicate a lot to actually learn enough information about the variables. What does work so, if this information that you had to learn was very sparse, then one can actually solve this LLL. And the bulk of our paper is then actually to find these candidate triples of nodes here. So candidate triples, I always mean two nodes which could potentially get colored with the same color and one gray node here in the middle, which then would get slack. We want to find many of these, but we want to find a sparse subset of these nodes. So it's essentially in this LLL language, what we want to find here is a sparse subset of variables, which then makes it much easier to solve this LLL in a congest manner. Because it's a sparse subset, we can learn a lot of information about this, which makes it much more suitable for LLL. So what we do need here is that all these triples here are disjoint, there's no overlap, which makes it easier to work with them. And sparse, well, what we just need that the graph induced by these triples actually has a small maximum degree. So essentially, this is what we do, and this is where a lot of the work goes in here, is that we actually design a sparsification procedure to sparsify this LLL. And this is done by a sequence of 3 simpler LLLs that are more amenable to congest because they use lower communication, but it's a pretty involved process, and I cannot talk now in this short talk about the individual steps. So the main takeaway here is that you can do, or that you can sparsify LLL instances to make them fit a low bandwidth situation. And I think this is probably the nicest idea of this paper, this general sparsification approach here. So with that, let me just summarize that we've seen, or what we have in this paper is this sublogarithmic time congest algorithm. And there are lots of open questions, for example, coloring with less than delta colors, but in general, also the complexity of LLL. So essentially, we needed to develop new LLL algorithms here, but in general, it's open. What can we really do with LLL? And really, what is the difference between congest and local for such local problems like graph coloring? Thank you very much.
Thanks, Yannick. Do we have questions?
What happens in the case of completely regular graphs? So if you go back to the slide in which you said we have permanent slacks, temporary slacks, and...
I can go back. So well, essentially what happens is that the very left part doesn't happen. And you can just assume it doesn't happen, right? Wherever the left part happens, it's very easy. So really the hard instances are really the ones where everything is regular, delta regular, and this is really, and for example, whether.
So how does the algorithm work intuitively in that case? What happens? If you know.
It's many steps, and we have to deal with all the different types of almost clicks separately, and we also have to process them in the right order for this to really work out. So really, like the fact that in the last level we don't run into a problem and a situation that we cannot solve really crucially relies on how we actually do set up the structure here of, and how we classify the almost clicks into the different categories here. So I think at this point, there's no very simple, short description of this algorithm. Even so, I think like phase 3, 4, 5, they all have relatively simple proofs that they do work. So it's usually like a few lines, each of the arguments, but it always crucially uses the properties of how the click looks in that case. And yeah, the bulk of the work is really in this step 2. This is really the most difficult part here.
And what if we also add the constraint that the graph is supersymmetric? So in this almost click decomposition, you have all similar stuff, or you still create some kind of hierarchical?
Yeah, how I like to think about this, for me at least, the difficult part is I just imagine that the graph almost everywhere looks like these ordinary clicks on the left-hand side, and you just have like an infinite area that just looks of these ordinary clicks that always are connected. Of course, this cannot expand for too long because then you have expansion. So that's how I think about it.
Thanks.
All right, maybe we can have already the next speaker setting up while we have other questions.
So you said that the hardest step is the second step with the clicks, with the one edge going outside. If you assume that the graph does not have this structure, it's like a forbidden graph, can you do something faster? Or is it easy to see to get the same result?
I think, yeah, then our paper shortens by some 20 pages, I think. This is really nice, in particular in Congest, then it's much easier. And I could also imagine that then one can reclassify the clicks to actually get a much simpler algorithm. Yes. I can imagine that. I don't see it right away, but I can imagine that then you can identify different substructures to actually significantly simplify this. Yes.
And can you get like a log n round algorithm, or is it too much?
Like the lower bound is log n, at least for small, with a base delta. So that we can for sure not beat. And even for constant delta, we don't really know how to get to exactly that lower bound.
All right, let's thank Yannick again. And our next speaker is Alexandre, and now we progress from delta coloring to, well, degree plus 1 coloring.
So incomparable. All right. So this is joint work with Maxime Flin and Magnus Alderson in Iceland. And so today I'm going to talk about so coloring in a congested setting, and more particular coloring virtual graph, which I think will be the, let's say, the biggest part of the talk will be just explaining kind of like this model that we are in, and how I think that's a nice way to approach the coloring problem with congestion generally. So we are in the congest model. So, you know, quick recap of the local and congest model. You are in a synchronous message passing model. In local, you can send messages of infinite size, and in congest, you are limited in bandwidth. You can only send log n bits per round on each link, where n is an open bound on the number of nodes. Which means that if you are in local, if you spend a round, like for example, if you think of this node labeled 8 here, after a round, it knows everything about this distance 1 neighborhood. After 2 rounds, it knows everything about this distance 2 neighborhood, and so on and so on. So here, since the diameter is 4, it would know everything about the graph after 4 rounds. Whereas in congest, you are much more limited in that. If you just spend 4 rounds, all you can have learned is like, I mean, on a link, you can only learn x times log n bits of information if you spend x rounds learning stuff, right? So we are interested in coloring. So we start from an initially uncolored graph, and we want to assign the color to each node, so that at the end, the graph is colored properly. And usually, like the common choices for the number of colors, like one of the most common one is delta plus 1, where delta is an upper bound on the maximum degree of the graph. So we can see immediately that this guarantees that you can always color the graph if you have more colors than the maximum degree. But you can also have a more local constraint, which is degree plus 1, where basically every node, a node with very small degree has access to less colors, but since it has more colors than its degree, it's also always going to be able to color itself with one of its available colors, even if all the neighbors took different colors. But until now, I presented this problem as in, so we have this communication network, and what we are trying to color is the communication network itself. Why would that be the case all the time? Why would we always want to color the same graph than the one we are using to communicate? So, for example, a very common problem that's considered is coloring line graphs that corresponds to coloring the edges of the graph instead of coloring the nodes of the graph itself. Very common other problem is power graphs. So you are trying to color your graph, and you want the colors to be distinct, not only at distance 1, but at distance k, for some constant k. And another example you can think of is cluster graphs. So in this last example, imagine that the graph is partitioned into clusters, and you want clusters which are adjacent, meaning that there is an edge going from one cluster to a neighboring cluster. You want the cluster to receive distinct colors. And in local, the infinite bandwidth basically means that all these cases I just had on the previous slide, they're kind of captured by the general case. Like if you have an algorithm for coloring general graphs, you also have an algorithm for coloring line graphs by just having a node simulate the edge, that's each edge being simulated by a neighbor next to it. So you basically have these things that we had log n algorithm in the 80s already. We had polylog log n algorithm. So we now have polylog log n algorithm for the problem of randomized coloring. on general graph. And so the fact that you have this for general graphs means you have all of this also for edge coloring, coloring cluster graph if they have constant diameter, coloring power graphs, and so on. And of course, sometimes the extra structure of like the power graphs or the line graph or something, maybe that can help, but you always at least have this more general upper bound that applies. In congest, the picture is much more complicated. So when it comes to coloring, so the top lines, right, are like when the graph you are trying to color is the same graph as the one for communication. So this is the state of the art from a few years ago is that so you can do it in polylog log n now. Oh, and I should say so this deterministic, this det means basically that you are solving small instances. You are deterministically solving instances of small size. And nowadays, what that means is that you can do this in polylog log n. So replace all the det by polylog log n. And so when the communication graph is the same as the graph you want to color, you have polylog log n time. This is also known for edge coloring, but that was a different paper. Like this had to be proved separately because when you are trying to color edges, it's not clear. Like you have the two nodes that are, you know, the endpoints of the edge that have to decide on the color, and they have to coordinate. Like one of them knows about some of the colors that are used next to it, and the other node knows about the other colors that are used around the edge. So you have this extra layer of communication that you have to do now, which is not so easy in congest. For power graphs, same thing. Like this is you have this very recent work. You can also have the case where you retrieve the communication to only be broadcast, meaning that when you send a message, you need to send the same message to all your neighbors instead of having a different message on each link. In local, it doesn't make sense. You have infinite bandwidth, so even since you can send something infinite, you can just have an extremely long message that just contains all the messages you could send, right? So all these things don't make sense in local. In congest, it requires all this extra work. And what I want to talk to you about today is this framework we have for like unifying this result to a large extent. So what do we mean by virtual graph? So you have to think of the graph on the left being the graph we actually want to color, and the graph on the right is a communication graph. And basically every node, virtual node in the graph we want to color is mapped to a set of machines on the right. And basically for each edge in the virtual graph, it has to be handled by some machine which is at the intersection of the nodes which are handling one of the endpoint and the other endpoint, right? Like for example, here you have this, so at the bottom you have the node that is mapped to these the blue link, right? You have this node at the bottom which is mapped to 3 nodes, and then you have these 2 edges between the middle node and the bottom node, and they're going to be managed. So the link 3 is going to be managed by the machine 3 on the right, right? Which is at the intersection of the blue cluster and the orange cluster, right? And a critical parameter here, critical parameters are going to be congestion, which is whenever you have a link in the communication graph, how much is that link used in many clusters, right? In many supports. And the other parameter is going to be dilation, meaning when you have one node on the left, a virtual node, and it's mapped to a set of nodes it supports on the right, is this set of nodes of low diameter or very big diameter? Okay? So for example, here, the congestion is 2 because if you look at the green cluster and the orange cluster, the edge between 1 and 2, it is shared by 2 supports, like the green one and the orange one. And the dilation, depending on whether you put the center of the orange cluster in the middle or at an extremity, it's going to be like these clusters have radius 2 or 3, depending on where you put the root. I mean, the depth 2 or 3, depending on where you put the roots of the cluster. So let's see how this thing captures the things I mentioned before. So if you want to color line graphs, one way you can cast that as virtual graph is that every link is basically, so for every edge, you're going to consider the cluster, which is made of the two endpoints and the edge connecting the two. And when you have two neighboring edges sharing an endpoint, well, basically the machine in the middle is handling the communication between the two edges. So the virtual graph setting captures this setting. For power graphs, it's a bit more complicated. So if you take this node with a star here, and we're going to do the distance-free power graph. So we consider the subdivision graph of the communication graph G. So meaning that for every edge, we add a node in the middle. And every node is, like it supports this BFS tree of depth k, if you are considering the distance k power graph. And now if you take this other node, basically, so that in the original graph, the node V and the node U are distance free. And in the virtual graph, they have a support that intersect in the middle here. And basically, for every node which are a distance at most k in the original graph, we let the node that is in the middle of a shortest path between the two handle the edge. And so this is how we capture power graphs as virtual graphs. Right. And if you have these different edges, like here, you would have like this machine connecting the two nodes. So, and in general, like if you have a power graph, the power graph k, you embed it in the subdivision graph with congestion delta to the k minus 1 over 2 and dilation k. All right. And so the main result is this thing, that basically if you have a virtual graph so if you have a virtual graph H that is embedded in some network G, you can color this graph in time congestion times dilation, CD, and polylog log n rounds. Okay? So you could take this as a takeaway, but I think the real takeaway is that you have a polylog log n algorithm, but the rounds of this algorithm are like complex rounds which do some broadcast and aggregation on the supports. Right? So what I mean by broadcast is that when you have a virtual node, within the support of this virtual node, you have some node in the support that broadcasts a message to everyone. And in the other direction, aggregation, you can think of like within the support, every node in the support can have some information, and you try to compute something which aggregates this thing, for example, a sum or a max or a min of what is available within the support. And such operations you can always do in congestion time dilation for like quite trivially. So what can you do in this framework if you just assume that no, this is how we are going to design our algorithm with doing broadcast and aggregation? And so, for example, like in the talk just before, like Yannick was saying that one of the most basic operations we have in randomized coloring is a node picks a color at random, tries if it can get this color. So this we can also do here, right? Because for each virtual node, you have one node in the support, designated leader, the root, that picks a color, broadcasts it to its support. And the thing is that now if you think of the machines that are responsible for connecting two adjacent virtual nodes, they know both the color of V and of one of the neighbors, right? So then what you can aggregate is a O of whether a conflict was detected. So this already gives you like some idea of how you could design things. Some of the non-trivial thing you can do is some probabilistic counting. So since we are in this virtual graph setting, so the degree, when we talk about the degree, we actually mean the number of edges in this virtual graph, but the virtual graph is actually a multi-graph. Sometimes you are connected multiple times to the same node and you cannot really detect exactly when that happens. That would be very costly. But the thing is that if your actual number of neighbors is much lower than the number of edges you have to other virtual nodes, that actually helps you, because whenever one of your neighbors gets colored, the same color is going to appear on a lot of edges, right? Because the edge just gets repeated. So it can be very useful to estimate whether the two are close or far apart. And this you can do with some probabilistic counting. So basically, in each spanning tree, you sample some random variables according to a geometric distribution. You broadcast the values you sample to the tree. And then you compute a max of the values that were sampled in your neighborhood, and you aggregate. And somehow, like this is like a classic streaming kind of, you see this a lot in like the streaming setting, for example. This is if you take the value of the random variables that were sampled, this gives you a good approximation of how many neighbors you have. And the thing is that since you're taking a max, right, when you have two neighbors, when you have a neighbor and you're connected to it multiple times, it doesn't matter if you were doing a sum, you would count it multiple times, but here you're doing a max. So even if something appears many times, it doesn't change anything, right? So this is why this is able to give you a good estimation. And another thing you can do is doing some kind of binary search to search for a color. So if you are, so you just initialize, like, so you want to look at you want to find a color between 1 and the maximum and degree plus 1. So what you do is you just say, you're going to count how many edges that you have in the virtual graph are to a neighbor which has a color below the middle between low and high, like the search space. And then you just iterate left or right, like very basic binary search. You can do some kind of binary search here to find a color. So imagine this, right? Because we have to do this because you just don't know which colors are used by your neighbors. Like this is very expensive to discover the colors used in your neighborhood. But if you just want to find one available color, this is doable with some kind of binary search. And actually, there is a talk on Thursday which uses this exact kind of idea to get speed up in for like implementing, for example, some sort of linear algorithm in power graphs. So if you're interested in this kind of thing, like maybe good idea to go to that on Thursday. And so I don't have time to go into the structure of the algorithm, but to give a quick idea, basically, just like in the previous talk, we do some kind of graph decomposition, getting in some so we identify the nodes for which the degree is small. We're going to treat them separately. We identify nodes for which the degree is far from the actual number of neighbors they have. We treat them separately. We identify nodes which have neighbors which are not connected together. So this was something that Yannick was talking about in the previous talk. Like if you have neighbors which are not connected, it's like you can make them get the same color, and that's very useful. And then you have the things which are more very well connected, and then you can do some kind of synchronization. When things are very well connected, that can also be helpful to like coordinate. And we match this. We also give a lower bound for a problem. So remember that we had C times D times polylog log n. We show that you need, if you have bandwidth B, congestion C, and dilation D, you need at least C over B plus D times log star n to color some graphs. And this is a classic communication complexity lower bound. The intuitive idea is like you introduce some kind of gadget, you show it's not a trivial thing to solve, and then you embed that in a virtual graph. So here is the gadget here is like free coloring the thing that you have on the left, and basically Alice has the matching on the nodes on the left, and Bob would have the matching on the node on the right. And so you don't know the matching in advance, so you have to exchange some information between the two. And so some takeaway message. So I hope this gave you some hint of like maybe why these virtual graphs like are a nice way to capture like maybe it's the right formalism to generate results like from edge coloring, power graphs, and so on, and maybe it should be applied to other things than coloring. So if you're interested, like look at it maybe. And yes, and like the main thing was showing that all the complex operations that were usually done in distributed in randomized coloring algorithm can be done with this aggregation and broadcast kind of operation. And some open question: can we strengthen the lower bound, or can we improve also this implementation of a round of broadcast aggregation from CD to maybe something which would be more like the addition of C and D? And that's it. Thanks.
So while the next speaker can already set up, we have time for a quick question.
So your lower bound construction, at least one of those, was using cycles as your virtual graph. So I'm wondering, what are the upper bounds that you will get in that specific case of a cycle? Like, do you get anything better than C times D times log star of N?
Right. You're saying like if instead of designing a generic algorithm, I just specifically aim for the lower bound graph.
Yeah.
I would say it's probably faster, yes, but I don't. I'm not entirely sure, but I would say probably yes. Yes.
Yeah, but especially like, can you avoid this multiplicative C times D in that case?
I mean, I would say so. Like I can also tell you that there is already one case where you can avoid it, and it's power graphs. In power graphs, like the congestion is much higher than the dilation, right? Because the congestion is exponential in K, and the dilation is just like linear in K. And in that case, specifically for power graph, you can just do like congestion.
Okay.
So addition.
Okay. Thanks.
All right, let's thank Alex again. And as the last speaker of the session, we have Manish, who will tell us about agent-based leader election, MST, and more.
Hi, this is joint work with Ajay, Anishur, and Gokana. So, agents are the moving entity, and they have unique IDs, and they can communicate only when these agents at the same node. They has memory, and when the robot moves from node U to V, it knows the port used to enter. Basically, there are port numbers by which they can navigate. So, if we talk about graph model, this is anonymous graph. Nodes have no IDs, no memory. These are just a container for the agents. These are connected, undirected, unweighted. So port at each node have unique labels from 1 to delta, and in these they have no correlation, and delta is the degree of the node. So if we see the runtime and memory, we are using synchronous system. So the total number of rounds required to solve our problems is the runtime number of rounds. And the memory required is the number of bits stored at each robot. So the leader election problem is there are n agents, n nodes, and they are scattered, and we want to elect one of the node as leader. First of that, in this process, we first elect the local leader election. There are two. One is among the singleton agents, so there that one agent is the agent is single on a node. So what they just explore their neighbor based on their ID and port numbering, and they figure out based on their priority, which might be their ID, whether they are local leader or not. The other case might be among multiple agents, in which if there are more than one agents on a node, then one among them become the local leader, and it kind of help to other agents to move to other nodes. And after that, it start the kind of DFS to figure out whether there are some other agents which have higher priority, and if it doesn't find any agents, then it run the DFS and become the leader. So results, we have order of m time because we are using DFS, and The memory is order of n log n, because an agent might have to remember order of n agents, what kind of path they have done. And we are not using any parameter knowledge. So the leader, after leader election, we are running the variant of well-known GHS, and we are constructing the MST. The other well-known the application for in which agents are gathering on a single node, MIS, MDS. So basically our results are this. We are using order of m time to elect the leader and order of n log memory. And then we have the kind of immediate results. So in MST, we are taking additive factor of n log n. In gathering our improvement, it is kind of, these are, others are immediate results. We are using time order of m. And in place of n cube, similarly for memory, we have improvement. And in case of MIS, we are removing the log n factor, multiplicative factor, and in MDS, we are removing other factors, additive factors. Yeah, thank you.
Thanks, Manish. Do we have a quick question? So if you go back to the table once, there's this O of n time d you have for MIS, I believe it was. Guess the O of n times d. What is your feeling? Should the right answer be there? The O of n time d that you have for the time in the MIS. Like, do you think this can be improved?
Select the leader and we figure out the immediate results. So this was the existing algorithm, and based on that, I can't comment right.
Okay, thank you. So let's thank our speaker again. And once more, let's also thank all the speakers of the session.
Okay, this break is a shorter one because we need some time for the drinks before the business meeting. So the next session will start at 16:25. Is that okay? Thanks.
Karthik said. Yeah.
People are coming. There's like a lot of people.
So the reward for you for saying here is that there is a happiness following this session, right? There is a happy hour. Yeah. Let's start in 2 more minutes. For change. Okay, let's begin. So we have 3 papers in this session, 2 long papers and a brief announcement. The first paper is presented by Neil Giridharan. The paper title is, of course, Random Synchrony, and he has co-authored with Ty Abraham, Natasha Crooks, Karthik Nayak, and Big One. And Neil is at UC.
Thanks, Nathan. Hello, everyone. Excited to be here. Today, I'm going to talk to you about granular synchrony. This is joint work with my collaborators, Itai, Natasha, Karthik, and Ling. So I wanted to start off this talk by saying something perhaps a bit controversial. I believe we theoreticians should actually listen to what the practitioners in our space are saying. Many practitioners have long argued that many of the assumptions we make in theory are just simply not practical or realistic at all. So Peter Deutsch wrote this very famous piece called The 8 Fallacies of Distributed Systems, in which he writes many common fallacies that people make are that the networks are reliable, networks are homogeneous, and network latency is 0. But reality paints a much different picture. We have evidence that says that networks experience significant latency fluctuations in a variety of settings, including both over the internet and even across regions in the cloud. So real networks aren't just some ideal black box. They're unreliable, they straddle across multiple fault domains, and they have non-trivial latency that we must account for. So with this reality as theoreticians, what assumptions should we actually make about the network? Well, today we basically have 3 options. The first option is synchrony. And with synchrony, we assume that messages must arrive within some known upper bound, often called delta. At the other extreme, we could assume asynchrony, in which we assume messages will eventually arrive, but we have no assumption on their delivery time. Or finally, we could go for a hybrid of the two, with partial synchrony. So with partial synchrony, we assume the network is asynchronous for some unknown time until GST, and then is synchronous afterwards. So unfortunately, these options put us in a bit of a conundrum. So on the one hand, if we pick synchrony, we have a nice simple model that has really good theoretical results. However, synchrony is a bit too optimistic for practice. A single message that's delayed outside this upper bound delta can make all of our guarantees go out the window. On the other hand,
if we pick partial synchrony or asynchrony, we have a model that's more robust to non-ideal network conditions. However, this comes at a significant cost. Many theoretical results are simply worse than their counterparts in synchrony. Famously, the FLP result said that the consensus problem was impossible in asynchrony. So how can we resolve this tension? Well, our insight is that the models synchrony, partial synchrony, and asynchrony are simply just too coarse-grained. Not every link needs to have the same synchrony assumption. So we leverage this insight to come up with new network models that allow for this link diversity. We then come up with necessary and sufficient conditions for solving consensus in these models. And finally, we show that with these conditions, we can get better replication factor bounds compared to traditional partial synchrony or asynchrony. So let me now introduce you to granular synchrony, a new network model that's more pessimistic than synchrony, but more optimistic than partial synchrony or asynchrony. So we have two variants of granular synchrony. The first variant is called granular partial synchrony, and the second variant is granular asynchrony. In granular partial synchrony, we assume all communication links are partially synchronous or synchronous, and with granular asynchrony, we assume that links can be partially synchronous, synchronous, or asynchronous. So for this talk, I'm going to focus on granular partial synchrony, but we also have results for granular asynchrony in the paper. We're going to assume that this graph is going to be complete and undirected. So every pair of nodes has a communication link that's bidirectional. And we assume that nodes do not know the synchrony type of the links. So in this granular synchrony model, we're going to study the specific problem of fault-tolerant consensus. Now, consensus probably needs no introduction for everybody here, but so I'll go over it pretty quickly. So there are two variants of the consensus problem. The first is we have n nodes and we assume f can crash or fail stop. And the second is the f nodes could behave arbitrarily or Byzantine. So for this talk, I'm going to focus on the crash fault tolerant case, but we do have results for the Byzantine case in the paper. A key concept in our model is the notion of a synchronous path. A synchronous path is a path in the graph consisting of only synchronous edges with no faulty intermediate nodes in between. So as an example, suppose we have the following graph. R1 has a synchronous path to R3 because there are synchronous edges connecting R1 to R3. And importantly, the node R2 is correct. But if you'll notice, R1 does not have a synchronous path to R4. And that's because while there is a path containing synchronous edges connecting R1 to R4, the intermediate node R3 is faulty. I also want to make a quick note here that we assume that every node has a synchronous path to itself. So we can use the concept of synchronous paths to define our next key concept, synchronous connected sets. So we say a set A is synchronously connected to a set B if for every node in B there exists a synchronous path to a node in A. So that may be a bit hard to understand, so let me give you an example. So suppose we have a set A here consisting of nodes R1 and R2, and we have a set B consisting of nodes R1, R2, and R3. Here, set A is synchronously connected to set B because nodes R1 and R2 have synchronous paths to themselves, and the node R3 has a synchronous path to a node in A, in this case R1. So that's all the background. Now let's get into the real meat of the paper. So a core contribution of our work is identifying a necessary and sufficient condition for solving consensus in granular synchrony. This condition may look simple at first, but it took us a long time to formulate and come up with the right condition. If you take nothing else away from this talk, this is the main thing to remember. So our condition states that any set of n minus f nodes must be synchronously connected to at least f plus 1 nodes. So here's an example. Suppose we have the following graph of 4 nodes with R1 and R3 faulty. What this condition would mean for this graph is that for any 2 nodes I pick, it must be synchronously connected to at least 3 nodes. So for example, suppose I pick R1 and R2. Well, R1 and R2 are synchronously connected to themselves and R4. Now let's suppose I pick R1 and R3. Well, R1 and R3 are actually synchronously connected to all 4 nodes in the graph. You can do the exercise yourself, but you'll see that no matter which 2 nodes I pick, it'll be synchronously connected to 3 or 4 nodes. So therefore, this graph satisfies our condition. So some clever individuals in the audience may have instantly understood the condition, but for the rest of you, I'm going to try to give you some intuition. I think the best way to understand this condition is to look at the extremes. So let's take the case where suppose every edge is partially synchronous. So this essentially degenerates to the partially synchronous model. We know from the lower bounds of partial synchrony, we must have n greater than or equal to 2f plus 1, which means n minus f is greater than or equal to f plus 1. Well, since we assume that every node has a synchronous path to itself, this is trivially satisfied in our partial synchrony model. Now suppose we're at the other extreme, where we're considering that every edge is synchronous. Well, we know from the lower bounds of synchrony, n must be greater than or equal to f plus 1, which means n minus f is at least 1. And since every edge is synchronous, every node has a synchronous path to all nodes in the system. So again, this satisfies our condition. Hopefully you believe me that this condition makes sense. Now let's move on to actually proving this condition is necessary. Well, to do so, let's suppose for contradiction that there exists a set of n minus f nodes that's synchronously connected to at most f nodes. Well, what can happen? The classic split brain attack. So with the split brain attack, the adversary can partition nodes into two sets, and each of them can make progress independently due to asynchrony. This is the key technique that was used in the DLS result. So let's see how this split brain attack works in action. Suppose we have a set A consisting of n minus f nodes, and it's synchronously connected to some set B, such that in total, there's at most f nodes. Well, by definition, there must exist some set C of size at least n minus f nodes that's not synchronously connected. Well, nodes in B can't distinguish whether nodes in C are slow or crashed, and similarly, nodes in C cannot distinguish whether nodes in B are slow or crash. Therefore, B and C can make progress independently and perhaps decide two different values. So I now showed you the intuition for why the condition is necessary. Now let's go move on to proving that it's sufficient. To do so, we need to have an algorithm that solves consensus in granular partial synchrony. Now you're probably wondering, okay, the obvious choice is to use some existing partially synchronous algorithm like Paxos. Well, unfortunately, Paxos only works when n is greater than or equal to 2f plus 1. When n is less than or equal to 2f, Paxos loses all of its safety guarantees. So you may be wondering, why is that the case? Well, Paxos uses quorums of size n minus f, and when n is less than or equal to 2f, n minus f is less than or equal to f. This means that quorums of size n minus f actually don't intersect, and this is the key property for how Paxos maintains safety. Now you may be wondering, okay, let's just use larger quorums. But the problem is that f nodes may be faulty and just never respond. Okay. To solve this problem, we're now going to utilize the condition we proved was necessary. So if you recall again, we have a set A of n minus f nodes that's guaranteed to be synchronously connected to a set of f plus 1 nodes. This set of f plus 1 nodes is guaranteed to intersect any set of n minus f nodes in at least one. So we can make quorums of n minus f indirectly intersect by using this set of f plus 1 nodes as a sort of conjugate. So I've talked a lot about the sets being synchronously connected, but how do we actually take advantage of this in our algorithm? So our key technique that we're going to use is this message echoing. So suppose we have the following graph where R1 has a partially synchronous edge to R4. Normally, there wouldn't be any guarantees on the message delivery time for a message sent from R1 to R4. However, if there's a synchronous path as such from R1 to R4, we can do better. So if R1 sends a message and it echoes it, and R2, upon receiving a message from R1, also echoes it, then we're guaranteed that after 3 hops, R4 will receive this message. And we can generalize the concept to say that if there's a synchronous path in the graph, a node will receive this message by order n delta. Okay, so that's our key insights. Now let me show you how our protocol actually works. I'm going to start with the normal case, which occurs in fault-free ideal conditions. Now you'll notice that the normal case looks a lot like normal Paxos. The protocol operates in a series of views where each view has a distinct leader that tries to drive progress. So this leader is going to send a proposed message to all the other nodes in the system. When the nodes receive this proposed message, they're going to lock on this proposal. And this lock is a promise that they're not going to vote for a proposal in an earlier view. Okay, once they receive this proposal, the nodes are going to broadcast a vote message to all of the nodes in the system. And once the nodes receive enough votes, in this case n minus f, they're going to commit. Okay, simple enough, but you're probably, for those of you who are still awake and really paying attention, you'll realize we didn't actually change anything fundamentally. Quorums of n minus f don't intersect, so how does this actually ensure safety? Well, in order to have a split brain attack, you actually need to have two different leaders, which requires a view change. So we're going to modify the view change protocol of Paxos so that the new leader hears about the most recent lock that could have been committed. So let's see how the view change works. So it's going to start when some node, say this third node here, suspects that the leader is faulty. So it times out. Then, upon timing out, it's going to send a new view message and a lock, its most recent lock, and importantly, it's going to echo it to all their nodes. And similarly, when other nodes receive this new view message and lock, they're also going to echo this lock and new view message. And importantly, once a node has echoed the lock and new view message, it's going to wait this 2n delta period, and it's going to stop voting for anything in the view. This is important because if there was a commit, then we know n minus f nodes have locked on a value. By waiting this 2n delta period, we are guaranteed that after this time, at least f plus 1 nodes will receive this most recent lock. Okay, once the waiting period's over, each node is going to send a status message to the new leader containing the most recent lock they've heard. And the leader is going to pick the most recent of these locks and propose it in the next view. And remember, out of these n minus f status messages, we're guaranteed that it's going to intersect with our f plus 1 quorum, so this helps maintain our safety and prevents the split brain attacks. Okay, so that's the protocol, but why should you actually care about this result? The key enabler is that we can get a lower replication factor compared to traditional partial synchrony or asynchrony. So let's see an example. Suppose we have 4 nodes as such, where one node can crash. Well, normally in partial synchrony, we can only tolerate one fault with 4 nodes. However, if we just add these 2 synchronous edges as such, we can actually tolerate 2 faults with just 4 nodes. To tolerate 2 faults in traditional partial synchrony, we would need at least 5 nodes. So I unfortunately don't have time to cover all of our results, so you can check out our paper for more details, but here's some of the other results we have. So we have a necessary and sufficient condition for crash fault tolerant consensus and granular asynchrony, and we also have results for Byzantine fault tolerant consensus and granular partial synchrony and granular asynchrony. Okay. Finally, I want to conclude by reiterating that granular synchrony enables protocols with better resilience to faults compared to pure partial synchrony or asynchrony. And it's not just another theoretical construct. It's rooted in observations seen in practice, and we think it's useful for practitioners to adopt. Thank you, and I'm happy to take questions now. Yeah, definitely. I think problems like secret sharing, for example, MPC, I think that's some interesting future work to look at as well. Yeah, it's yeah. Right. Yeah, so we only consider undirected graphs, and for that result specifically you're referring to, they consider only partially synchronous and asynchronous edges. So we additionally consider synchronous edges, which allow us to have this bound between a half and a third. Yeah, exactly. In the bidirectional case, yeah. Well, I mean, they consider directed links. We consider undirected.
they could dynamically change in a slow manner to preserve some invariance of synchronous connectedness throughout the entire. Would your results still apply then?
Yeah, that's a good question. So another way you could formulate this is, because our algorithms don't actually assume knowledge of the specific synchrony assumption of the graphs, is that you can imagine you have an adversary. Like you start off with a graph that's fully synchronous, fully connected, and the adversary can pick links and alter them to be either partially synchronous or asynchronous. Now this comes with the crucial caveat that once you alter it to be partial synchronous or asynchronous, you can't unalter it back. But yeah, that it seems to be that it wouldn't be too hard to extend, but that'd be interesting future work to look at. Yeah, thank you.
Diana is also here. Diana is also here. Hello, hello, distributed humans. I'm Kobe, and this is Kobe's clocks. So, partial synchrony, right? Partial synchrony is everywhere. It is all around us, even now, in this very room. How is it so omnipresent? One could argue that's where we live, somewhere between the utopia of synchrony and the war zone of asynchrony, right? But what do you mean by partial synchrony, Kobe? I mean, even in the original paper, there's two models separated at birth called partial synchrony, right? There's global stabilization time and unknown latency. So, okay, there's two models. One is the global stabilization time. So in global stabilization time, it says we first need to endure this war zone for some time, but at some point in the future, we can enjoy the synchrony. Then unknown latency says there's always a bound on the message latency, but we don't know it. It can be anything. It can be very long. So what is it? I mean, is one model stronger in its assumptions than the other? So is unknown delta more difficult model, or is it the other way around? Is GST more difficult? Okay, almost immediately we think about it, we can, no, the latter is not true. Why is that? Because, okay, let's think about some protocol we have for unknown delta, but imagine we actually live in the global stabilization time. And then the devil says global stabilization time is at some point. Now we can think, okay, our protocol works in the unknown delta. If the unknown delta is actually equal to this GST from the other model, then one icon doesn't show. It says, if we are good here, we're good here, right? Okay, that's very cheesy, but it means a lot of things we can do in the unknown delta, we can do them in global stabilization time, that's clear. So is it the other way around then? Is unknown delta a stronger or like harder model to make a protocol for than GST? Let's try to think of a way to make a protocol for the unknown delta, given a protocol for the GST. So one popular technique is that we have some timeouts, we have some timeout thing in our protocol, and we just increase it. Okay, things don't work out, we increase it. So okay, your uncle did it many times and it worked, it's a good technique, but we cannot assume that for every protocol, we can just pick like a sanitized point in time where we increase the parameter and then things don't explode, because the model says that we have this delta from the beginning and that's it. Okay, here's where we come in. What you actually can do is you can transform the clock inputs before the algorithm uses them at all. So we're just going to continually slow down the clock. The algorithm will think that the delta from the beginning, like it's the same delta forever, but actually the effective delta really needed for the protocol to work, it will increase because the clock slows down. So that means if we're good in, okay, at some point, this effective delta will increase, it will get bigger than the unknown delta from the other model. It means we can do something in GST, we can do it in the unknown delta. So I'm happy to announce that the long separated models are unified, and thank you. Yeah.
When you said, when I can solve in one model, I can solve in the other, you just needing some notion of correctness.
Yes.
But maybe you can do some better guarantee if you knew the delta and the different.
Yes, that's an excellent point, right? Because in this brief announcement, we talk about time agnostic properties. So they depend on the order of things or like what the outputs are, but they cannot depend on the sort of time, right? I mean, if you can do something in the delta that's known in the GST, then how would you even translate it to unknown delta if it can be anything? So yeah, I mean, in this brief announcement, we talk about these time agnostic properties. But I mean, some properties, right, that relate to time, they are hard to translate so that it makes sense, right, between them. Thank you.
The next paper is titled Convex, Consensus, and Asynchronous Fallback. Three of the authors, Alex, Ian, and the talk is given by.
Maybe I should have joined before, actually. Would have been very helpful. Huh? Right. Come on. Perfect. Okay. Great. Yes, I am. Request permission to wait. No, share. That's fine. Okay. Does this work? Okay. Yeah. Okay, this should do it. So hi everyone. I know everyone is really struggling to stay awake by now, and they cannot wait for the business meeting and all the interesting proceedings happening there, and maybe for the happy hour. Who knows? So I'm gonna try to bore you even a bit more now with convex consensus with asynchronous fallback, where convex consensus is one thing and asynchronous fallback is what makes this talk be in this session. We will see yet another way to be between sync and async. So, what is and why do we even care about convex consensus? Because everything is convex if you believe, and I will try to make you believe. So by consensus here I will mean Byzantine agreement, which many of you know what it means. Here you have n parties, let's say these four smiley faces with different disturbing personalities perhaps. They communicate over a complete network, they have some inputs, they want to give some outputs at the end after running some distributed protocol. And because this is Byzantine agreement, three of them are Byzantine, they don't listen to what you are saying, they do whatever they want, they try to mess up your protocol, that's their only sole purpose in life. Like this guy, for instance, but nobody knows who he is. The other people are called honest, that's just a name people use. So it's called agreement because we want all the honest at the end to agree on the same output. Why? Like that. And obviously, like agreeing on an output is easy. You just output one. You just output dog, and that's we agreed. But we want the output to in some way be meaningful. So what does meaningful mean? And that's where it all becomes very interesting. So people have in the distributed computing literature considered this question a lot. Now, this depends, of course, on what are the inputs, right? If you want to agree on the perfect wine to drink in 20 minutes from now, that's a different question than agreeing on a binary number, for instance. if X is just some general purpose set, so the inputs are just something, whatever they are, then people considered strong validity, for instance, which just says that if everyone says yes at the beginning, then the output should be yes. And if some people say yes, some people say no, then it can be anything. But even with not just yes and no, it can be 100 possible elements in X. That's one thing. You can do something even stronger than that, which is honest input validity, which is maybe something you would want maybe in a blockchain context. Like if everyone proposes a block, you want the block that is agreed upon in the end to be proposed by someone that is well-intended. So you can imagine many setups where you want this. Of course, the second is harder to achieve than the first. They coincide for binary, if anyone cares. Now, the thing is, the setup at the top is like general and okay, so much for it. But in practice, people care about agreeing on more like concrete things. For instance, on a real number, if like in the original long ago paper where we talked about altitudes, temperatures, prices, and here people consider usually this property, which is called honest range validity, which just means that if some people are annoying and propose the value to be 1,000,005 and everyone proposes temperature around 30 degrees, then you cannot agree on 1,000,005. It should be around 30, which just means you should be between the lowest and the highest honest input. You can generalize this to higher dimensional spaces and one super nice application, and there's many people in this room who know about this and some people who worked on this, agreeing on, let's say, a point on a map or some general vector in R to the D. And for this, we have convex validity, which is just honest range validity generalized to R to the D, which says Y is in the convex hull of honest inputs. I will give you an example of what this is, because this is essentially what the talk is all about. And you can visualize it a bit more, and we will eventually generalize even further. So you can imagine you have these 4 friends who want to agree where to meet. This is in the city of Zurich, if anyone is concerned about the exact location where we are doing our agreement. And they have those inputs. Like, if everyone is honest, convex hull validity just says that you should agree in some place inside that area. That's fine. So the meeting point should be somewhere, everyone should agree on the same meeting point. That's okay. Now, if this guy is malicious, then we want the agreed upon point to be in the convex hull of 3 people instead of 4. So that's what the problem is about. Now, the question is, and this is where it becomes even more interesting, is this all that convexity is about? Like, can we talk about more things like, did we basically solve convexity if we solve this, like agreement with convexity? Well, you might notice that we might agree on a point inside the river. Nobody wants to travel there. So maybe we want to consider different kinds of convexity, maybe on graphs, and people considered other things. So let me now define to you a quite abstract framework that mathematicians have put together of what is convexity. It sounds a bit like a topological space. If you don't want to quite listen about the details, it doesn't quite matter, because you can think that it's R to the D for the whole talk, except the results are general. So a convexity space is defined on a ground set, which could be maybe R to the D, and it specifies what sets are convex, what sets are not, and we will eventually take convex hulls. There are 2 technical conditions for this to be a convexity space. They don't quite matter. What matters is you can define a convex hull one way or another. This is pretty scary looking, but it doesn't quite matter. Let's not get into that. What is interesting is the examples we can make of convex validity if we choose C. Of course, we looked at R to the D with the normal notion of convexity. That's good. You can do, there are ways to define convexity on graphs. There are ways to define convexity on lattices, which I'm not going to define, but the point is there are ways to agree on vertices in a graph this way, so we can solve our river problem. You can even define weird things, like say, take X to be any set and say that everything is convex, and that sounds ridiculous, except that's exactly honest input validity. So actually, even when you don't think there's convexity, there is. You can also do this weird thing. You can say only the singletons are convex, plus the other 2 things that have to be convex, and then you actually get strong validity. I mentioned, I guess, already, honest range validity is just the D equals 1 case. So basically, by varying C, we can get a lot of the properties that have been studied in the literature already. And now what we would want to understand ultimately is, given a convexity space C, which can be anything, it can be bottles of wine if you want,
what is the largest T such that we can get agreement, convex validity with this bounty on corruptions. Maybe a third, maybe a fourth, this kind of bounds that you always see in Byzantine agreement. Now, and this is what is called convex consensus, or at least what we call convex consensus. The problem is that to even specify bounds on T, you need to look at C, and C is some arbitrary mess. And I'm going to show you that actually you don't care about C, you care about one specific thing about it, which is called the Helly number, which is a nice geometric invariant. So for those of you who do not know about Helly's theorem, I'm going to just quickly show you. So Helly's theorem is this amazingly cool result, in my opinion. I really love it in R to the D. Let me just put it there quickly. So you have some convex sets in R to the D. And you know that however you choose D plus one of them, they all, okay, if any subcollection of D plus one intersect, then they all intersect. Okay, this sounds extremely abstract. As an example, consider 100 disks, very concrete, any 100 disks, such that every 3 intersect. If this happens to be the case, then all 100 of them intersect. And this is non-obvious, it's very non-obvious, even more non-obvious because with 2 it doesn't hold, because you can do something like this, any 2 intersect, but there is no point common to all 3. Now, this is Helly's theorem in R to the D. You can actually take the same thing, like copy-paste it downwards, and just say, okay, we have our C, there needs to be some number, omega, in there that makes the theorem hold. Okay, maybe there is none, in which case it's infinite. I'm not going to get into that for the talk. We briefly mentioned it in the paper. But the thing is, there is such a number W for every convexity space. And this is called the Helly number of the convexity space. And I'm going to actually show you that the question I phrased can always be answered only in terms of, let's say, n, of course, nW. Like you will get things like n over W, and that's it. These will be your if and only if conditions for every C, where, of course, W is given the C. Of course, to actually answer everything precisely, we need to know the model. Is it sync? Is it async? And this is where the second part of the title comes in. So let's talk about synchrony, asynchrony, and this in-between model that we sometimes call best of both worlds. We sometimes call it the network agnostic model. We sometimes call it, there was even a third name I forgot. So I'm gonna not bore you quickly. Synchronous communication means messages get delivered between 0 seconds and 1 minute, or like some known amount of time. And the problem with synchronicity is that while it allows for large resilience thresholds, if one message is 1 second too late, then the protocol breaks down. And as you have seen in the session previously, you can define the asynchronous model where messages just eventually get there. The problem is they require a lower threshold. And now there are many in-betweens, and you have seen 2 ways to do it in the previous talks, how to define in-betweens between those 2 models. And here is a third way, so to achieve a trade-off. It's called the network agnostic model, or the with asynchronous fallback. That was the third model. In this model, you are given not 1 T, but 2 Ts, a TA and a TS. And let me just put it here. If the network happens to be synchronous, you need to tolerate TS, which is the larger number because it's the easier condition. And if it's asynchronous, you need to tolerate this smaller or not larger corruption threshold TA. And of course, this is easy if you know in which one you are. The idea is the protocol has to work for both without having any signal on which one is true. And of course, the question of what is the largest T here degenerates into what pairs TS-TA are possible. It's 2D. So I'm going to show you the results quickly and then try to give you a short overview of like one cool technique and some small things about how we can get them. And what I want to emphasize is where omega appears, like why we have the Helly number in the conditions. So convex consensus is solvable if and only if in the synchronous model T is less than n over omega. This is something that, of course, for R to the D, it was known. Most of these things were known for R to the D. There's a tremendous line of work on all of these things, but not as general with this C that we consider. In the asynchronous model, you need slightly less corruptions. This is probably what you would expect if you work on Byzantine agreement. You always have n over 1 more for the asynchronous model compared to synchronous. And now for the network agnostic model, of course, we need to first have the synchronous bound to hold. We cannot do better while having asynchronous guarantees if we ask for even more.
You might also now say, okay, we want also the asynchronous one, and you do that, but you want even slightly more. You don't want omega plus 1 TA less than n. You want omega TA plus TS, which is slightly stronger. You need this. And you need also a third thing, which is actually unrelated to the convexity space. It's related to communication, and I don't want to talk about it, but this is something you see a lot in these network agnostic papers, that you need 2 TS plus TA is less than n. Now, just for people who cannot visualize this complicated mess of a condition in one line, for instance, if you take omega to be 3 and you plot everything in the plane and you let n be 100, let's say, the green part is the pairs that are possible. And now, depending on omega, the picture looks slightly different, but you always get a polygon of what is possible. Now, to prove all of these things, you need to prove, like what, 5 impossibilities and 3 possibilities. Of course, some of them swallow the others, but I'm going to show you 2 of them, time permitting. Like, I'm going to show you why n over w is required, which is like something that was kind of known already for r to the d, but we generalize it, but I want to show you because it's quite a simple proof. And then I'm going to give you an idea how we do network agnostic, so possibility. So why do we need, why n over w is impossible? So we need strictly less, why equal is not possible? Well, consider 3 people in a triangle. We are in r squared, I'm just simplifying a bit, but the proof is the same in many dimensions. And take this guy. This guy can think, okay, maybe this guy is corrupted and then I need to output something on the black line. Or maybe this other guy is corrupted and I need to output on that black line. So then I don't know on which black line I am, so therefore I need to output my value. And of course, everyone reasons like that, and they will get completely non-agreeing outputs, and that's terrible, it's not possible. To do it in general convexity spaces, we do something very similar, but what I want to emphasize is that you always get such a bad instance, but it's a bit harder to construct it, but you literally get that the instance exists because of the definition of omega. And this impossibility was known for r to the d, and it was known for something called convex geometries, but it was not known for every convexity space. Okay, for possibility. And if there's one thing that I want you to take away from the talk, will be the first part of this slide. So what we will do, we are going to try to turn the problem into a local problem. How are we going to do that? Well, we make the parties somehow magically, this will be a whole protocol, distribute their inputs to get a common view on what everyone's input is. The idea is we just want everyone to have the same view on who has what, and then at the end they will just locally compute something, and deterministically, meaning that at the end they get agreement for free and we just need validity. But what do we want from the common view? Well, we are going to get exactly the best things possible. Some values will be unknown, and that's necessary because we have asynchrony as a possibility, so you just cannot guarantee that everyone finds out about every value because values can be infinitely delayed. All honest values that are in this vector, in this common view, are the correct ones, and that's easy to ensure with something like reliable broadcast. The number of non-values is large, and this is actually best possible. You cannot get better than this. And if the network is synchronous, all honest values are known. And this is something easy to ensure if you know you are synchronous, but you know you are synchronous or asynchronous. So it's a bit tricky. Now, this thing is called agreement on a core set or core set agreement, and this paper is, to the best of my knowledge, the first paper where we get these conditions. These are like the strongest. This is like the strongest core set agreement definition you can get for the network agnostic model, and it basically simulates a trusted third party. Like you cannot get a better, like a stronger core set than this. Okay, and the second part is people just locally, based on the view, compute something. It's called the safe area, which is not new to this work in any way. Agreement is for free, as I said. And quickly, the safe area, and I might skip some things, but it's not so important. The safe area is the following idea. Let's say I make you one of the parties, and I say, look, in the common view, you see 4 values. And I somehow tell you, and you magically know at most one is corrupted. What do you output? Well, you just brute force who is the corrupted one by one, and you think what is the convex hull in that case, one by one. And you intersect all of them because you don't know which one is true. But if you intersect, you know you are good in any case. And you will get some set. In this case, it's a point. And this set will always be, it's called the safe area. It will always be valid no matter what. Points in this set, and you deterministically choose a point from that set. In this case, it's only one, but it can be larger. Generally, If you have A values in the common view and you know somehow magically that most B are corrupted, you take intersections of all convex schools of subsets of size A minus B. Any point in the safe area is valid, you take one deterministically, you are done. You're gonna ask me why this is non-empty. That's because of omega. And I might skip that quickly, but anyway, who are A and B? You know the common view is large, let's say it's that large. If you are synchronous, at most K values are corrupted. Therefore, you will set B to be K. If you are asynchronous, at most TA, so you set B to be TA. You don't know which, therefore you take the max. Why is the safe area non-empty? The idea is you intersect many convex sets, but by the Helly theorem, it suffices to only show that only any omega of them intersect. And then you do some pigeonhole argument and you use the condition and you are done. Some outlook of future work is we kind of showed that convex validity is an umbrella that captures many things, but there are also many things it doesn't capture. The question is, what can you do with them? In fact, does it rain on them? Well, the answer is not really. There are actually a few works that consider this even more general validity conditions, and we have a recent preprint as well on how to do even things that are not convex for network agnostic, and there are previous published papers on how to do synchronous or asynchronous. You can also ask what happens with approximate agreement, and there are also lots of works on this. Well, the problem with approximate agreement is that it's even hard to define what approximately agreeing means on an arbitrary C. Therefore, people considered graphs, considered R to the D, and there are many results. What happens with other adversaries, like with crashes? Again, it's harder to get impossibilities there. And there's like a whole line of work on understanding when can you get approximate agreement on graphs. Here you have all this line of work on topological methods. You have so many ways to talk about this. Anyway, this is an exciting line of work, and you can probably do a lot with it, and you can try to understand the whole landscape of like validity conditions and Byzantine agreement. Now, I'm just gonna ask you before the business meeting to run our protocol to decide what kind of wine to drink and how to behave in the meeting, and with this I leave you and I take questions. Yes. Thanks. No. So the question is like to do this intersection of convex schools, you need to know all the inputs. Well, you don't need to know all the inputs. I'm just saying you look at the 4 values in the common view. The common view does not have all the inputs. It has at least n minus ts of them, and that's the best you can guarantee. But all the parties know the same values in this common view, so you are fine. Does that answer the question? I mean, we can also take it in the coffee break. Yeah, no worries. But they all view the same thing. It's a common view. So the first step of the protocol is you run call set agreement. After that, you do part 2, which is this like local thing. That's the thing. Okay, that also answers your question. Yeah, sorry, I maybe jumped a bit too fast through that. But again, what I want to sell is that we have this call set agreement protocol. Maybe people can make it faster. Message complexity, round complexity. That would be cool. Anything else? Thanks all.
Borrow this. So in exactly 31 minutes, we are going to have the business meeting starting here. We are going to have very important matters in the business meeting, including, for instance, who is going to be running this whole show in the future. So please don't even consider leaving this conference site before attending the business meeting. Thanks. See you in 31 minutes here.